is the 5-minute call. We start in 5 minutes.
Make it 40 if you want. No, that's fine too. Yeah, please.
I mean, I'm not going to gong you off stage. Let's put it that way. So if you run 46 minutes.
Yeah, I mean, stop me the questions when I start trying, but until then it's fine.
I would like to gong you off stage, though. But you'll have to make a lightning talk for that.
Please do.
And that reminds me, like, how many slots do we have open for lightning talks?
0.
0. Can we kick the jokester out and open up a slot?
We gotta have them. Give you more reason to hit the gong.
Yeah, like I said, I'm only letting it happen if I get the gong after a big fucking joke. So.
When's the lightning talk? Tomorrow? Yeah. Tomorrow, 1:30.
You said 1:30. People are going to come back happy from lunch and have to put up with that.
Yeah, they're just gonna do some computer science form, and you're gonna use your shitty math. Yeah,
See, there's jokes, there's dad jokes, there's puns, and then there's.
Then there's gong worthy jokes. Yeah, I mean, you said to me last week.
It's difficult for the gong, to be honest.
You said last week to me you prepared new ones. Did you yell at everybody?
Yeah, that's why they're all coming up. That was my spot. So far, I don't feel like putting on my jacket already. That's good. Any housekeeping before we start?
None for me. I guess later at the evening, for the last talk, just tell everybody we can meet at the Travel Lodge. Yep. City Road.
Yeah, I'll do that after. Okay, wow. This sounds like perfect topic for the morning after DConf.
I mean, there's good fun in the title, so it should be good fun.
Oh, yeah. Let's see how hungover everyone is. Is everyone even here?
No, not at all.
No, they're all hungover in the hotel.
Yeah.
All right, let's just go for it. Welcome. Welcome, 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 welcome. We're working now. Hey, welcome one, welcome all for those that are here for the morning after DConf. Where is everyone?
Sleeping.
Sleeping? That's not the term I would use for the morning after DConf. Passed out is a bit more likely.
Fair enough.
So, I mean, everybody that survived, I assume you did not drink beer last night. Wow. Well, you're still high energy, so, thank you. It's much appreciated for that. Okay, let's just get this kicked off then. The perfect topic for the morning after DConf, creating a data-oriented parser/AST/visitor generator. This sounds pretty technical. Robert, it's all yours, mate.
Thank you. Good morning, everybody. So yeah, Ethan missed the important part, good fun. So that's in the title as well. For the last couple of years, I usually have been presenting on stuff I did for work. And this is not that. This is just stuff I like to do, which I think is good fun. So I really like writing parser generators. I think it's awesome. The interesting thing is, though, I don't need them. I needed a parser generator once, and I used it, and it's OK. And I don't really like to do something useful with it. I usually stop somewhere after the AST part, like sort of doing the code generation that Walter did and actually getting something that executes. That's not that much fun for me. So let's really stick to the fun parts here. And if that's not fun for you, well, drink coffee, have a relax or whatever. So in the good old days, when you use Yak or something similar, you get something like this. You sort of put your grammar in, and then there's a block of code that you can execute. And also there are sort of some dollar symbols in there, and you really have to know what to do. And you don't really get much for free. You basically get a parser, and that's it. But you don't get an AST, you don't get a visitor, you don't get Alexa. You're sort of really limited in the options of what you can get. And I sort of wanted to do a bit more, because creating the AST, I find is usually very linked to the parser itself. So if you change your grammar, chances are that your AST is changing as well, which also means that the visitor is changing as well, or the classes that are sort of using the visitor have to change. And I thought, well, how hard can it be, right? Famous last words, as always. And I sort of tried to do a thing where you put in a grammar, you get out a parser, you get out the AST classes directly, and you also get a visitor that you can subclass. And that's basically what resulted in a thing I called DASA. I know the name is really shit. It's basically parser with a D in front, so it must be in a good programming language. So, and I used that for my GraphQL implementation, and it just works fine. You get an AST out, the grammar is fine, you put it in, you have a visitor, and then this one was the actual instance where I had to do something with a visitor to actually finally execute the queries I got with GraphQL. And the grammar, I was young and naive, and I used YAML as an input language. So basically, the idea is the definition is sort of the overarching name for the rule. And then there are 3 sub-rules, O, F, and T, because obviously typing is difficult. So O is for the operation definition. So you can actually in GraphQL define operations like this is my mutation, and it's taking this argument, these arguments, and then it's sort of crewing these elements. You can also define fragments, which is a fancy term for macros, basically, because the GraphQL people also apparently don't like writing. So you can basically create a block that you can insert into different places. And also, as it's a type query language, you also are able to define your types. And this basically does it. The stuff after the hash is a name for the elements in the AST. So you get to name the elements in the AST. And if you put that into DASA, you get, among other things, one class called definition that is inherited from Node. And it has a rule, which is basically an enum with the elements, what was it, O, F, and T. And you have the 3 sub-elements of the production. So far, so easy. And you do that for your whole grammar, and you're done. The class itself also has a couple of constructors to make it nice and user-friendly and easy to understand. And also, what is important, to have code completion, because this is not done at compile time. It's sort of a pre-compile step. I would think there's nothing in Darza that couldn't be done at compile time, but I've just found it more convenient to generate it ahead of time, also because it's faster, but also because you get code completion, which was the more important reason. And you get a bit of boilerplate generated for the visitors. And the sort of more interesting thing, obviously, is the parser itself. So you get a parser class, and for each of the rules, you get a function that gets called. And yeah, basically, the recursive descent parser you would very likely write by hand is written by Darza for you. So first of all, it figures out the first set, so all the all the tokens that actually sort of define where the rule starts. And then if you sort of found the token for instance, the operation, you recurse into parsing the operation. If it's a definition, you recurse into definition, and so on and so forth. Very easy. Also, what is cool, you get somewhat sane error messages. As you know, as Darza knows what data to expect, you can at the end say, hey, I got this, but for instance, I was expecting an opening parentheses, but I got a closing one. That doesn't fit any of the rules we are currently at. So really simple so far. Like the first operation type, as I said, is basically checking the type of the current token to see if it's, for instance, here the query keyword, the mutation of the subscription keyword, which is basically the first token in any operation in GraphQL. The visitor, again, is relatively simple. We know from the enum inside of every class or every node what follow nodes or what nodes to follow, so we can generate a visitor. And I added two things which I found to be really useful while implementing GraphQL is I have an extra sort of callback for entering and exiting a definition, or pretty much every node, because quite often I didn't really need to know what was in the node, but I needed to know when it started and when it stopped to do some stuff in the visitors that I created. And I found this really useful. And I mean, again, I would assume if you write a visitor by hand, it will look very similar to this one here. So, and then if you want to have a visitor, and here a very small count visitor that counts the occurrences of definitions, you just do that. And I omitted the override keyword because, yeah, looks nicer this way on the slide. And the interesting bit is, so I would say in general in the D community, there is a bit of hate against classes, quite often for good reason, but sometimes also not. Overriding a function and then using the super keyword to call the original implementation is extremely useful for visitors in this case, because as we saw previously in the definition, there are certain, depending on the state of the node, we have to call the visitor again with different fields out of our class. And not having to re-implementing this, but just calling super is just super. So, I mean, sometimes classes are bad, but sometimes they're awesome. And I think this is a good instance where it really saved a lot of code and makes the code easier. So, doing a bit more, the recursive descent parser is basically created by taking the subrules of a rule and turning it into a prefix tree or trie, however you want to call it. And that obviously results in a bit of nesting. So going from the first rule here, the TDS, we check for our on. Do I have a pointer? Yeah, but you can't see it. So on line 2, you check that you found the on keyword. You pop that from the Lexa. You check for the name sort of in there and continue down. And the cool thing about the try is if multiple subrules have the on keyword as first thing, it just sort of works out nice, and the recursive descent parser really sticks out here. The only sort of difficulty there is that you have to write your rules in such a way that the there is no first conflict, meaning that at some point, the DASA needs to be able to decide what subrule you're actually in. And also, if you are going to like a different rule from one rule, and there are possibly multiple options, you have to make sure that there's no first conflict sort of on the first token for those rules. But DASA will complain if it finds such a conflict, but that makes writing the grammar a bit more complicated. You can insert handwritten rules in DASA, because every once in a while recursive descent with like a one token look ahead is not good enough. But sure, at that point you can just write a bit of code, insert it, and DASA is happy. Yeah, this one is just continued, and at the end you can see we have again a sensible throw message there, and everybody's and usually the error message that you get as a user of the library then are reasonable enough to see what went wrong. And this works, and I did most of that back in 2018 before actually getting my new job. And this was fun, and I worked on GraphQL with it, and it just works. But over time, obviously, you learn stuff, you get new interests, and for the last year and a half or so, data-oriented design was sort of creeped up on me a bit. While using SQL a lot, or Postgres to be specific, and also while programming, and I realized, maybe there's something to explore there. Basically, the idea is to put data that gets accessed together into a structure, together into an array. Because if you look, and as we're going to look into here a bit later, performance nowadays is usually not dependent on how fast the CPU can do adds, multiplications, bit operations, or whatever. It is how fast can get your data from the RAM to the CPU, or to like L1 cache and then into the registers. And like also, if you sort of looked into the database space the last couple of years, there was a big push from going an array of structs to a struct of the array. So columnar databases are now creeping up in many places and are obviously faster. So, or faster in some regards. For instance, let's say you have a big table with 15 columns, but you would just want to compute the sum of one of that column. And if you have to load the whole table from the database and you're just reading one int out of 15, let's say, obviously you're going to lose performance compared to you're just loading all the ints at once and just summing them up. It's obviously going to be faster. So yeah, basically know your access pattern will result in performance. And sort of to get an idea of that, if we do any instructions on pretty much any hardware nowadays, it's somewhat between 0.25 cycles and 10 cycles. And basically the memory that you have is all the registers, and roughly speaking, you have like 128 bytes there. And then going to L1 cache, sort of you can already expect to wait for like 3 cycles to get the data from L1 to the registers to actually do something with that. Obviously, the size increases, but then if you go to memories, to RAM, you have to wait 100 cycles, and there are a whole lot of operations that you can do in 100 cycles. And obviously, the size of the RAM, like how much money do you have? You can buy terabytes of RAM nowadays, but the performance really comes from having the data close to the actual operations units of the CPU and operating on them without having to go to L2 or 3 memory. And L1, again, is somewhat interesting. You load it by cache line. And if you think about it, if you do operations on an array, most of the time, it is very likely that if you read one element, you're also going to use the next element to do some of your computations. And also, while sort of working in that space, I sort of realized 64-bit pointers are extremely wasteful. Linux, or sort of the Linux of 2024, only allows you to address 2 to the power of 48 bits. So you already have quite a few bits that are not set. This laptop only has 2 to the power of 39 bits. and it only has like 16 gigs of RAM. So who cares about pretty much 32 bits of our pointers? Maybe there's something that we could exploit. And I would say uint indices are pretty much always good enough to address every memory that your program will ever need. So, and you already saved like half the size of a pointer, so yay, basically for free. But then obviously, if you sort of connect that back to the parser generator, it's called abstract syntax tree and not abstract syntax array. But if you really think about it, what is a tree but indices into the ultimate array, which is main memory? Like it's basically you have the main memory, your nodes are sort of placed in the array called RAM somewhere randomly, and you have pointers into it. Why not think of it as one array and have indices into it? Pretty much the same thing if you think about it, minus a couple of nasty casts in there, but who cares? So how hard can it be to turn it from a tree and a class-based thing to an array and struct-based thing? Actually, it's not that difficult. So instead of having pointers to your nodes, you have uint indices. And then in the parser itself, you have a couple of arrays for each of the rule types that you have. And then you just point into that. So that's my talk. Thank you. Have a nice day. But obviously, there's a bit more that we have to do. So again, taking the parser generator part here. So we are still doing the parsing, but the return types, for instance, on line 4 or line 10, are no longer pointers or references to the class, but basically the subrules now return uints pointing to the array index of the thing that they returned. And then on line 6, for instance, as we have seen, or as we can see, we created a selection set for our operations definition. We append that to the array and then return the index to it on line 7. And I sort of got lucky there as I implemented DASA and the outputter, sort of turning the data structures and the trie into the actual D source files. I did this via classes, so I could very easily subclass my outputter class for the original thing and turn it to this one. So I think that is another good place where classes just work fine. I mean, it's not that performance relevant generating the whole AST parser and visitor for GraphQL, which is a relatively big grammar already. It's basically when the key up event comes, the generation is done. So all good. A bit more parsing is basically wherever you at the beginning had a uint wherever you had a pointer reference, class reference, you have an uint now. So that works just fine. The visitor then again is also, as you would think, instead of dereferencing the element inside of the current node we are visiting, you just get the index and reference the parser and that array and take the element out of there. Also, that's, probably as most of you would have expected at this point here. Now, sort of for an interesting bit, I was really hoping to say, hey, put this switch into the next time you use DASA and get like a 20% performance increase. But actually, on my laptop here for the last couple of days, I have been getting a consistent 20% performance decrease, which obviously is not the thing I wanted to present, but maybe let's think about this for a while. So I would like to start with the last line here, the memory the thing actually used. So with the class-based one, and I took the GitHub GraphQL schema definition, which is a file of 65,000 lines, so not a small grammar. So and with the class-based one, sort of doing quite a few inefficient things, we already have like 300 megabytes. With the struct-based one, we reduced that to just below 200. But while time goes up, L1 cache or data cache loads go up, and cache misses go up, and also, it's slower. And there are sort of a couple of interesting things here. First, obviously I opened up Valgrind to see where the performance is going, and parsing and actually doing the accessing of the data in a count visitor. So I implemented like the count visitor from before for every node, and basically as a debugging tool to see if the new implementation with structs yielded the same result, meaning that every node was, or every node type was counted the same time between the class-based one and the struct-based one. And that is true. They all counted the same way, or they're counted up the same way. But actually, the performance of the whole test goes into lexing. So first of all, measure the right thing, meaning that the bottleneck for parsing the GitHub GraphQL grammar is definitely not the parser, it's not the visitor, it's the lexer. But luckily, this is talk about a parser generator, which I like, so all is good. But then also sort of a bit more reflective, right? You can commit no mistake, but still lose. That's not really weakness, that's just life. Sometimes it doesn't pan out. And I think that also comes up in our daily lives whenever we do something. Maybe we have a good idea, maybe we think it's brilliant, maybe we think we are brilliant, but then life happens and, well, we get schooled a bit. So now I want to sort of continue the thread of data-oriented design a bit further into what else can be done, where improvements can be done, and maybe what sort of can bleed into other areas that is not just parser generation. And as I didn't have really good title for this section, I called this structured ranting. So even like the grammars or the productions for the GraphQL grammar get big rather quickly, but there's always sort of the problem that the enum define or selecting which rule has to be stored, and that is not a uint, that is usually a byte from the size y. And I thought to myself, well, it should be possible to do a bit of bit mapping here to make this possible as well. D has this; it's just behind the switch, and it's not documented. And there is debate about should we do it C-like? Is it okay? Is it safe? Is it not? I would say this is what I would consider to be a sane use of it. Obviously, a uint with only 28 bytes is less than having 32 bytes, which is obviously true. But I think it's fine in this regard, because even though I would think that the GitHub GraphQL grammar is probably one of the biggest ones out there, 28 bits for the number of operations is still way fine. I mean, there are probably a few hundred in there, and with 28 bits, it's like 32 million or something, or 33 million elements you can index, so who cares? But then also, we can press this again into a very nice form that is easy to load into a cache line, and we can just move on. So, yeah, bitfields and structs, have another look. I think they're not as insane as we might just think. And the other interesting thing that sort of, bubbled up is that if you have a tree, storing that on disk is sometimes a bit tricky, because you have to pointers, you have to sort of follow the pointers, and then when you restore it, you sort of have to recreate the pointers. The cool thing about arrays is you can just sort of say, okay, the next thing is going to be so many elements long, and then just write that to file. And reading that again is also just the other way around. You read the first 4 bytes, you say, okay, this is how many elements of the next thing I have. As long as you don't change the ordering of your arrays in the parser during writing and reading, you are fine, and you can just sort of load that from file, cast it, and be happy. And obviously, if you do that with a memory mapped file, you can even simplify that and probably get quite a bit of performance boost. And considering that in the good old days, the HPP files, sort of the precompiled C++ headers to increase performance were a thing, and also D had a similar thing, I think storing sort of the AST raw on the disk and then just sort of memory blipping that into existence is most likely a lot faster than sort of doing it the more traditional human readable way. So the interesting bit is, or sort of doing the non-so-fun part is, I really don't like writing lexes. They're just so fiddly, and when you are sort of at the parsing stage, you have a nice rule, it all makes sense. But just think about D, for instance. If you have a number, a dot, you don't necessarily know if it's a float. It could also be another dot following, so you have a slice operation. And that is just, it just gets messy very quickly, and dealing with the Unicode symbols and all that. So lexers are not really fun. But from my benchmarking, as alluded to earlier, there is probably quite a bit of performance that can be gained by taking a closer look, and especially taking a closer look at the token type. So the current token type in the GraphQL implementation is something like this. You have your token type, and you have the token itself, and the token has a value. And it also stores the line and the column the token was created. But for most things, that information is irrelevant. Like, I only need the line and the column if something fails. And also, for most of the tokens, the value is irrelevant. Like, I'm not going to store the opening parenthesis token and then also store the string of the opening parenthesis token. It's just, there's an enum set it's to open parentheses, and it's all good. So, and also, it's quite a lot bigger than our uint indices that we use to index the tree itself. So again, using bit sets, when we can just count the elements in the enum, say at this point 7 bits are enough to store all the possible enums. And then also, we can turn the value in itself into a value or index. And for the token position, obviously, when we get a parse error, it would also be nice to sort of say, hey, we are here, and we started that rule over there. So just basically have a circular buffer of the last, 16 token positions in your lexer, and be good. And the other thing, again, similar to how the AST nodes were stored in the parser, there are only so many value types in GraphQL that need storing. So they're ints, floats, doubles, and strings, pretty much. That's actually everything you get. So in the token itself, we have sort of a value and index. And I would say with 25 bits, you can probably store most ints that you come across in real life. So we can already sort of store that, embed it into the token, and not store the index itself, because obviously having to go to the array to get the int is going to be slower than just doing a few operations when the value is already in the registers to figure out what int is in those 25 bits. But if it's not there, you can just go to the array and get that. And sort of, I said strings are also a thing, and strings don't really fit into that, because currently as this looks, you could just take the lexer the same way as you took the parser and just write that to disk and read that from disk. But for strings, obviously, if you sort of load this GraphQL mutation from a buffer or from a file, most of, like, all the data is already there. So if you have to reopen that and then have the 8-byte indices into that one and the length, it might just not be optimal. But if you actually look at this, the only strings we are concerned about are like counted just 20. There are 20 unique words that we actually need to store here. So on that regard, obviously history already sort of given us a tool to do this, and it's basically called string interning or array interning, how you want to do it. And doing this in D is pretty trivial. So I have a thing I call the small string index. Instead of size t's, it's a uint of the index and the length. And then there is a struct called the string interning thing. And in it is the string itself, which is basically going to be a concatenation of all the strings that we want to store. Then there is an array of indices that get used to point into that string. And then there is a map to basically do the uniquing of them. So, and if you then want to insert a string into this thing, you pass in the string, you check if it's already in the map. If that's the case, you dereference the index already stored. If it's not in the map, you create a new small string pointer, get the current length of the string, because that's going to be your start index into your string map. You get the length of the string, because that's going to be your length. You append the string to the str string of the string index. You append the index, and then you just return the index, and you're done. And by this way, you're compressing the strings that you actually want to store. You also have something that you can write to memory and then return, or write to disk, sorry, and then reopen and have that. And also, this is actually, for me personally, the first real use case for const. So when you reload the string map or the string interning thing from disk, you wouldn't reload the map, meaning you can no longer insert any string, or the information that needed to insert data into the string is lost. And but insert is the only non-const operation here. So if you then have it const returned from disk, well, you have your constant string interning thing that you can index into, but you're sort of safe by const to do any errors with the data inside. So I find that really useful. Obviously, the construction of this thing is very slow, but if you know that there is a limited amount of strings that you have to read many, many times over, this is most likely going to be, or extremely likely going to be quicker, because the amount of data that you need is a lot less. And also, comparing if two strings are the same is just a uint comparison. So that's probably as quick as you can get. So I'm probably a bit ahead of time, but that is fine. So first lessons first. Measure first, and also think about what you want to measure. Obviously, I measured the wrong thing, but I learned afterwards that what I wanted to measure. So it's definitely an iterative process. I hope you can see why parsers, AST, and visitor generators are fun. I mean, you put in a bit of grammar, you put it into it, and you get a lot of code out, a lot of value out. And I've seen it time and time again in like presentations at DConf, like generating larger programs from a bit of input is the thing, and I haven't really seen it in other languages as much. So I think we have to, like, probably before measuring, the first thing is how can we do a tiny bit and get a lot of with D, and yeah. So also data-oriented design isn't really a new thing. I mean, if you look at pretty much any C program from the 1990s, you will find some very size-optimized buffer with weird indices into it, and you can't really follow what's going on. But for most cases, I bet it's some data-oriented design, because the engineers realized, hey, we have limited bandwidth to our memory, we have limited caches, and we have to make it fast because we have some hard time constraints on what we are trying to do. So also, one thing I find very interesting and is quite often helpful to think about. So in the field of databases, database normalization is really still a thing. Thinking about, but it's mostly used to make sure that you don't have inconsistencies in your data, so that you don't store somebody's telephone number in 15 places and you read the wrong one every time. It's more about that part, but also what results from it is that quite often you get less data that you actually need to store without losing any of the information. And they're interesting concepts to connect different pieces, because everything is stored in tables. And usually what I find is that when you get to one of the higher normal forms, you basically already compressed and organized your information in a way that you're also reading it, which from sort of the intro realizes or gives you a way to get quite a bit of performance into there. And just in general, I think we ought to more often look into the past for inspiration. I know large language models are all the rage now, but database normalization has been here for 40 plus years, and it's still an extremely valuable tool that will likely yield, at least performance-wise, a lot more performance than large language models will ever yield. So, and that goes in many domains. Like, I mean, just realizing how little compute and memory power they had to get a rocket to the moon and all the calculations they had to do. They had to be smart and resourceful about the resources they had. And there are things to learn there. A link to the thing, and I'm at the end, and I'm, 10 minutes quick. Yeah, a bit early. So, question times.
Same deal as yesterday. If you're not in the room, you can ask on the internet.
Testing. Sorry. I have a question about the data usage. So you gave the example of like data normalization and keeping track of repetitive used strings to keep in like a map, so you don't have to keep storing them again and again.
Yeah.
And while that reduces the total volume of data, you can think of this as walking along the same path as something like the zip program. So zip also reduces the total amount of data, but the amount of data you have to store at the moment of your processing, what fits in the CPU cache, is bigger because you keep having to jump to your index of the total thing of strings. So zipping a file is slow. Now, when you're parsing a file, you may be looking at keywords like while or whatever, or with capitalization, without capitalization, but you keep indexing the small piece of the file that you're looking at right now. So it's in total more data, but it's faster for the CPU because you don't have to keep looking it up or go into a cache or anything. And then the second question is, do you have an opinion on a D library called pegged, which I've used to great success? I'm curious what your opinion is.
So for the first part, I would most definitely not store the while in the string map. For that, it's just an enum as its keyword. So you're not storing any value for that at all. But yes, you're right. It's more about like how often are you reading the text there and what are you doing with the text ultimately. Obviously for construction, as I said, that is going to be way slower because you have to look up the map and then all do the things. And obviously, as you said, you're also going to get cache invalidations when you index it again. So like as always, it's a trade-off, and you need to know what you are trying to measure and what you're trying to improve. So yeah, but I think sort of the more interesting bit there is, especially for programming languages, like after you have parsed it once, chances are that you have to actually parse it again are very slim, because like how often does stdio .d change, right? But you have to reparse it every time, and if you could just memory blip it into existence, and that part at least is gone, or that part at least you don't have to do. And then also for the semantic phases, if you sort of get the outputs of the visitors, and that gets stored just as a memory or gets loaded as a memory blip, that is obviously going to be faster than redoing it again. On pegged, I used it, but I alluded to it a tiny bit. The thing I don't like the kinds of grammar they accept, because I think as a human, LL1 is as difficult as I can understand. So recursive descent is sort of my drug of choice, and the red part, or the the pegged parsing algorithm is a lot more complicated. Also, the ASTs are not so typed that from the name itself you can see that you have an operation definition or a fragment definition. You can't see that. And sort of the probably most important bit about that I don't like is that it is a compile time thing. So you don't get code completion on that. At least not now. Where's Jan? Probably have to talk to him about that. So, I mean, but it works, and if it works for your use case, most definitely use it. But I had sort of other requirements, but then also I found this to be fun. And obviously that is a really good reason to do it yourself again.
Did you, Robert, did you produce, I may have missed it, I wasn't here all the time, but were there some performance numbers on the on your Lexing's part, you know, the less fun thing that you did at the end? I noticed you did a bunch of data-oriented optimizations there, and I was wondering if you had some performance deltas or comparisons on those.
Yeah, unfortunately, my data-oriented design with structs and array was slower, about 20%. But I sort of measured the wrong thing and didn't really look before into what was going on, and it's basically all Lexing that takes the time.
Okay, so that was incorporated in the 20% numbers. The Lexing that wasn't broken out parsing, that was the combined number. Okay, thanks.
So another advantage that I would expect from storing a tree as a flattened in an array, I would assume, is that you can pre-allocate the array instead of allocating each node.
Yeah, and that's absolutely, and that's sort of one of the things I looked into yesterday a tiny bit, but sort of on the surface here for the comparison, I found that to be cheating a bit, right? I could have looked at the parse result and say, hey, okay, I'm needing like 20 elements here and 30 here, just pre-allocate and be happy and sort of beat the old thing, but yeah. But most definitely, in production, you would do that and probably have sort of a heuristic from saying, okay, I'm having an input of, don't know, 16,000 characters. Most likely, this is going to be how much memory I'm going to have.
All right, we have a question from Ricky on the internet. Is there no UAX31 support?
Come again?
UAX31 support? Yes, no?
No. Pull requests welcome.
So just to be clear, like when you implemented the array-like tree, so the Lexer is the same, right? Did you have to so the 20% is coming from that. It's not from
and that's sort of the interesting bit. On my home PC, actually, I sort of got like a 2 or 3% improvement. But the last couple of days, I was using this laptop, and the optimizer in LDC is doing something I can't explain. Like for whatever reason, it sort of, don't know, is smarter with pointers than it is with indices into an array, which totally baffles me. I really don't know why, and hopefully Martin or somebody else can explain to me why.
Is it possible? So I don't know exactly how the code looks like, but is it possible that you're allocating the structs and then, I mean on the stack, and then you're just copying them into the array? Because if you're passing them to functions and if it's not by ref or something, that might be it.
That could be, I mean, I'm doing that. That could be a possibility, but like compiling optimized, I would assume it's sort of optimizing that away a bit. I mean, it's definitely, I could check that relatively quickly. But I mean, instead of doing that, the class-based one has to basically malloc the space for a class, right, and sort of copy that into there. And I would hope and assume that that is going to be slower by default than, copying a struct. Maybe?
It really depends on what you're doing with the struct from multiple. I mean, if you're passing by value the struct to different functions and so on, I don't know.
Yeah, but for the visitor, I'm passing by ref. So there I'm not copying it. And also the visitor that counts the occurrences of the nodes, I mean, that was like 0.1% of the whole runtime. So in both cases.
Hi. I know why it's got slower. Yeah, I'm not surprised at all. Basically, I'm glad you had fun, but that was a very stupid thing to do. If your Lexing and parsing got 20% slower, and Lexer was the most part of it, it means your parser got like 3 times slower, and I'm not surprised, absolutely, because you are grouping the wrong things. You're accessing you need to look at which data you're accessing in the memory. And when you're working with AST nodes, if you're looking at, say, addition, you are not interested in what will be the next addition and then the next addition. Or if you see a string, you're not interested in what will be the next string in the program. You're interested in what will be the arguments of this particular node. So you need to group in the memory not different types of nodes, but you need to group the data of one particular node and then another node. So basically, what you need to do to use cache, to make it cache friendly, you need to a different allocator that stores things that created at the same time at locations that are basically close together, like a bump locator. So
okay.
And with your approach, basically you're grouping in memory their own unrelated things. So you are causing yourself to have even more cache misses, and we see it in your data. You increase number of cache misses, and also previously your program just chased some pointers, and now instead of chasing pointers, you do first array bounds check, and then basically the same chase pointers. So you added bounds check into every pointer access. So of course it is slower. It's obviously slower. I'm not surprised at all.
So I absolutely agree on that part on the accessing, but that actually hasn't changed at all. And on the construction side, I would have assumed that that's not really that relevant. And then sort of the follow-up question is, I thought about that as well a bit. And you basically have like a binary heap in the memory, but it's not definitely binary because obviously you can have multiple nodes. And then unrolling, I gotta put this, basically what I thought you would have to do is have a node that has the maximum number of indices, which then would lead to most of the time, most indices would be unused. And I wanted sort of to avoid that. I'm not quite sure how to square all those different requirements there, and probably we can, looks like you have looked into that a bit more, and maybe can give me more pointer. Yeah, sure.
So I have been trying out using a tree data structure with indices as well, and what I found annoying was instead of with pointers, you can pass them to a function, and then that function can call a method on it, returning a new node, and you can go like .next. But with indices, you every time have to make sure you have also the array passed, and then the user of that index has to index the right array. But recently, I found a C++ library which it stores indices internally, and then it hands out tuples of a pointer and an index, so you can still call methods on it. So my questions are, have you found the same annoyance, and have you explored similar solutions?
I haven't found the same annoyance, but what I do in the visitor is instead of passing down the index, I basically pass down a ref. But then obviously you have to make sure that you don't store the ref somewhere. I mean, you technically could, and you could also compute the index from the ref and the array. But yeah, I sort of had that annoyance a tiny bit, but in this regard, not that much. But I can definitely see that being annoying rather quickly.
Just to reiterate what the previous commenter said, I think this is a classic case of malloc having natural locality, since the calls to malloc are for things that are related and next to each other, and then you transform it into something that is not type-based. But I think it would perform better if all the nodes were in the same big slice of memory. And this is why with a custom allocator, sometimes you end up being slower than malloc because you didn't preserve some locality properties you already had.
Okay, yeah. I mean, it's definitely worth a try.
All right, we got time for one more question if there's a good one. It needs to be a good one, mind you. No, apparently it's too early for good questions. Well, thank you, Robert.
Thank you.
All right, so we got about 10 minutes to the next talk. Be merry, have tea, coffee, probably coffee. You all look like you need it. And back here in 10. Done. You finished in like 35 minutes, not 50. Yeah. All right. Who's our next speaker anyway? Today's Wednesday. Okay, we got Max up next. There he is. Welcome. Yeah, no, that's fine. You're late. Robert panicking. It's like, oh, I don't know if you might need the full 50 minutes for my talk. He wraps it up at 35. Yeah.
I've been slightly sneaky though, because my demonstration of a build system is actually the fact that you can the smallest demo I can come up with that hits all the bases is actually showing how you can like put an auto format check as part of the test suite in the build system.
Okay.
So we have to sit here for half an hour, see your computer compile the thing?
No, because I've taken a screenshot. What I wanted to do was to have the remote execution thing call my box back home. But it's just I can't, I'm not setting up work.
I can relax now. Yeah.
That's good. Well, we'll get one of the audio guys up here while Max up correctly. Yeah, go get it. I would say go get a beer, but it's not beer time. Where's Attila? I bet he's drinking a beer right now.
There's nothing dense, so we kind of want to play with. Yeah, but this
I feel like there's
bringing.
going to be less interactive talk here for some reason.
Oh, you mean the Irish guy? The Irish guy, yeah. Who, if I recall correctly, blagged a bunch of beer off people, didn't pay, and then left. And then switched, and then 2 days later stopped using D.
Yeah.
So, get the bag, queen. Hang on, let me, what did I do with it? I thought I brought some more, oh, yes. Doing everyone a favour because I have way less slides than I thought I would. So lots of time for riffing with questions at the end. Yeah. I like that a lot more than actually presenting. Like I enjoy the questions a lot more than the actual. Because people usually ask the things you forget to say in the. Oh. Is Attila here today? Do we have Attila? No, I walked off.
No, I've been working out how to get it sounding really good for a really long, drawn-out thing instead of just going.
Do you do the accent as well?
Which accent?
Oh. Maybe not polite to say.
Which accent?
Maybe not polite to say.
Well, maybe not, yeah. Oh, I think I know where you're going. Yeah, maybe it's a bad idea to talk about. Hello, everyone! Wow, that took a while. Sure, let's applaud our chatter. Come on. No? Hey. See, that's the energy I've been looking for this entire time, and it takes us just talking on stage to get it going. Be better, crowd, come on. Anyway, should we do a bit of housekeeping? Yeah, remember all those lightning talks? It turns out we're all full up, so if you've got a clever idea, next year is going to have to be it. But now we got Max here, who's, what's this? This is like your third DConf talk, isn't it?
Yes.
Third?
So
Third.
I'm going to rock the microphone.
Yes, that's what we like to hear. Max, rock the microphone.
So, yeah, I'll just preemptively apologize. Right, so I am going to talk about build systems because anyone who I've spoken at about this will learn that I'm quite interested in this one because it's new. Because build systems are like aphorisms about opinions, and everyone has one. Fine. Fine. They're like recursive aphorisms about opinions, and everyone has lots of them. So everyone basically here, I assume that knows we can automate processes with them. We can capture information about our builds and so on. They're very useful. We have lots of them, e.g. Make, but also Excel. Excel is a build system. They're all quite different. They're all subtly different. So, for example, like Ninja and Make have different semantics, but kind of look quite similar. Without going into that too much, there's a very, very good paper called Build Systems a la carte, where they effectively build lots of different build systems in using snippets of Haskell, for example, because it's written by that kind of programmer. So for example, like the way that they can express like the difference between the way that the things you need to do to deal with like dynamic dependencies, for example, within monadically and so on. You can do anything in a monad. And the point that I want to get at is actually not so much about building things as much as I think the tools that we have, both as an industry outside of basically a few kind of concentrated places where people spend money on this kind of thing, are quite poor. So, for example, we throughout every DConf basically there's always a lot of like how can we make the horse faster? E.g., we have like dub, redub, reggae, and so on. There's people using Meson and things like this. And they're all hobbled by various things. So, for example, like dub, as far as I'm aware, historically was trying to copy NPM or something like that along those lines. So anything downstream of it, reggae and so on, can only extract so much. You can only extract so much blood from the stone, if any. And I think there's an analogy to be made with testing in that you can view a set of tests about a program, which is you prove the absence of a bug, you fix a bug, you had a test, and so on. But more generally, they're a collection of assumptions you can make about a program, which is why we go to very long lengths to test things, and sometimes you put a lot of effort into, for example, to be, for example, like testing what happens if like a file operation fails, for example, is quite annoying, but it's worth doing sometimes. And I'd argue that our build systems don't capture enough information about what we're doing. So there are common problems that occur quite a lot in software, where pretty much regardless of language, and even like choice of tooling a lot of the time, you end up with things that are slow, complicated, and brittle, and so on. And we get, like, if anyone's ever worked on a project that, for example, that has a script that you have to run, which like mutates your machine first, so you can actually build the code, for example. I think a lot of the stuff is basically terrible. And one thing that Peter Thiel likes to point out is that in the kind of modern world, there's been a lot of progress in the kind of the bits. It's like immense progress in software, but not much in like atoms. So, for example, you have a very modern software and so on, but the actual world you live in, with the exception of basically your phone, you might be, for example, if you went on the tube today, you'll notice that some of the tunnels are like 150 years old and the things don't work anymore. And I think this is sort of fractally true inside software, where like the code for the most part is actually is probably better than ever in many ways, but the plumbing around it, there hasn't actually been that much progress, and in some ways we've actually gone backwards. If you imagine like sitting down and writing out a make file for a project will often get you a more pleasant experience sometimes than using Dub and so on, kind of controversially. And these are kind of the thoughts that I'm kind of pinning on the door, if you will, where we've simultaneously ventured too far away from the sort of spirits you get in a kind of old-fashioned make file, in that there's a benefit to being forced to write things down explicitly. In the sense, because it's a sort of hormetic effect where the a little bit of pain is good for you, or radiation, depending on who you ask. But then equally we can't just go and use make files, for example, on a big project, because they're still far too permissive, and also like no one has time to actually sit down and write them. And I think there's a solution in the form of that people have thrown money at this before, both kind of metaphorically, and they kind of just throw money at the problem and also make it go away, but also because it's proven to be the profitable in terms of developer productivity, like easily provable, for example. So like Facebook's new, what this talks about, this build system is probably the product of tens of millions of investment, at least by Facebook, and it's paid for itself, or at least they say it's paid for itself, based on their internal metrics of the throughput they get from the developers and the feedback loops and so on. And the solutions that people have come up with are all vaguely, they all fit within the name of the so-called declarative build systems, of which there are basically a handful, and they all have their roots going back to Blaze inside Google, if I'm not mistaken. So they wrote Blaze inside Google. People leave Google, they want Blaze elsewhere. So they ran away and then wrote Buck at Facebook, and I believe Pants at Twitter, and then Google open sourced. I think which is sort of it's bits of Blaze, but also it's its own thing in the form of Bazel, which is probably the most mature offering in the open source world, because Buck, and then Facebook threw Buck away and made Buck 2 as of sort of release as of last year or so on, something along those lines. And in brief, Bazel and Buck both share the language you specify your builds in. They actually share, called Starlark. And you write things like this, and then you build stuff. It's not particularly shocking, but where things start to become interesting is that, for example, the D binary, for example, can, sorry, the libraries may be more interesting, but you can, for example, have the tests and documentation generation and so on encoded within the build implicitly as part of the declaration. Thus the
declarative moniker. And just on the Buck actually already has a like if you run it now, it does actually have a D binary, but it's technically a stub, so it doesn't work. That's what I've been trying to work on. So the difference between this and say like double whatever, for example, is that it enforces they enforce very aggressive constraints on what you can and can't do. So, for example, if anyone's ever had the problem where you don't declare like a header file correctly in a make file, and then things don't get recompiled when you change things because you forget to include the dependency, for example. If desired, these build systems, for example, can actually explicitly, if you try and use something that you didn't ask for, they'll just fail, which is quite brutal. But then means that when things are actually checked in, people can actually rely on the assumptions made to build things and make inferences about the project. So I have an empty bullet point. So far, no, okay. But anyway, so yeah, so as a result of basically paying the price, as I rambled at yesterday, we've bought an option to do things. So, for example, like there are questions we can ask, and things we can now do which we couldn't previously do. So, for example, with regard to the point I made earlier about things eventually becoming slow because they're just doing too much work. For example, in your CI and so on. If we have a static graph, you can ask questions of it in both directions. So, for example, you can if you have a diff, you can work out exactly which things you definitely need to run, and so on. And if you have enough information about the inputs and actually the outputs, then you can cache things. And the bullet point that's missing there is that you can send work off to a server to do it for you. So, for example, you can do the equivalent of like a parallel build with however many 1,000 jobs if you so wish. And also, since I've mentioned Buck and Bazel, there are already D rules for Bazel. So the reason why I'm effectively talking about it now, rather than saying just use Bazel, is that firstly, kind of all of the other offerings are basically priced in, whereas Bazel is. Whereas Buck is sort of new and interesting because it has a slightly different theoretical model where they've integrated a mixture of sort of innovations from other build systems and relatively new academic research to be able to it can actually deal with that like dynamic dependencies properly. For example, so you can be a lot more expressive in the input rules, and the initially caught my interest. Is that the build system itself doesn't actually know anything about any of the languages which it like supports, in quotes. So they're all defined in a standard library of the Starlark stuff that I mentioned earlier, which means that in fairness, some of it is a little bit janky, but it means it's extremely flexible and it's very easy. It's very easy to just throw everything else away and go your own way, especially if, for example, you have existing stuff you want to onboard, because one of the reasons why people don't use Bazel in particular is because it's basically a kind of like step function in terms of using it. And on a purely kind of ergonomic front, Bazel is, I think, is at least partly written in Java, which some people blame for some of the performance problems, but I don't think that's actually true. But it just means that like rolling it out to people can be somewhat difficult. Whereas with Buck2, for example, it's just it's a static binary that you just download and run, and that's it. So the way you add new things, i.e., for example, D rules and so on, is you write your rules in effectively a sort of Turing incomplete subset of Python called Starluck, which looks quite bizarre at times, but it basically it works. But it's sort of it's a fairly strange language that's evolved over time, but it's a standard, and they're sticking with it because it means there's some level of compatibility between things. So there are some odd bits of software heritage where like the project is actually like kind of bits of it like pass in between sort of Google and Facebook and so on, where they've lost interest in some parts of the ecosystem. And the key part is that we have to write basically everything that we want to do, and anything that the things we do could touch has to be declared, or either declared, or we have to read in a dep file afterwards, so the build system knows and is able to actually store stuff properly. As I said earlier, there's good and bad to that. And on the one hand, obviously, you build a much greater set of assumptions about the work you're doing. But then, obviously, you actually have to write the stuff, which is quite annoying. There are escape hatches for doing things more efficiently. So, for example, like you can quite happily build stuff without actually writing any rules, because there are basically sort of generic escape hatches. But if you want to do things like properly, you have to sit down and write them. But that reminds me of something that David Ogilvy said about advertising, which is that sometimes the benefit of a sort of marketing campaign, and sort of especially sort of like sitting down with people who actually do it for a living, potentially similar with the kind of IV stuff that was going on last year, is that the benefit can sometimes actually be introspective, in that it forces you to actually like think about what your brand means. So there's still your brand and your values and so on as a company, and what you kind of want. So even if you paid them and then never actually use the ad campaign, you still gain something. And there's something similar with this kind of thing, where being forced to think about stuff, and indeed putting an upfront cost on some kinds of complexity might actually have a benefit. Although obviously you don't want to like deliberately block people, because you have to actually do work and get paid. And the example that I've gone for to demonstrate Starluck is actually some slightly left field, in that we're actually not going to build anything. It's actually that because it's, I think everyone could basically work out how to do that. You like read the docs. Read the docs and copy some examples. So I thought I'd demonstrate something that, for example, you can't really do, or rather you can't do sort of cleanly in a less expressive build system. So for example, like, so I went for actually running a code formatting check, which some things can sort of handle. So for example, I think Dub has dublint, for example. I don't know if anyone actually uses it that much, but and like NPM has like a scripts block you can use, but it's basically a complete Wild West chaos internally. But with a more powerful build system, you can actually just encode this just the same as the test that tests the behavior of the code, because it's effectively the same thing. It doesn't really care about what's going on underneath. And this is a tool chain for such a linter, where the beginning of every anything you want to do you'll write a tool chain which fetches, effectively, so the user can actually, they have to say, for example, where a compiler comes from, whether it be the system or or the internet or whatever. And like one of the interesting things here is that if you see, we have the URL and the SHA-256. This actually runs off and downloads the tool as part of setting up the tool chain, which, for example, means that if you were onboarding someone to a project, for example, as long as they have the build system, they can have all the tools, which I think is actually quite nice. And then the provider up at the top is effectively the equivalent of a struct. Well, it is the equivalent of a struct. And then we return here. So you'd configure. You'd then add this to your there's basically a folder called tool chains in which you can configure your tool chains. And so on. So that'll run off and download this particular formatter from a GitHub release, and then just sort of set it up, and it just so there's no you don't have the classic problem of like a format check fails in CI, and then you don't actually have it locally at all. You don't have to run away and replicate a CI environment on your machine manually. And then in terms of actually running the tool, we write a rule called biome check, in which the interesting bit is that we add an attribute to the rule called a tool chain dependency, which will then implicitly add whichever active tool chain go and look for it and grab it automatically, which we can then pull the binary out, and then we return basically a test info, which just runs a command called CI, which just does a immutable check on the file, which you then configure like so. Point to the JavaScript file, whatever, and then it just becomes another test where I'm calling it directly here. But for example, you can build. There's a query language where, for example, you can ask for any you have a list of files in a diff. So then you ask for all of their reverse dependencies going up the thing, and then you run all the tests. These would just appear along with those. And then, oh great. Okay. Well, anyway, so the image didn't get included in the PDF. But anyway, if you imagine, you run test, it runs the tool. And then because I've made sure it fails and gives you an error message, et cetera, et cetera. And I think this is fairly enticing for a certain type of project. But if you'll know that if you Google for declarative build systems, one of the top results is why not saying with a question. Why aren't they popular, but telling us why they aren't popular, which is true. The incentives and the economics aren't there for a lot of projects. So, for example, most open source code usually wants to be a cog in someone else's gearbox, and these don't make a huge amount of sense in that kind of situation. And similarly, they're pretty singularly aimed at singularly aimed at monorepos, which I'm a fan of, but I'm not aware of. Sorry, not everyone else is. And for small projects in particular, they're also, they can just get in the way. Like a shell script is fine. But the reason why I'm actually bothering to talk about this and getting interested in it is that all of these points are true with this. You all kind of particularly complicated build systems a lot of the time. But I think the way they've done Buck 2 is a lot more malleable and interesting for a smaller project. So, for example, I think it would be completely feasible for like something like Dub, for example, to actually bundle Buck 2 with it, and then run it in the background, and so on. And because it's a static binary as well, it's also much easier to bootstrap as part of a relatively simple kind of open source thing. Yes. I had a closing note, but I've forgotten what I wanted to say. So I think that's. Yeah, I think I'm at the end. So there you go. Yeah, I like the questions more than the talk, so if anyone has any. VJ.
Getting there.
There's another advantage to declarative build systems that I think is worth mentioning. So in systems like Blaze or Bazel, it'll stick around as a server. It'll keep running, and it'll basically remember build artifacts. So if you have many developers working on the same project, they can share pre-built artifacts and greatly improve the build speed of incremental development. That's a big advantage why they're often really liked in companies. And then an idea to an explore, because you mentioned like these rule-based build systems like Make, and then kind of the jump to these declarative systems. One intermediate step that's a bit smaller that might be worth also thinking about is, so in Java, it's quite old, but there's a build system called Maven, and what they often do is, rather than just having bare rules or a complete declarative system, they have an API with a lifecycle, and the lifecycle can have like pre-build, post-build, whatever. And when you write plugins, you can access that API. And so you can write a plugin that says, before you build the code, run this linting tool. And then because it has a built-in concept of a repository, you can have a repository for your packages and dependencies, and there's also a plugin repository. So I can say, give me this tool that runs a linter. So there's like two common ones, Surefire and Failsafe, which run like integration test and JUnit test. There's other ones for linters. And it's kind of like a much simpler way of getting access to this kind of functionality without a full commit to something like completely shifting over to a paradigm shift like a declarative system. So it's just an idea worth exploring, that's it.
Yeah. I mean, speaking of bridging the gap, I think one thing you can do particularly easily with Buck 2 in particular is that you can declare rules that don't do anything and then capture in fact, if you have like if you had an existing sort of loosely defined set of projects which may or may not depend on each other in a sort of big monorepo, for example, you can have rules that capture effectively like the gist of effectively the sort of the political structure of the project without actually having to build things by default, and then you get a lot of the benefits of the just, for example, like with querying things based on like files, for example, you get a lot of the benefit to begin with to kind of get people on board. Having a more complicated system without having to commit and break everything inevitably. To begin with. One thing I also completely forgot to say is that I mentioned the D rules in it at the moment are a stub, and I have most of them working. But the reason why they're not in the slides here is because they are the style in the sort of standard library kind of prelude is relatively advanced, so that they'd be quite confusing. Or rather, there's basically sort of historical baggage, which you kind of like to get them merged in. You have to join in with before they undo it. Although it does move extremely quickly. So more questions?
Hello. Towards the beginning of the talk, you had a slide where you mentioned that with static build rules, you can sort of capture the environment and then do global caching, like across the entire company.
Mm-hmm.
I've seen a bunch of people mentioning that sort of thing, and we're sort of experimenting, where I'm sort of like trying it out right now at Funkwerk. And one issue I'm running into is that we have 100 megabit network mostly still. And like with the way D generates very large binaries very quickly, it isn't, at least isn't obvious that it's faster to get it from the network than to get it locally. Mm-hmm. And I'm kind of wondering, like, generally speaking, asking around, how do people resolve this? Do you all just have faster network than we do? Do you use compression? Like, what's the answer there?
And can you repeat that? Can you repeat the sort of the last, the middle third of the last question?
Yeah, the problem to me is that it's, from what I'm seeing empirically, like if you're looking at a 100 megabyte binary that's generated in 2 seconds, yep. Like how is to everyone else this is an obviously worthwhile trade-off, and to us I'm looking at this and it's like, doubt.
One of the features that the sort of big boy build systems have is that they can completely defer the build entirely. So, for example, if it's cached, first of all, there is a heuristic where it will just build it locally, but don't ask me what, but it exists. But then they will just completely defer the build steps entirely if it can. So it won't by default. For example, like fetch a bunch of stuff and then just send the job straight back off to the server. Because the idea is that the remote execution model is the default. Because one of the sort of it's. I wonder if it's entirely honest, because it sort of doesn't. But one of the taglines for Buck 2 is that it's technically a remote-only build system that just happens to build locally.
So if I understand you correctly, the gap here is that what I'm thinking of in terms of a build system is something that makes artifacts appear on my computer in a folder. And what Buck thinks of it as a build system is just something that runs tasks somewhere. Is that about correct?
Yes.
That makes sense, thanks.
Yeah.
Yeah.
Hello?
Yeah, I've been trying Buck to actually, as a proof of concept, to replace or actually trying to build faster with our code base. And did you actually try to do a prelude for D?
Pardon?
A prelude for D? Like there is an official prelude.
Yeah. Yeah, I have. Like basically a commit on my personal machine, which I've been like tinkering around with, and it's almost there. Especially if you have a project which the tricky bit with compiling any D code is always going to be like the dub dependencies. But for example, within a kind of relatively closed system, it's actually not like D is reasonably sensible. Actually, the one blocker I had actually. Was that by the server we currently host the DMD releases on doesn't respond to a HTTP head properly. So as part of the as I demonstrated that you can I wanted to download the tool chain or be able to download a tool chain.
Yeah.
For the purposes being for testing and so on, very especially. I couldn't actually get that working with. DMD, but like there's enough there to know that doesn't work. So when I get a chance, probably like next weekend, I'm going to try and actually upstream. I actually don't know how they have actually added support for external rules, which you'll fetch from a Git repo now. But I think the best way, especially kind of cynically as a marketing tool for D, is to have them in the main sort of prelude.
Yeah, I made a prelude, so if you want to share things, yeah. And one thing just to answer the other person, there is also one cool thing about Buck, that you can add heuristics to the rules. So for example, you can say that one rule is more expensive than another. So for example, some builds are deferred to the remote machine, and some that is very cheap can be done on the local machine. So yeah, that's also pretty cool.
Yep. Hello.
Yeah. I was wondering, have you considered Nix as well as a build system? I know it's a bit different, but we're using Nix actually in our repo. We also use monorepo, but we're actually able to run tests with it. You can even set up a caching server as well. And I think like that's basically made for open source in the sense that I think it's actually the biggest package repo now, like the Nix package repo. So lots of packages are actually working with it, and even Dup is now actually supported with Nix, which is quite nice.
I mean, yeah, these. I'm not particularly good at Nix, but like I generated this PDF using a Nix package. For example. Okay. So like I'm a believer. But the only thing I say is that I think Nix is a fairly crap build system. Like it's not really. They do actually in the build system that a la carte paper, they do actually also build a theoretical model of Nix, which is quite interesting. But the way I would envisage it sort of mentally is more that you have Nix to provide, for example, maybe the tools, and then a build system which you may then package as inside a flake, for example, or whatever. And one thing you can do, which is quite interesting, there's a guy called Thought Police on GitHub who has a project called like Buck2 Nix, which is like an entirely custom set of build rules where all of I think like there's something similar for Bazel as well, where when you set up a tool chain, what you're actually doing is it builds a Nix environment in the background. So as long as you have a machine with Nix, I don't know how it works with. Although that being said, I think there are some blockers with the like remote execution for that, so it's not it's not completely a free lunch, but it can be done, and there are people quite interested in it. Yeah. Is that it?
Okay, so I have a question about whether it would be useful to take the model, the semantics of a functional programming language and extend it to operate not on values in RAM, but also on values referenced via hash digests of any data fetchable from any place. In that, if you had that, you could basically treat that as a build system operating on files and files accessible on GitHub and so on, and add a layer of caching somewhere where you think it's performant.
Yes.
Have you thought about that?
I mean, not really in this context, but it sounds a bit like Urbit. If you're familiar with the Urbit project, but
what is the project?
Urbit.
Okay.
So it's a fairly strange. But I'll talk about it later.
So why aren't Buck so would it be useful for an organization like, or a company like Symmetry to use something like that? What are the benefits?
What do you mean? Do you mean what I'm talking about, or what you just mentioned?
I'm just looking from the perspective of Buck2. What are there any obvious pros about using Buck2 instead of such a functional programming language with caching?
Well, I mean, obvious things first. One of them exists, but I think, I think the underlying model of Nix might be quite similar to that, but I don't know. Like I don't have a particularly clear opinion. So yeah, you can speak later.
Yeah, just wanted to say, if you look at Nix, it's pretty much a pure language that you can declaratively define your build. It's sort of what you mentioned, but yeah, not fully. But it basically hashes everything, and it's pretty much a build system that it's functional.
All right. Well,
going once, going twice.
I think that's it.
Yep.
Though. Yeah. All right. Thank you. Talk before lunch.
think it's fine.
I'll cut.
I haven't completed 17, working on it now, 17.
Are we awake out there? Are we upstairs? No, nobody's responding. Are you awake? Am I
Yes.
awake?
No.
Oh, no, you're not awake.
Not at all.
Maybe you should be awake. You guys have got a freestyle rap in about a minute, so limber up, you know, do some exercises. You know, just like,
Ready?
you know, slap your face a bit.
I think I hit the microphone if I do that.
Anyway, so we all here now? I hope so, because this is the first of, what have you guys got, like 5 or 6 talks in the
Something
rest
like
of the
that. Oh,
conference?
at least.
At least 5 or 6. We need, can we have the screen up now, please? Yes, we need a new GC. This promises to be a lively discussion afterwards. So, Stephen, I'm going to take it away.
All right, so as the title says, we need a new GC. I'm Steve Schweikhofer, and that's Amory Shea, and we have been working on this garbage collector. The current GC it's okay. It's based on the same code that's been in D1 since the Tango days. D runtime is actually a port of Tango. And we've had several improvements since then. Precise scanning was added a little while ago, but it was only really important for 32-bit systems because you can actually have memory pinned by a random integer somewhere in a stack. So with 64-bit addressing, it's pretty much no longer important. The fork scanner basically was created by, I think it was Leandro, right?
I don't know.
But it was used by Sociomantic, and that's also now an option that you can set with a config flag. And the default scanner now is actually multi-threaded, so you have it'll fork a bunch of, or create a bunch of threads to scan your memory while the world is stopped, and that uses the CPU a little bit more efficiently. But those are basically the big improvements that we've had. It's not optimized for the architectures we have today, so there's still, anytime you look up where a piece of memory you got to mark, it does a binary search for that piece of memory. There's too many touches of various pages, so anyone who's familiar with CPU architecture, Amory's going to talk about that, is going to know that anytime you touch a piece of memory that's outside your cache, you're going to flush the cache and have some problems there. And yeah, it doesn't take enough advantage of modern hardware, and the TLB is something that we're going to discuss later, but does not try to reduce that pressure. All the allocations are done from a global structure, which means we need a global lock. And the global lock means that if you have multi-threads all allocating all at once, you essentially have a single-threaded application, which kind of stinks. You can't do any allocations while collecting. That's basically the problem is because of the global lock. You would have a deadlock if you did that. All threads must be stopped during scanning except for with the forking allocator. So if anyone's not familiar with the forking allocator, it forks a copier process. All the pages become copy on write in the second process. And then it just resumes your original process, does all the scanning in the fork process. Anytime a page is written to in the fork process, it has to basically stop both processes, adjust the page table, and then continue on. So you have these write barriers that they're a little bit expensive, but at least you can continue running your application. And then once the scanner's done, it transmits all the dead blocks back to the original, and it can clean those up. Even doesn't have to stop the world for that even, I don't think, because it's all garbage anyways. The implementation is very tied to D runtime, so all type data is fetched from type info. You know, we've had the talk about converting D runtime hooks to templates, and that's a huge benefit because we don't have to rely on type info. You know, we can build functions that do specifically exactly what we need, but the garbage collector requires you to pass in type info for finalization and other things.
Okay, if I may interject quickly on that one so that you realize how bad it is. When you allocate memory on the fast pass, that is taken like 99% of the time, half the time you spend is not allocating at all. It's just like fetching data from type info and other stuff like that and combining them in the right way to figure out what type of allocation you want to do. It's half the time. It's crazy. Like a template could get all of that at compile time and we win. Like we have a 2x on allocation performance right there.
Yep, and also the array runtime is dependent on implementation details of the GC, which I'm working on getting rid of. So who here has done like, oh, this GC allocation is bad, so I'm going to use malloc and free and save some time? Yeah, pretty much everyone. Most people use the C allocator as a faster allocator, but it's just an allocator, right? We should be just as fast. And if you use the C allocator and you store pointers to GC memory in there, you have to pin that memory. Otherwise, it might accidentally get collected at some garbage collection cycle. We should be just as fast. And here's a few examples of things in Phobos that use C malloc and pins the memory in the GC. So the fact that, and remember, pinning memory in the GC also has to take the global lock. So it shouldn't be faster. It shouldn't be faster to allocate with one allocator and then call into another allocator to pin it, but somehow it is. So that's kind of the de facto solution that people have reached for. But we should get rid of this so that instead of, if you want to do manual memory management, sure, just use the GC that's performant and malloc and free, and you should be fine. But because that is slow in the current GC, people don't do it. We're hoping to fix that. The GC that we're working on is only for 64-bit architectures because we take advantage of all the features that 64-bit addressing has. The current architectures that we support all use maximum 48 bits for addressing, which gives you a maximum RAM size of 256 terabytes, plenty of space. Using memory mapping, we can plan out how things are laid out so that we take advantage of these architecture features. And we can use sparse data structure, so use a lot of address space, but most of it is zeros, and we're going to talk about how that works. All right, so Omri, you going to take over?
Yep.
All right.
All right, so we're gonna, like, before we dig into the GC itself, we're gonna talk a bit of, about all the OS and the CPU managed memory, because a lot of design decision, depend on that, and if we don't explain that, then nothing makes sense. All right, so actually on a modern, and by modern I mean like at least, it's been true for more than 20 years, right? Like any kind of CPU that you used a variation of that scheme where a pointer is not like an actual address in memory, right? It's a virtual address, and it's somewhere, it's kind of like a struct with a few fields, and then there is a data structure in memory that the OS maintains, that the CPU understands, that tells the CPU how to translate those addresses into physical address into your RAM, right? And the way it works, at least, so this one is like for x86, 64 bits, but every single kind of CPU out there is going to use a variation of that scheme. So the way it works is that, so first, the first 16 bits are going to be always 0, except if you do kernel development, they can be 1s, but we are not doing a kernel GC, right? So in our case, it's always 0s. And then you have a series of 9-bit buckets, and each of them are like an index into some kind of data structure to resolve what the actual physical address in the physical RAM is. And then the lower 12 bits are just like within a page, where are you, right? So the lower 12 bits are actually always the same between physical and virtual addresses. And so the data structure that the CPU uses to do that resolution is effectively like a tree. And each level in the tree is like one page of 512 pointer-like kind of thing. And those are either going to point to the next level in the tree, or they are going to point to a physical address, right? And there are a few bits in there to indicate, well, is it a page or is it the next level in the tree? Is it readable? Is it writable? Is it executable? This kind of information. And so you end up with that structure where if you use 4 levels in the tree, you end up with the 4 kilobyte pages that I think most people here are going to be familiar with. This is the default that most system uses. But what you may not know is that those systems also support bigger pages that are going to be, 3 level or 2 level in the tree. Like if you have the right flag that say, oh, this is a page now, then you're going to have a 2 megabyte page, 1 gig, or 512. I've never seen anyone use that, but in theory, if you have enough RAM, at least it's theoretically possible. So you're going to realize, for instance, if you branch out at level 2 and have a 2 megabyte page, well, the 9 bits level 3 here, they are just part of the, they join the 12-bit here, and they are part of the address within the page. So now you have a 2 meg block that is 2 megabyte aligned, and all of that is within the page. So why this is important is because this whole process of resolving addresses, you can imagine, is pretty expensive, right? If you had to do it every time you do a memory operation, a store and a load or whatever, you had to walk down the tree, which involved itself, 4 loads pretty much. Each one of those loads can also be a cache miss, right? So potentially that's pretty expensive. And your MMU is doing that to resolve address. So there is a cache that is similar to the L1 cache you have for instruction or data in your CPU that is called the TLB that store the result of that process, right? So if you access the same page several times, well, the first time it's going to have to do that resolution, and subsequent time it's going to fetch the result in the TLB, and it's going to give you the right physical address right away. So you don't need to do it many, many times. But just like your L1 and your L2 and stuff like that, the TLB has typically different level, but the one that is fastest and very close to the CPU is very small. And so as program got bigger and used more and more memory, it actually becomes a problem to work with only 4K pages because, in a modern application that's going to use several gigabytes of memory, the number of 4K pages that we represent is way, 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 way bigger than any space that you have in the TLB, right? And even the hot set of data that you access a lot, it tends to not fit in the TLB anymore. So you want to be able to leverage at least those 2 megabyte page, as much as you can. And it's very important in the modern age. For 32-bit system that were pretty small, it doesn't really matter, but know that we have, big application with a lot of memory, justified or not, we can discuss that, but this is, how things are now. So we want to be able to leverage those 2 megabyte pages as much as possible. And to do that, the OS is actually going to help you because all modern OSs, maybe if you use embedded stuff and they may not support it, but Windows, Mac OS, Linux, the big usual suspect are all going to support the feature that's called transparent huge pages. And what it says is once you request memory from the system, it's going to give you some, and it's going to be split into 4 kilobyte pages. And as you use it, the OS, may notice, hey, here we have a consecutive 2 megabyte block of 4K pages that is all used by the application. It's 2 mega line. I can swap that out from behind the back of the application into a huge page. And previously, you would need 512 entries in your TLB to represent that whole thing, and know that the OS shifted it to use a huge page. It's just one entry, right? So when the OS can do that, it's effectively a multiplication by 500 of the size of your TLB for the specific chunk of memory. Obviously, you cannot do it for everything in memory, so in practice, it's not a 500x, but when it can do it, it's literally a 500x improvement, so that's a pretty big deal. And modern OSs, they do that behind your back once in a while, and you can also hint them For instance, on Linux, it's going to be with the madvice function or memory advice. I'm not sure how we say it, but that function can hint the OS like, hey, you might want to look at this and turn that into a huge page. But even if you don't hint the system, it's going to try to do it behind your back. All right, another concept that we need to explain, because we leveraged it quite a bit in various places, is the concept of like virtual 0 and O that that is memory mapped by the OS for you. So when you request memory from the OS, you actually don't get any memory. You get address space. And as long as you don't write to it, there is pretty much no memory there. You can read zeros from it. It appears to be like actual memory that you can read from, but it's not. And the way it works is that it gives you effectively like a degenerate page table where it all points to the same zero field page that is write protected, right? So if you read like any address in there, you're gonna resolve all the level, but like whatever you are in the first level, you point at the same place in the second level, and whatever you are in the second level, you point at the same entry for the third level, and so on, right? And at the end, you point to the same write-protected zero page. This is very useful for us in many ways that we're going to describe in the implementation. But generally, because we are the allocator, we cannot rely on an allocator to allocate for us, right? Like that's, fairly obvious, right? So sometimes we're going to be like, oh, we don't know many of those things we need, right? Maybe we need like 1, 2, 1,000, we don't know, right? So what we do in those instances, it's like, well, reserve the address space for the maximum number that we think we can need. And as we use those zero pages are going to be materialized on, as per needed basis. And we don't use that much actual memory, even though we use a fair amount of address space. So this is a bit of a diagram that demonstrates like what happened when you write somewhere in there, right? That zero page is zero protected because the OS is pretending for you that there is an actual huge chunk of memory there, even though there is just one page full of zero. So when you write in it, the OS traps your write, right? Because the page is write protected, so you get some kind of fault, and the OS can catch that and do the right thing. And what does the OS do? Well, it creates a new path, here represented in green with the red arrows. And your new page, it's gonna like locate a new page for you where you can write in, and everything else still points to the magical zero page, right? And as you start writing into more and more pages, more and more of those green paths are being created in the page table by your operating system to do as if you had a bunch of memory there all along, but you did not. And this is why if you look, with tools like HTOP or whatever, if you look at the statistics of your program, you're going to see like how much memory does it use, quote unquote, and it's not really memory. You want to look at how much resident memory does it use, and it's not going to be the same value. The resident memory is going to be smaller, and the resident memory is actually like how much green stuff you have here, like how much like real memory there is with real RAM behind it. Whereas the total memory, it's going to be actually the address space, and a lot of it is going to be, or a lot of it, or a little of it, depending on the application, but some of it is going to be just like virtual zeros. So we rely on that mechanism quite a bit because effectively, like, we can use the operating system as an allocator for us when we need it that way.
Yep.
You want to go?
All right. Next one. All right. So now that you've all consumed that, if you have any questions, raise your hand at any time. But now we're just going to go into the first part of how the GC works. So we're just going to discuss large allocations this time. One of the cool things that we have in our GC is we wanted to create our own mutex to avoid initialization of our allocation. Like Amaury said, we have all zero data, so as long as you have something that's initialized with zeros, it's free until you use it, right? So we don't want to have to allocate memory for our mutexes. We don't want to have to initialize it with anything with zeros. So we have these mutexes, and we don't have to actually initialize them in anything. So we may declare large amounts of metadata structures. As long as they're all zeros, it doesn't actually materialize, so it doesn't cost anything. We're not contended, so atomic operations are enough to take the mutex. So if you don't have multiple threads going after it, it doesn't matter. You know, it's really fast. And even under contention, then we just swap out to using a kernel API. The region allocator is the main piece that gets data from the OS. So the region allocator gets allocations 1 gigabyte at a time. Remember those 1 gigabyte pages? But of course, they're all zeros. So at the beginning, you just ask for 1 gigabyte, and it just gives you 1 gigabyte of memory, but you still only have, you know, just a page table in your process. We track ranges of memory that are not used in a red-black tree, and we have 2 separate regions, one for pointer-containing blocks and one for non-pointer blocks. And this is important because we only want to scan the pointer-containing blocks. So if we section those off in its own address space, we can both easily determine if it's pointer-containing, and we also keep that scanning algorithm so it's focused on the same part of memory. And once the region allocator gets its 1 gigabyte of space, and it can ask for more if it runs out, it's going to hand out those chunks in those 2 megabyte pages. So it's important that we use the right sizes that the operating system likes.
It's more like the CPU.
The CPU,
likes, yeah.
the CPU likes, right. The things that the region allocator hands out are 2 megabyte pages. So there's a thing called a page filler. I guess this is a standard term. It confused me when I first read it, but
this is the term from TC malloc, so we just went along with it.
So the page filler gets its address space from the region allocator saying, give me a block, I need n blocks, whatever. And of course we have 2 region allocators, so pointer containing blocks are separate from pointer free blocks. And they're tracked in heaps ordered by the longest free range and the number of allocations. So we have all these heaps, you'll see the diagram later, but we have some small allocation heaps, which we'll talk about in tomorrow's talk, and large allocation heaps, and basically each heap is sectioned off by allocation classes, which are basically how much of if we wanted an allocation of like 15 pages, there's a certain heap for that, either that or bigger. So the longest free run of memory we can pull data out of, we put it in a heap. And we store, I guess it's 31 heaps, right? Not 32. So
this is 31, yes.
Yeah, so that's a typo. But anyways, but since it's under 32, we can have a bitmask that basically gives us a constant detection of which heap we should pull from. So with one operation, we can determine exactly where to get the next piece of memory from or allocate a new block. So as a result, heap operations take amortized constant time. And we'll see how the heaps work in a minute here. A little note on metadata tracking. So in addition to the memory you're requesting for your application, the allocator also needs some tracking data, just kind of like the OS needs a page table, we need to track this data. And so we have some allocations that basically never get freed, but they're just metadata, and then when you stop using them, it just goes on a list of unused ones so that you use it later. The main thing here is the block descriptor, which keeps track of just various information about the block, how many pages in the block and which pages are allocated. Remembers the longest free page run, which is used for sorting the heap. Allocation class, which is it's kind of like a range of free page lengths, which we have a list of those later. And how many allocations are in the block, so that's just for like bookkeeping and stuff like that. And then a generation, so as you ask for more data from the region allocator, it stores which generation. So like you ask for 1 gig, oh, you ran out of that, you need another gig. So that's generation 2. And it tries to keep those blocks together, or those block descriptors together, so that, again, we're trying to keep things as close as possible so that you're not touching multiple pages of memory that then it's going to flush the cache. And so unused metadata, like I said, goes into a heap to be organized by the generation, so you can use it later. All right. So the pairing heap data structure. This is a cool thing that we took from GmalloC.
GmalloC, yeah, but GmalloC also took it from elsewhere. It's
so
very old arcane technique that were a bit lost at the time and rediscovered in recent years.
So if anyone's familiar with a heap, basically a heap is a tree, kind of a tree structure that has the most important value is at the top. So you're always looking at that one to be the next one that you want. And then once you remove that, it does some amount of operations to put the next best one at the top. When inserting a child, we have this algorithm with, is it better than the root node? If it is, then it becomes the new root, and it's just like a linked list. It goes to the next one. If it's worse than a root, it goes into kind of an auxiliary heap off to the side. And whenever a child is added to the auxiliary heap, if the count is even, then we perform n merges where n is the number of trailing zeros. And in practice, that amortizes to 1 merge for insertion. So if you have like, okay, 2 insertions, I do 1 merge. Then I have 4 insertions, I'm going to do like 2 merges. So
and you do 8 and you do 3.
Right. So eventually it ends up being like close to 1, I think, like 1 to 1, right?
It's going to be 2, right? You have to insert your node, and then you have to merge 2, and half the time you do 1, a quarter of the time you do 2, 1/8. So it's like half plus a quarter plus 1/8, and so on. It tends toward.
It approaches 1.
It tends toward 1. So total is 2. So you do on average 2 merge operation per insertion. So it's amortized constant time, which is pretty cool.
So when we remove the root, then it performs a merge on the root's children, which is generally like 1 to 2 children, and it performs a merge of the new root with the auxiliary list root. I get that right? I mean, it's written there. So he knows a lot more about this than I do. But we're going to show a demo of this. So I wrote a little application to kind of show what it looks like. Let's see. So first I'm going to put things in inverse order. So can everyone see that? It's kind of small. But you have a node at the top. That's the root node. It's got a value of 127, so lower numbers are better. So I'm just going to add nodes, and as I add nodes, it just becomes a linked list because the new node is always better than the root node. And then if I pop them off, they just come off in that order too. So you can see the comparisons done and the operations. So the comparisons are way less, so it's actually better than standard. Now if I reset this and put like random values in, and you'll start to see this is the auxiliary heap to the side growing off, and we just keep. It kind of looks like a binary tree, but it's like off to the side. But you can see the comparisons are like about twice as much, and as we pop off, they become a lot more. But it's still amortized constant time essentially. Now, if I do this in
you might want to do this in reverse. This way. So that we show the auxiliary list, how it builds up.
Yeah, so if we do this this is like the worst case. Every single time the new one is not better than the root. It just keeps filling up the heap here, and as we pop them off, it actually is pretty fast. So this is just like a little demonstration of what it looks like if you can visualize. I think it's a lot easier to understand. All right, and I think Amarie's going to take over the next part.
All right, so we talked about allocation classes a bit before, and don't worry, like we're introducing many concepts. We bring them back together in a bit of a diagram, as we explained, but we need to explain a bit the fundamental components before we put them together. So to try to allocate, large allocation, it's going to be on a, page granularity, right? So it's going to be on 4K granularity, effectively. And we're going to have blocks. We allocate those large allocation from blocks. And we are going to, sort, essentially, those blocks into different buckets. Each bucket is going to be a heap, like he demonstrated, based on, what is the longest free run of pages in that block, right? So that we can know, hey, if I want to allocate, I don't know, like an allocation for 12 pages, I need to go into one of the heap that has blocks with 12 pages free or more. To do that, we don't want to, because there is 512 pages in a block, we don't really want to have 512 buckets. There are two reasons for that, but the first one is just because that's a lot, and that would just take a lot of resources for no good reason. Like most of them would be empty, and the vast majority of them would have one element in them. So we essentially use different sizes with 2 bits of precision. 2 bits of precision, effectively. So for the smaller one, it's going to be the exact number of pages. But as it grows, after 8, it's going to be like 10, 12. We go 2 by 2, and then we go 4 by 4. For 16 to 20, 24, 28, 32, it's like 4 by 4. And then 8 by 8, and so on, up to 512, which obviously we never reach, because if the block has 512 pages free, then the block is empty, and we return it to the region allocator. So I don't know, if you've programmed for quite some time, you've seen all those numbers. They're a bit usual suspect in programming. Those are, kind of recurring number that you're gonna stumble on, all the time. And those are what we use as our allocation class. So say you want to allocate a large allocation that's gonna take, say, 21 pages. Well, you need to allocate from the heap with 24 pages or more of free run, because the other one are going to be too small for you. And you're going to have to select a block in there, and you can do your allocation from that block. So now the question is do we actually want to do best fit? Because it's a bit wasteful, right? If it's 21 and we do at best 24, maybe there is a block somewhere that has 22 pages free. It's going to be in the 20, bucket. And we're never going to use it to allocate our 21 pages allocation. So the question is that a problem? Is that wasteful? And to some extent it is, but there are 2 good reasons to do that. The first one is obviously we can do the lookup much faster in this way, and that matters as well. But more importantly, what people realized over the years when building memory allocator is that best fit is actually not the best. Right? So intuitively, when people started building allocator, they were like, okay, let's sign, if I'm looking for 21 and there is a 21 range somewhere, I want to use that. And if not that, then a 22, right? And I want to be as close as possible. The problem with that approach is that you end up with a lot of very small runs of pages, like 1 or 2 pages, and you don't have enough demand from the system, in other places to fill all those very small runs. So having some amount of slack is actually beneficial. Too much is also going to be, not good. But you want mostly best fit, but not quite. That's what is actually best in practice. So, yeah. So, that's 31 allocation classes in total, and it's pretty much how it works. So then we have page filler. Steven talked about it a bit, but we're gonna dig in there a bit more. So there are 496 of them, potentially, right? Because they're all virtual zeros. So when we start using one, it's going to materialize, but all the other ones are just, static address space that we take, but there is nothing there. Why? Because we cannot dynamically allocate them, because they're the one doing the allocation, right? So when we need the page filler, for instance, to do a large allocation in our case, we're going to select one. How do we select one? We use the ID of the core you're running on to do that, right? So if you have 4 core machines, it's going to end up using like 4 different page filler, and depending on which core your thread is running, it's going to pick the corresponding page filler. Why do we do that? Well, that's a way to ensure that there is very little contention, because the only situation when there are going to be contention is when the OS, like suspend a thread that is mid-allocation and resume another thread on the same CPU core, and that other thread is going to also do an allocation, right? And that requires a timing that is quite specific. That is still possible, and this is why we use mutexes in there, but it's like very uncommon in practice, so we get very low contention out of that mechanism. And as we mentioned, the page filler maintains a set of heaps for each allocation class to be able to select the best block that correspond. So this is a bit of a simplified diagram of how it works, but here you have the page filler. You have 31 heaps that corresponds to each allocation class that you may need, and you have a bit field that contains 0 if there is no blocks in that heap, and 1 if there is some block in there, right? So now imagine you want to do an allocation, and based on the sizes allocation, it's allocation class 5 or more that you need. Well, you're going to build a mask that have the first 5 bits are 0, and then all the following bits are going to be 1. You mask with that. You count the number of trailing 0, which is 1 instruction on modern CPUs, and boom, you know the index of the heap you need to get from, right? So it's like a couple of instructions, quite literally, to know which heap you need to pop from. And then you pop from the heap, and we've seen that this is amortized constant time. So we can select the right block to allocate from, basically in amortized constant time. Yeah.
Yeah, and then?
Well, then we maintain the list of all the blocks, because when we do like garbage collection process, sometimes we need to go like over all the blocks that we've allocated in there and do some maintenance work. We're gonna dig in that a bit, but it's more for tomorrow. Yeah. Do you want to do next, or should I go on?
Oh, you can go.
Okay.
The rest.
So yeah, so now that we have all of that, we have all the pieces that we need to allocate and free. Well, not quite free. There are a few pieces to free, but we have all the pieces we need to allocate a large allocation. So the process is essentially, so what is a large allocation is like more than 14 kilobytes, right? Because at this point we get into page granularity is okay. Smaller than that, you need to be, you need to maybe like fit several allocation on some pages because you start wasting a lot of space. But after 14K, we consider we are fine. So basically what I explained, based on the size of the thing, we compute the allocation. We compute the allocation class. Based on that, we select the heap and we pop from the heap the block that we want there. Once we've selected the right block, we select like a number of pages in the block. And we create what we call an extent that describes, hey, there is an allocation there. It's that many pages long. If it has a destructor or stuff like that, we also put that in the extent. Basically, the extent is like a structure that describes, hey, like here is your large allocation. And here is all the property that this allocation have. The extent is 128 bytes in size. It's going to come important later because we can 128 byte align them. But that's pretty much it. Very simple data structure. Gets more complicated for small allocation, but that's going to be for tomorrow. Just like block descriptor, those are allocated but never freed because they are managing allocation, so that's difficult. So when if you free a large allocation, they are returned into a heap of unused extent, and next time you need an extent, it's going to pop from there instead of allocating new ones. So in practice, it's not a big deal. Okay, for huge allocation, because we've seen we allocate from blocks, but blocks are 2 megs, right? So what if we want to allocate 4 meg, large allocation, right? Like what do we do? And when it doesn't fit on blocks anymore, we call them huge allocation because huge is bigger than large. So, and like basically what we do is that we request from in that case, we don't use a block because we cannot. We request from the region allocator a set of contiguous block where we can put that thing in. And if it's not a multiple of 2 megabytes, for instance, you ask for 3 megabytes, well, there is still 1 megabyte free at the end of the last block. So that last block, we're gonna give it to the page filler to, to put something after your huge allocation. We tend to deprioritize those blocks. So in each heap, we have, a priority system between blocks to know which one are the best to take from and which one are not the best. And one of the parameters that we use is how many allocations are there in that block. Not how many pages are allocated, but how many allocations. Why do we want that information? Well, because if there is, if you did like a 3 megabyte allocation, half the block is full, but with just one allocation. So there may be like just one free somewhere that frees up the whole block, right? Whether if you have half the block that is taken, but with like allocation that are 1 page in size, you have hundreds of them, and the probability that those hundreds of them all go free at the same time is pretty low. So if you have 100 of them, de facto your block is immortal now, right? But if you have like 1 or 2 of them, there are good chances that the block is gonna go away, right? So you want to target the block that are statistically likely to be immortal rather than the one that you're gonna be able to be free later on, right? You want to go for the free?
Sure.
Yeah.
Sure. Do this one. All right. So when we want to find what block or page or information about an address, we maintain a 2-level radix tree for reverse lookup. So you get a pointer. You want to know the metadata about that pointer. We have this 2-level tree. Level 1 is a 2 megabyte buffer of static data that's initialized with zeros like everything else. And each pointer size thing in that is pointing to the next radix tree bucket. So that first level never goes away. So we require it at the beginning of the application. We need this 2 megabytes. Of course, it's still zeroed address space. And in practice, that doesn't get filled up very much anyways, because each level 2 is made up of another 2 megabyte buffer, and that covers a gigabyte of actual address space. So unless you allocate, you use 1 pointer in the first level for 1 gigabyte of address space. So you're not gonna do probably more than 3 or 4 of those most of the time. So it's actually pretty efficient. And then the whole data structure is lock-free and can be accessed by multiple threads at once. So we have low contention on that. And this is kind of an example or kind of a model of how it looks. So if you have your pointer, you have 16 bits of use because we only use 48 bits in the pointer. The lower 12 bits are also unused because those are per page.
The address within the page, yeah.
Yes, address within the page. So we have 2 18-bit things. Each one is 2 megabytes. So you have 2 megabyte pointers to table 2, and then various table 2 descriptors that would be composed of these page descriptors, which we'll get in the next thing. But each one of those tables in the level 2 covers 1 gigabyte of memory. And this is what a page descriptor looks like. We get 4 bits indexed into the extent, which is important for small allocations. We'll see that tomorrow. Arena index, which is which of those page fillers are you using? The extent metadata address. So this is the pointer to the little extent thing that's 128 bytes. So this is why we have 128 bytes aligned. The lower 6 bits is what kind of extent it is. If it's a large extent, the extent class is 0. If it's something else, then it's a small extent, and that's, again, for tomorrow. And then we get 1 free bit. So we have room to grow this data structure at least once. All right, so when you want to free a large allocation, use the radix tree to find the extent, the block, and the page filler. So you get all that information just from that tree, so it's basically 2 lookups in memory. And we clear the page description from the radix tree, so we remove that element, and we remove the block from its heap, and then we free the pages, and then we reinsert it into the appropriate heap. So you've freed this piece of memory, it might change the class, the allocation class it goes into, so it could go in a different heap. It could get completely freed. You know, all that stuff happens at that point. That's freeing a large allocation, and I guess we've got to the end then. Tomorrow we will be talking about smaller allocations, because most people are not allocating page size things. You're allocating a few bytes here and there, so.
Yeah, smaller and collection.
Yeah, and collection, yeah, that's important too.
All right, first question down here.
So you talked about huge pages, and one of the problems that we have with the optional flag for using fork, we can't actually do it because huge pages doesn't copy on write on Linux, so we can't do that. And also parallel GC, I think we disable it for some specific reason. I don't really know. So GC is particularly bad for us in that regard because we don't have this advantage. And a few other things that I have some ideas also for the GC, so I can share with you. For example, one of the things that I've seen from the first like our current implementation is the page size is locked to 4K. And for example, for AARch64, the kernel can be configured to use 64K pages. So the page pool of the GC is actually not using a lot of space. So maybe we are losing a lot of memory because of that. So if someone can actually take a look at it, because I tried to look at it, but it's very not documented. So if someone wants to touch there and not break anything on the GC, would be cool.
So I won't be able to answer the question, but on the large page, 2 megabyte pages, the reason why it performed very poorly with the fork is because every time you write into some piece of memory, it's going to do copy and write. And obviously, if you have 2 meg pages, then the OS have 2 choices, and the 2 of them are bad, right? So one is you copy the whole 2 megabyte page, right? And you duplicate that, which is going to create like a lot of mem copy going around and a lot of memory consumption. The second one is like you split back that page into like 4K, and you clone the one that is 4K, but that require modifying the page table, which is also expensive, right? So when you do that with the fork technique, you're a bit in a catch-22. We have a strategy for concurrent collection that we want to implement, like in the next version of that thing, because we cannot do everything in V1, but we have a good idea of how we want to do it, and it's a bit different than the fork, for that reason, amongst others. Also, the other remark was based on the fact that, ARM, 64-bit ARMs use different page size, and it's actually a bit of a mess because it can use like 4K, 16K, or 64K pages, right? And it's going to depend on in what mode the operating system configure the CPU. So it's a bit complicated. We are not the only ones having problem with that. I've talked with various people working on other memory allocator as part of that process, and it's always a bit complicated. But what most of them do is that they keep using 4K pages as granularity anyway, even though the system is going to fill 16K every time. But for the block size, they may use 32 megs, for instance, if the system is configured as 16K pages. And I don't know if it's 64K pages. I don't know what the next level pages size is, but it's probably something like absurdly big. So I'm not sure it's worth doing that, but 32 meg block could be an option on those systems. We're gonna have to try.
I think it's half a gig. Is the next size.
It's half a gig, yeah. Well, the problem, like if it's get to half a gig, it's gonna be very difficult to fill consistently, right? Like you're not gonna get half a gig of different allocation with no holes in it consistently. It's gonna be very, very difficult for the allocator to create that situation.
Hi, I noticed that on one of the slides you track where the pages are dirty. Does it mean that you have write barriers?
Can you repeat? I didn't hear very clearly.
There's a dirty. Which one was that?
It was earlier in the presentation. One of the points was that you were tracking if pages were dirty. I think that's something you want to do if you have write barriers, and I wanted to ask if that was something you're doing.
What was it?
Oh, I see what you mean. I'm not sure what slide you're referring to, but I understand the question. There is a very sad story there. It's a very tragic story because in the page table, there is a dirty bit, and the CPU fills it for free, right? The problem is this is accessible to the OS, and the API that exists on different OS to check that information, first, they are non-standard. They're going to be different for every single one, and they are all complete and utter garbage, right? So, so what many people end up doing is like re-implementing a red barrier on top of it, even though the CPU gives it for free. That I don't have, if I had a lot of power in this industry, I would badger operating system implementation so that they give us a good API, but I'm afraid, I'm not that powerful yet. So we're gonna see.
I think you'd have to get the CPU vendors aligned too. Wait.
What? Louder.
Missed that.
You'd have to have different, because each architecture has a slightly different way of doing that, right? So you'd have to get all the other CPU architecture folks all in the same room and doing the same thing.
Have you tried using page faults to track writes as write barriers?
This is the plan if the fetching the dirty bit with the Cree API doesn't work or we don't have it for that implementation. The problem is like it's way more expensive to do it that way, but you can disable it, right? So it's a like one-time cost, and also we can limit it to only the memory region that contain pointer. You don't really care about writes, of memory that don't contain pointer. So this is one of the reasons we segregate the memory. Like what I'm talking about is not implemented, but the reason we've implemented things in a certain way is so that we can implement that in the next version. So yeah. Doing memory protection on the memory that contains pointer and tracking the write there is definitively in the cards.
Awesome, thank you.
Oh, okay, my turn. So I actually had a couple questions. I wanted to ask questions about the architecture differences, but I think you guys, it sounds like you guys are just using mapping 4K pages as if just slicing up a huge page or a 64K page on AR64. You guys are just going to slice that into 4K pages?
Yeah.
Okay. The other two questions were on the best fit versus first fit or other kind of approach. One approach I've seen is when pages become scarce, and I don't know if we actually know that pages are scarce. I don't know if we're actually interfacing with the operating systems enough to know, like, oh, I might not actually, memory might be low. But if you know, then you could shift your approach. So you willing to pay more to try harder to get a page in the face of scarce resources. And I don't know if that's something you guys have considered or not, or if it's even applicable. Do you even know if memory is scarce?
Well, it's probably possible, right? Because you have application that gives you here is how much memory there is in the system, here is how much memory your program using. So like you can know, but the API are going to be non-standard across systems. Now, there is a second drawback to what you're mentioning. So obviously, it's going to be a bit more expensive to do best fit, but the problem with best fit is that it creates long-term fragmentation because you have like those, unless you have the exact size, right? You're gonna have like a little extra, And you end up creating, too many of those little extra, and there is not enough demand for slices that small to fill them. So you create like long-term fragmentation in your heap when you do that.
So that's a nice segue into my next question, which was an approach I've seen used in other systems I've used. I assume you're familiar with the slab allocator, and one of the big advantages of the slab allocator, aside from being very, very efficient, is that because you have uniform sizes, and if you have fixed size objects, and I don't know in D how frequently applications are. I know in the applications I work with, we have a lot of objects that are pretty much the same size, and so the slab allocator is a really nice solution for when you have that kind of a profile.
Yeah, so we're gonna cover small allocation tomorrow, but we use a variation of that idea for small allocation because it works great. Though we needed to cover large allocation first because what do you do to get a slab and to get like many units in it? Well, you do what we described today, right? you get like a few pages and you make a slab out of them, and then you allocate from that. So we kind of needed to, even though that's slab is more common, like in practice you allocate small stuff way more often than you allocate large one, but we needed to explain that one first.
I was actually I forgot my question, but one thing that I wanted to answer for Garrett is we on the current GC from the code that I read, we basically check the memory usage and call the gc.minimize, which will basically defragment the pool of pages that we have. I don't know if this is just for large allocations, but also for small allocations, but I'm not really sure. But yeah, we definitely do that.
So I think.
Go ahead.
In the current GC, I don't think that it provides. So it doesn't give back memory to the OS, I think, until you call minimize, right? So like it'll just keep free things in a list.
It does, but yeah, not that much. Yeah.
So that's like the way it does with our allocator. As soon as we see that a block is completely free, we'll give it back to the OS. And so I don't think we need to support that piece, right?
Yeah, so we release blocks on a 2 megabyte granularity. We also, when you do a garbage collection cycle, but it's for tomorrow, it may be missing some pieces, but when we do a garbage collection cycle, at the end we need to scan all the block to see all the dead stuff that are in there and free them. And as part of that process, if there is more than, I think it's 64K in the block of memory that is, like actual memory that we've used but that we don't use anymore. If we are more than 64K, we purge all the news page in the block. Now we want to have some slack there because purging that memory is expensive in itself. And so if you very aggressively purge everything that you don't use, you end up like purging the memory and then requesting it back from the OS when you start writing in it and so on and so forth. So we added a 64K slack in there, or 16 pages. So we allow basically 16 pages dirty, unused in the block. And if there are more than that, we purge everything.
DJ?
Wasn't it my turn? Oh, thank you. So towards the beginning of your presentation, you said that you're trying to remove the need for type info when you are running your sweeps. And my question is how? Because what happens is that the D runtime will sometimes need to put those type infos in there. For example, when it creates new structures or classes, in order for the mark phase to be able to correctly mark indirections. For example, if an object has references to other objects, then those should also be marked as live. So then how do you want to get rid of that? I would love to not have to write that thing in the runtime, but I don't see how.
So in my fork of D runtime, I actually have removed the requirement to have type info because we need it for our garbage collector.
Okay.
It turns out there's two things we need from type info. We need the for the precise scanner, we need the bitmap that comes from the compiler. It says these are the words that have pointers in them, and that's just basically a compile time constant byte array. So we don't need that piece. We don't, we have this thing called RT info that takes every type and puts it into the type info. But the only reason it does that is so that it can then later use it in the garbage collector. We can just pass that block into the garbage collector. So that's one thing. The second thing is the finalizer. So if there's any finalization that you need to do, we pull that from the type info. You obviously still need the type info for classes, but we know that's in the block already. We don't store it separately. So I'm still playing with the API a little bit, and I'm eventually going to submit a pull request to fix all that. But right now, I have it working without type info. Okay. And I think it's good not to have type info as a requirement because of the cost of calling the virtual functions in the class, and you're going around touching quite a few things that might not be cache local. So it becomes very expensive.
Yeah, the TLDR is everything you get from the type info, you could have known at compile time. And so you could have directly called the GC, like, okay, give me an allocation. It's this size. It contains a destructor or not. Here is what the destructor is if it's contained one, and it contains pointer or not, right? Like all of that you can provide at compile time and generate direct call to the GC with the right information.
We're already using with the new template runtime hooks, we're already using the compiler to tell, does it have pointers or not have pointers? Does it, those bits that get sent in already are being done outside the type info. So we're not really using the type info as much. It's just for those two things.
So then the GC has to be compiled together with the code, right? Because you can't just use it in a precompiled fashion. Otherwise, it wouldn't have the compiling information, correct?
The GC doesn't. The GC just will accept. Oh, you have a list of you have a bit. You have this pointer bit field. It accepts that as a parameter, and you have a finalizer function accepts that as a parameter. So that's it. You don't need the runtime extracts the stuff from the type info instead of the GC itself. Does that make sense?
Yeah, I get it now. Thank you.
Yeah, as evidence of my poor social life, I find this stuff exciting. It's enjoyable. I appreciate the effort to get us to the front edge of allocators, with our particular constraints. Two questions. One was if GC, if I understood things correctly, GC malloc should become kind of like best practices for general allocation, that you just call that instead. Is there any downside to just migrating to GC malloc from malloc as a common practice in greenfield code? And the second question was with regards to your development environment. I think that you've surfaced a few portability concerns, and I was wondering what you're actually using. I think, Steve, are you on a Mac, like your Mac ARM or something? I was just wondering if you were already doing automatic kind of portability testing in your own development. So GC malloc, is that a good idea for greenfield development? And also just curiosity about your development environment, what you're using.
Yeah, I can take the first one, GC malloc. Currently in the D runtime, it's not really the malloc that's terrible, it's the free that's really expensive. So we're working on providing a faster allocator in that sense. You can use it now, it's just going to be not as fast as like C malloc. So it's okay to use it, just the performance isn't there yet. Until we get this new GC in, it's not going to be there. But yeah, eventually, hopefully, it just magically switches over to this fast stuff.
So there is something I want to add there. Yeah, so one of the design constraints of what we've been building is like if you use the allocation and the free function from the GC, you get a similar like memory and performance profile as you get from malloc and free from C. That's a design constraint, and that is working for us. So if you free everything explicitly, you should get the same as malloc and free from the system. And one of the big motivation there is that people use malloc and free, and then they pin and they do all this kind of funky stuff. But it always come back to bite you in the ass later on, because there might be pointer in there that you have not pinned or whatever. And we actually have a cunning plan of swapping malloc and free with our stuff, so that we can tell people like use malloc and free if you want, but it's gonna forward to that. It's almost working. There is one thing that is not working in that cunning plan. It is that when you start threads, or when you start and stop threads, the threading library actually uses malloc and moves stuff around and reuses buffer, does some like crazy shit in there. And the problem is, like, as part of the collection process, because we do parallel mark, we start thread and we stop them, and you need to get the sequencing of all of that exactly right so that you don't miss anything that is in the libc when it does this Chingenian, with thread creation and destruction. And we don't have that part completely nailed down, but otherwise it's all good. So that's the cunning plan.
And then there was a second question about the second one.
Just curious about your development environment to kind of
yes, the GC that we're building is using SDC. It's all kind of SDC flavored code, and it currently only works on Linux x86, right?
Yeah, it should be pretty close to working on OS X, though.
Okay, but we haven't tested
SDC
it.
works on
But the plan is for it to work everywhere, though.
Yeah.
And it will probably end up
everywhere, at least the big suspect, like OS X, Windows, and Linux, right?
Yeah. Cool. One last question down there with VJ.
There's many aspects of like making the system faster by having a more efficient allocator, and also one of the factors that goes in is how much are you scanning when you're doing your your sweep to determine what to garbage collect. And as you guys mentioned earlier in the presentation, often the way programs operate is there'll be a few variables that live for the entire lifetime of the program, and then there'll be like cycles of smaller lifespan variables. Is it possible, or would it be worth it, that if certain blocks of memory keep surviving sweeps, that they essentially get moved to another tier that's checked less often, so that each typical sweep is smaller?
So we actually have pieces of code to do that. Like we keep a generation in the block that tells us, essentially like how old it is. Right now we are not prioritizing that because we've found that prioritizing other stuff was working better. But I'm a bit like dissatisfied that we don't do more with that, and I think there is something there. I think you're right, there is something there, but we have not quite nailed it yet.
All right, well, that's everyone. So
I think Chris was...
What? Well, I mean, you're delaying your lunch at this point if you really want to ask it. All right, let's do it then.
Tomorrow, are you going to cover anything around like telemetry that you're going to report back, so that as an application, as a user of the garbage collector, we can see kind of what's going on, so we could see whether if we've invoked some pathological cases, that kind of thing, or is that a version 2 thing, or that you thought about?
This is like how does it perform, you're asking?
Yeah, in Windows for .NET, you've got performance counters that tell you how many generations you've got, that kind of stuff, so you can see whether you're doing stupid things by accident. So is that sort of
currently
we have ideas of what you might want to track and see, or how we could use that to feed back to for progress in future?
We use a very fancy technique to do that right now, which is kind of like printf, except we cannot use printf because it allocates. But you can use snprintf to print stuff in a buffer, and then use write to write that wherever you want. It's not ideal, though. We actually need some telemetry at some point, but we don't have that at this point. Yeah. No, yeah, it's useful for us as well.
Yeah.
But we don't have something that is streamlined on that front.
All right, now let's proper end it here. Thanks, guys. Yeah, they have like another 15 talks lined up, so you'll have plenty of time to ask more questions later. Right now, it's lunch. You've got an hour and a half. Be back here at 1:30 for the next talk.
You know the bone GC has all of
Yeah.
these tricks for the dirty
Perfect. run you through how this works anymore. You're like a seasoned professional.
Thank you.
One thing I will double check though is make sure I get your name pronunciation correct. It's like Murilo, right?
Murilo.
Murilo, yeah.
Exactly.
Cool. Yep, I think I've got it. And if not, my girlfriend's Brazilian and she will kick my ass when I get home.
Really?
Yeah. Cool.
I think that's the replay.
I think maybe the only thing worth pointing out is that you've already been told that they're what will be projected on the screen. So yeah.
Okay.
Otherwise, I'll wait until you're ready and then we'll kick it off.
Okay.
Hello. We all back from lunch? No, you are definitely not back from anything, sir. I mean, there's a few more people downstairs. We can wait for a couple of stragglers. I did yell out to them 10 minutes ago to get up here. I have an interesting thing that I think we should look into. I'm trying to find the nerdiest shirt at DConf. No, come on, you're just wearing a DConf shirt. That doesn't count. I mean, like proper nerd. Like Robert came up and it's like, oh my God, yes, I'm glad that you're wearing that shirt because this is from a Canadian television series, which, kind of nerdy. But I know there's nerdier out here. Like I saw Ian's shirt. If you look at the back of his shirt, it's like a byte header for an elf binary. There's a couple of jokes embedded in there, but I think somebody here must have a nerdier shirt than either one of those, right? No? Nothing? Wow. Wow. No, there's white collar, there's DConf shirts. I think there's just a handful of nerds in this room, which is frankly surprising. Oh, well, we might as well just kick it off then. I think that competition was a failure. Murilo is back. He was here last year. And I think I broke the pronunciation, Murilo, right?
Yeah,
that's better. Okay. He's going to talk about the search for artificial life in D-Lang. So, take it away.
Okay, can everybody hear me? Okay, so I'm going to have to speak a little fast because I have so much to tell you. The search for artificial life in D-Lang. Well, that's a little bit of a teasy title for talk, but what I'm going to talk about here is, have you ever heard of those software in which you can create a model of a biological system in order to watch it work? Like you can place the organisms, watch them interact, evolve. Some people use them for educational purposes or for research. I have started creating my own because I have noticed most of them were very limited. I've decided to create one which would be more complete, more realistic, and at the same time, very fast, one that doesn't require a supercomputer. And for that, I have used, of course, the language because of how very fast it is. This is just a beautiful image I found on the internet. When you think about evolution, you probably picture something like the apes, this stairway of apes. It was actually not like that. It was quite different from that, but that's what most people think about. And somebody had this brilliant idea to place the chimpanzee in front of a robot, meaning maybe in the future we are all going to become robots. I hope not. Okay, the definition of life. Why is it that a dog is considered life and this cup right here, this paper cup, is not considered life? Well, in order for something to be classified as life, it needs to have at least one cell. The cell is the building block of life. That's why viruses are not even classified as life. It needs to be something which reproduces, because that is the only way it can continue to exist. Otherwise, it will disappear in the blink of an eye. And it needs to be something that is like some form of machine that handles energy, that takes energy. It could be from the sun, it could be from plants, it could be from a prey it has just taken, and it uses this energy in order to function, just like a machine would. One great place for you to start learning about this fascinating subject is the YouTube channel of this guy here. Oh, wait a minute. It is not being shown. Let me see if I can. There, I'm going to switch. Back to there it is. Here, primer. This YouTube channel is really, really cool. The guy uses some animations made with Blender and a code written in Python in order to explain how evolution works here. I'm just going to click on a video just for you to have an idea. Where is the audio? Oops, I had it muted there. It's the next one. This one is going to give me what I need there.
Will still offer to cooperate and start shaking the tree. But the solo blob is just going to start eating the mangoes. Once the team blob realizes what's going on, it'll start eating too, trying to get what it can before the solo blob gets everything. We're going to have to make up a number here too, which again we can change later, but let's start by saying the solo blob gets 1.5 mangoes and the team blob gets the remaining half a mango. Then, when they go home to reproduce, the solo blob will produce one offspring for sure and then have a 50% chance to produce a second. And the team blob will just have a 50% chance to produce one offspring. Okay, now that we have two solo blobs, we can see what happens when they meet. They each go for the...
Okay, so if you guys want to learn, I strongly recommend you check this channel. Here. Okay, about other life simulation software. When I was a kid, I played this game called Spore. I played it so much. It was a game in which you would create your own creature and it would evolve from a mere bacteria into an animal and then into a whole civilization and then into a whole, how can I say, then it would evolve into having spaceships and traveling across the universe. It was really, really fun. And you could design your own organism. You could select the color, how many legs, all of those things. But of course, it was just a game. It wasn't a true simulation. It was designed for entertainment, not for education. But there is Conway's Game of Life, which is one probably some of you have heard about. This one is a serious one, which is used for research. This one, it really has all of the algorithms, the mathematical models about how life works, but it is a simple software where you only have those colorful squares. So what if we could fuse the two of them into one, right? What if we could have something with the complexity of Conway's Game of Life and the beauty of Spore? Okay, this is Charles Darwin. All of you know who he is. He's the one who figured it out. There were other people. There was a guy called Lamarck and some others, but he was the one who managed to understand it best when he published his book on the origin of species. And he managed to fully understand how it works after spending some time here on the Galapagos Islands, which are a group of islands in the Pacific Ocean. And he noticed that certain birds existed on several islands, and they were nearly identical. There were only some minor differences, like the birds on one island, for some reason, had their beak a little thicker and bigger than the birds from the other islands. And then he noticed that on that island, the fruits were hard. It required a strong beak for you to pierce it. And then he started realizing that the differences in the birds were related to the environment where they lived. But contrary to what many people at the time thought, and what many people still think, the body of the bird does not change in order to become adapted to the environment. What happens is something else. How does it actually work? It is an amazing trick called the natural selection, which has nothing to do with the smartest or the strongest. Natural selection simply says that those in individuals which can reproduce more often, the next generation will carry on their genes, and the next generations, therefore after several generations, you will see those traits nearly ubiquitous, like it will already have spread to most of them. So for example, when the birds arrived on the island with hard fruits, those who had a small beak couldn't eat very much and died fast. Those with a big beak could eat more, and therefore their offspring would carry on those genes. And so the next generation had big beaks, and it kept happening again, generation after generation, until it reached a point in which all the birds on the island, they all had a strong peak. So your body does not change to the environment, but those who are not adapted die, and only the ones who are adapted remain. It's kind of like that. Here, this is a simple image. Here you have a group of deers. I suppose those are deers. And then they migrate to an environment there, which is a very cold place. Only those who have a big fur, a thick fur, only those survive, and the next generation is going to have a much higher percentage of individuals with thick fur, and the next generation after that, and so on. But how did it all start? In order for organisms to exist, they need to have reproduced out of something, right? You came from your parents, who came from their parents, who came from their parents, and so on. But what was the very first? That is the question. Scientists believe it was this thing over here, the RNA. It is something that can be formed spontaneously, given the right chemical conditions. And once it forms, it has this magical ability to copy itself. And as it copies itself, some of the copies come out different. And as a result, you get to have different forms of RNA, and it will evolve until it ends up with all this diversity of life here on our planet. How did sexual reproduction help? What you're seeing here is the, I think it's marble lobster, they call it. It is an animal which it can reproduce by itself. It can make itself pregnant. Therefore, it can reproduce alone. It doesn't require a partner. And if you stop to think about it, that is the way it should be, right? If each person could reproduce without a partner, let's suppose we have here 40 men in this room and maybe 2 women. If each person could reproduce by itself, then the next offspring would have 50 people, right? If each of the 48 men and each of the 2 women can reproduce alone, then each person creates one more. So 50 people create another 50. But because we require a partner for that, then in this case, we would only be able to make 2 more people, right? Because there are 48 men but 2 women, so we would only end up with 2 more people. If you have, in the whole world, right? In the whole world, we only produce half our population. Each time we reproduce, it takes 2 people to make 1. So you can only create half the original population, and then you have to keep doing it again and again in order to, like, each couple needs to have 2, 3, 4 kids. If we could reproduce alone, then each time we reproduce, we would create another 100%. But why don't we do that? Well, it is because here. Well, there are some different debates about it, but some scientists think it is because when you fuse your DNA with someone else's DNA, it helps correct the flaws in your DNA and the DNA of the other person, so the offspring comes out with a better DNA. But another hypothesis, which is the most popular one, is the one of the Red Queen. Yes, the Red Queen, the name is after the Red Queen from Alice in Wonderland. It is because when you have sexual reproduction, the result is you have many, many people. Each one has kind of a unique DNA, so each one has unique traits. Therefore, if a bacteria or a virus shows up and starts spreading, many will die, but some will survive. If we did not have sexual reproduction, we would all be clones. We would all have the identical DNA. For example, this lobster, all individuals of this species, they all have the exact same DNA. They are all clones, which means if one bacteria or a virus can kill one, it can kill all of them, which means they are not going to exist for very long. Soon, they are going to run into some pathogen, which is going to wipe them out. Whereas those organisms that reproduce with sexuality, like us, we have already been attacked by so many different pathogens, and we are still here, right? The idea is to keep making people with different DNA, because the bigger the diversity, the higher the odds that at least some of them will be able to survive the outbreak of some disease, like, for example, the coronavirus. Some of us died, some caught it, and didn't even feel anything. AIDS. There are some places in Africa where the people, they have a partial immunity to it. They can catch the virus, but the virus that doesn't cause much harm to them. Here, take a look. Those are all the big cats, the felines. Look, you have so many of them, right? You have the cougar, you have the lynx, the leopard, the tiger. You have the lion, which does not appear here, but, well, there are so many of them, right? But when it comes to us, there are so few of us, right? You do not see different species of human beings walking the earth. There is only one species, only Homo sapiens, right? Isn't that a little strange? Why is it that there is only one of us when all the other animals have so many different variations of them? Here, our lost cousins. There was the Homo heidelbergensis. I don't know if it's pronounced like that. The Homo floresiensis, the Neanderthal, and the Denisovans. Those are some that have been found. There may have been others. All of those, they lived along with us. They existed only some tens of thousands of years ago. They existed along with the Homo sapiens. So they should be still here. They were intelligent as well. Maybe not as much as the Homo sapiens, but they also they looked like us. They made fire. They made tools to hunt. So why aren't they still here? Well, it turns out, for some strange accident, they all went extinct, and only one, the Homo sapiens, was lucky enough to remain alive. So unfortunately, we lost our cousins and we ended up alone. Here, these are some images of what the Homo heidelbergensis probably looked like. You can see, looked similar to us, right? Maybe the skull was, the brain was a bit smaller, but it looks so similar. I think if we had one of them here, we would not even notice. We would think it is just another man. The Homo floresiensis. This one is interesting because it was a small one. Some people have compared them to hobbits. It is because they ended up on an island. Food was scarce. So the smaller you are, the less food you need to eat every day, right? So they ended up evolving into becoming small people. And this is an image of what they probably looked like. I know in this image it looks like a chimp, but this was this species. It was an intelligent species like us. Not as much as us, but they were probably close. And the Neanderthal. These are some images of what the Neanderthal looked like. You can see in this second picture, right? It has red hair. Some scientists believe the Neanderthal, they had white skin, red hair, and freckles. But there is evidence that they went extinct before we human beings had that. So some people think the red hair and freckles we humans have could be a heritage from them, but there is evidence that freckles and red hair only appeared in the Homo sapiens thousands of years after the Neanderthal had already gone extinct. Denisovan. The Denisovan, last I checked, they did not know yet what it looked like because they had little data on it. But they believed it looked similar to the Neanderthal. So this is an image of what a Denisovan possibly looked like. Why do we have different races, right? You look across the room and you see so many different colors of skin, hair, eye, so many different shapes of mouth and nose and head, so many different heights. There is more to it than just sunlight. Most people think human beings started black in Africa, migrated to Europe, turned white, and this is it, because in Europe there was little sunlight. It is way more complex than that, because it turned out our lost cousins, we interbred with them, which means we all carry, most of us, not all, but most of us carry a small percentage of their DNA. Here, we are hybrids. Most of us carry more than just Homo sapiens genes. What you're seeing here, this image, is the image of Denny, a fossil, which scientists believe was the child of a Neanderthal with a Denisovan. Apart from some of the African population, all the rest of the world has a small percentage of Neanderthal DNA. There are some places in Africa where the people are 100% Homo sapiens. But apart from those places, everywhere else, the people have a small percentage of Neanderthal, and there are many places where they have a small percentage of Denisovan. So chances are many people here in this room, if we manage to check your DNA, we would find traces of the Neanderthal and the Denisovan inside you. Now to business, enough biology. You came here for D-Lang, right? Where does it fit in? This is DConf, and I am talking about evolution. I think some of you may be getting bored by now, but finally I'm gonna get to it. That's what you wanted to see. Why did I do that? One reason why I did that was, well, first, because it would be a great talk subject for me to be selected for this conference. Second, because it is very fun. And third, well, there is one reason. I hope my software may later evolve into something more commercial and more scientific. Maybe my software will be used by universities in the future, because I always found biological simulations amazing because they hold the key to create better machines. This is just an image from the internet showing a mechanical fish. But the idea is, by watching how organisms work, we may figure out how to make better robots, better software, because think about it. Your body is able to run, jump, hold things. It is able to think, to recognize faces. So nature can create such fantastic machines. So we could learn from that. Instead of simply trying to create our own machines from scratch, we could take a look at the machines that have already been created by nature itself, right? The airplane was created after they watched birds fly. The neural networks, they were created after they investigated how the human brain works. Meet the amazing slime mold. This creature I'm going to show you, it's a mold which grows. And scientists think it has some sort of intelligence, and it is able to hold some form of memory. They say it is able to solve some puzzles, some mazes, because it grows in a way which resembles the way a complex system works, like the way neurons in your brain would work. Let me show you a quick video, just so you have an idea what I'm talking about here.
But it's kind of like a mass that keeps getting bigger and bigger.
Look out, world! The real-life blob is here. This isn't a horror movie. It's a new exhibit at a Paris zoo featuring this fascinating, fast-growing, and quick-thinking organism from the slime mold family.
The organism is growing at a geometric rate. By all accounts, it's at least 1,000 times its original mass.
The real-life blob can heal itself in minutes if it's cut in half, and move more than an inch an hour without any limbs. The blob doesn't have a stomach, eyes, or a mouth, but it can still find and digest food. And it doesn't have a brain, but it can solve problems and communicate what it knows with other blobs. And though it is neither an animal nor a fungus, it can act like both.
Then on, there's no stopping the blob as it spreads from town to town.
Scientists have called the blob one of nature's mysteries. These types of organisms are found all over the world and typically grow in dark, damp forests. This real-life blob is the first of its kind to go on display in a zoo. Here's hoping it doesn't decide to turn on its human friends.
I think you pissed it off.
This is InsideEdition.blog.
Wait. Okay, here. I had seen once a video years ago, I don't know if it is true, but it said that they made like a miniature map of the city of Tokyo. All the buildings were actually pieces of food. They put this slime mold in there. It started growing in order to get the food, And after a while, they saw that the blob grew and formed a pattern of connections, which was very similar to the subway of the city of Tokyo. Okay, now the moment you've all been ready for, I'm gonna run the biological simulation software. But first, there is a good friend I want all of you to meet. I want you guys to meet this animal here. It's called a capybara. It is an animal, I see it in my city all the time. It is a rodent, just like a hamster, but it is the biggest one on Earth. It exists in South America, and it swims very, very well, by the way. You see packs of 20 of them swimming in the lake all the time. And they are very friendly, too. Here, let me show you guys a quick video. This is a video showing them in a city in Argentina, but you see that in many other parts of South America, in my own city too. They are very cute, aren't they? Now, moving on. Okay, and now I'm gonna, there. Finally, that's what people want to see, right? Okay, so here it is. This is just a backup when I am developing a software. The ARSD library, that library made by that guy called Adam Roop, that's what I use. The images of the environments, the images of the foods, the images of the interface, the images of the organisms, the sounds. This is a manual explaining how it works. This is a file which is kind of like a documentation of the source code. I am writing a documentation in this format. It says what the code is doing. That way, if you want to understand the code, you can read it alongside this. Here, this is the source code. So as you can see, number 1, the number 1 here maps to the number 1 here. The number 2 here maps to the number 2 here. The number 3 maps to it as well. Here, the number 3. The source code is getting very big, but of course, what you're seeing here is just the very tip of the iceberg. I have also this other file here called Toolbox, which is where I have all the classes, functions, structs, the variables. This is where I have all the tools which are going to be used in the source code itself. I always do that. I always create a file called Toolbox where I place all the tools which are going to be imported later. Okay, let's run it. I still have 11 minutes. Let's run it. Here, it's this one here. Where is the audio? It was supposed to have an audio. There is the audio. Here. Biosimulator. You can switch off the soundtrack, your choice. There is a manual here for the user who doesn't know it yet. And you can change pages here to read it. Now we can start a simulation. Here, you can go back, restart it. You can start a random, meaning the software will pick randomly an environment, foods, organisms, and you're just gonna watch what it chose for you. It chooses stuff randomly, right, using the std.random module of D-Lang, or you can create your own custom simulation. Now you can choose an environment here. You have the outback, the rainforest, the tundra, the savanna, the desert. Let's pick the outback. Now you can select the amount of foods. You have grass, apple, orange, lettuce, carrot, blackberry, banana, cabbage, cherry, cucumber, grape, peach, pitaya, raspberry, tangerine, leaves, watermelon, pistachio, avocado, acorn, tomato, and I am gonna add many more. Right? This is gonna be a long-term project because I'm gonna have to add so many. Here, let's add some apples. Not too many, a little less. 20 apples, 5 carrots, and many blackberries. There. Okay. Some cabbages too. Now, next. Now you can select the amount of organisms you want, right? Here. You have the capybara, the cow, the donkey, the leopard, the squirrel, the lion, the anaconda, the rat, giraffe, alligator, badger, chimpanzee, frog, fox, the green rat, snake. This one, the name got too big. I have to increase the interface here so it's big enough to fit this name. But anyway, you can pick how many males and females. So I'm gonna put 10 male capybaras, 10 female capybaras. I'm gonna put 6 male cows, 8 female cows. I'm gonna put 2 male leopards and 1 female leopard. Okay, let's start it. There it is. The simulation is running. The creatures, they are moving around, and you can navigate the map. And you can increase the speed too. There, now it's much faster. Let's make it a little slower. You can end it if you want. We're gonna go back to the home screen. You can, if you want, you can restart it, like it's going to restart with the exact same numbers you had selected, the exact same amount of animals and foods in the environment you had selected. But let's restart it. There. It restarts. It will later become a simulation which will contain thousands, maybe tens of thousands of organisms. It's going to be heavy duty. It's going to be very heavy duty on your CPU. So you can go into blind mode. it is still running in the background. It's just not drawing anything here. The simulation is running blind, meaning it isn't drawing the creatures and the foods in order to use less CPU time and run faster. But when I remove it, oh, look, this is moving downwards, right? So I go blind, I wait some seconds, and when I see again, it has moved. So it's still moving. It is blind, but everything is still happening. You can take a look at the status of the simulation here. It gives you the start date, the total of live organisms, dead organisms, the total of organisms live and dead, the total foods, the available foods. I mean, the total foods is the number of foods that had started, but some of them have already been eaten, right? So now we only have available 99 of them. And you can freeze the simulation in order to examine it here. Once I freeze it, everything stops happening, and I can click on something here. I can click in order to see what it is. Here it's a blackberry, which gives 500 joules of energy if an animal eats it. Here, that's a leopard. It is alive, status, name, gender, male. The amount of energy its body has available, the muscle weight, the fat weight. The total weight is muscle plus fat plus bones plus organs, so the total weight is that. This is the height of the animal. This is the speed at which it moves. This is the diameter of the pupil of the eye of the animal. I'm going to explain you the reason for that very soon. This is the distance it has walked since it last ate something, and this is how far it is able to see. It is able to see 98 meters ahead of it. And you can move things around it too here. If you click with the right button, I can move it here. I can move the food too. I can even move it to other parts of the map here. I can put it right here if I wanted to. This blue square is the vision of the organism. So the leopard can see everything within this blue square. The cow can only see everything within this blue square. So each animal has its own vision. Here, the capybara can see within this blue square. Now, okay, you guys have seen it all, but you guys are probably wondering how it works. So each organism has inside it, each organism is a class which has its own image, name, right? The weight, the speed, the list of foods it eats, and it has an algorithm which tells it how to move. So it keeps moving. It simply picks a direction randomly, and it keeps walking straight in that direction, searching for food, because food gives energy. When it eats the food, it acquires the energy of that food. However, if it sees a predator, then it starts running in the opposite direction, and therefore its speed increases. But if the speed increases, then the energy it consumes at each move will also increase. As the animal moves, it burns its fat for energy. If it runs out of fat, it burns its muscle, which doesn't yield as much energy as the fat, but it still does, and once it runs out of muscle, then it dies. So the animal has to be finding food in order to maintain energy, in order to survive. However, as the animal loses fat, it becomes lighter and it uses less energy to move. And the animals, they reproduce too. So here, I'm going to put this capybara close to these berries, and it's going to move to eat those berries. There. It is moving. There, it ate the berries. Now, here, I'm gonna take this leopard. Oh, this leopard is hunting this capybara over here. Look. It's chasing it. But the capybara is running faster than it. I am going to help it out here. I'm gonna place it right here. There. Let's help it. Almost. There. There. Now it killed and ate it, and now what you see here is just the corpse of the capybara. Yeah. If you click on it, now it shows status dead. It shows everything it had before it got killed. And now just to finish it up, because I know my time is up, let me show how they reproduce here.
Yeah, I'm thinking we can have questions going while this is running on in the background. What do you guys think? Yeah, let's see some more capybaras.
Here, these two, they're gonna see each other, and watch what happens. They meet, and a third capybara appears. So now there are 3 of them. This new one here, a new capybara. Okay.
All right.
Thank you.
All right, let's get some questions going that don't involve how to turn it into a The Thing simulator. Any questions?
Hello? Hi there. Very nice presentation and simulator. So I was in grad school. I worked with a lot of biologists who would probably love to have actually a tool like this for like population studies and that kind of thing. Have you thought about talking to researchers at universities and kind of showing them this and what you could develop?
Yes, I am just waiting for it to become a little more mature, and then I am going to start doing that because I am trying to make that as realistic as possible. For example, you see here it says the height and the eye pupil diameter. It is because in order to calculate how far the animal can see, it depends on how tall it is and the size of the pupil of the eye. For example, the eagle with a very big pupil can see much further than a mouse that has a small pupil. Also here, you see that the units are in joules, meters. I try to use the international system. So everything here has to be in the units which are used in science. So meters per second, kilograms, joules. I could have made the diameter of the eye pupil in millimeters, but now it has to be meters because this is the international system of units. And here you can see the vision range. With this height and this eye, it can see 38 meters ahead. So I am still maturing it into something even more realistic. I have to add water to the body of the animals. I have to add the ability to find and drink water. I have to add the temperature of the environment, because you can see here, look, the sun is going up. It goes up right here. This is the time elapsed. Hours, minutes, days, months, years. So the sun goes up, and once it reaches the limit here, it is going to turn into night, and then the environment is going to be darker. However, I have not yet set up so that the temperature will be smaller, but as you can see, both the environment and the map are now dark as the moon is moving. So I am still working on all the details before I start advertising it. any more questions. I think this one, because it was not so much about the language itself, I don't think it has provoked too many questions in people. Or maybe because I made myself very, very clear, everybody understood everything perfectly.
Oh, Ricky's asking on the internet if there's going to be like classic wolf and sheep or wildfire models in the future for this thing.
Yes, of course, there will be. There will be, definitely.
But if there's no other questions, I think we can just say thank you. Well, and you've either got 10 minutes of watching Capybara or you've got 10 minutes of going downstairs and having a break. Your choice. I'm not going to force you on to do one or the other. don't need to check behind you to make sure anything's working. Yeah. That's going to be pretty handy, I guess. Have you got that on duplicated or extended displays now? Okay, so it should be showing up. So it's just screens are off for the moment. Oh, it's just not coming through the feed at all, is it? Right. Ah. Yeah. That looks like it's running Windows 10 at least, right? Running a Linux system. Oh, okay. Yeah, okay, that makes sense, yeah. Yeah. And, walking around as well, beware, do not do the what was the Ali after a well-known first kick down the back. So it's not called the Ali. So don't do the Ali. It's fine. But otherwise, just time down there when we got left when you've got 5 minutes left. I will soak up a big 5 minutes for me. You've seen how. Yeah, I mean, especially if it wants to. I mean, it's not too many in-person talks like this. You always got to leave a bit more anyway because people are going to laugh. People are going to take that range. It's golden, you know. Especially if you're in front of people instead of probably going to talk faster as well. It's just one of those facts. That you're nervous. You got to get through it. You're in a room full of journal papers. You can just calm down. You can just. well, you know, you've got 2 jugs to go. I think you'll be fine. Toilet's just right there on off stage. So, you know, you're all set. You're all set. Like a prison guard walking around with this thing, actually. Just test that it goes forward and backwards when you click it. All right, we're good. Hello, we are back after some technical difficulties. Are you back? Are you sure you're back, Attila? Because you were not that enthusiastic an hour ago. Okay, okay. I mean, are you sure it's just caffeine in there? Because you were not that enthusiastic an hour ago either. Okay, we have a new speaker to DConf here. First time. Arthur is going to talk to us about exploring declarative capabilities of D. So, by all means, go for it.
Hi, I'm Arthur, and I'm very glad to be here. Thank you. I'm very excited, and I'm really itching to tell you about this. Like it has been announced, I'm going to talk about declarative programming. So for some context, I'm the author of Fluid. Some of you might have heard about it. Well, it's a user interface library, which is obviously declarative. What I want to point out today is what makes D great for declarative programming. After all, it's my choice language. Out of so many possibilities, so many available languages, I chose D, and I made Fluid with it. So I want to show you how it's good for declarative programming using metaprogramming, and how can you take advantage of it. So when I say user interfaces, I mean means of communication, right? I'm a human. Here I've got my computer, which doesn't really want to talk with me. But we don't speak the same language, right? And yet, the computer has a task, has a job, and I need to control what it's doing. I need to somehow talk to it, somehow communicate with it, and this is the job of user interfaces. Despite us not having a common language, really not being able to talk to it, user interfaces make this communication possible. In context of Fluid, we'll be talking about graphical user interfaces. So we have a surface, a screen that we will present data, information on. And now, using the same screen, presenting components, interactive components, we're going to use a mouse or a keyboard to talk to the computer. So user interface will consist of components that will reappear all this time. Like, if we have something, the user, for example, has a confirm an action, like in the slide previously, we are going to have buttons every button is going to act alike. They have differences in size, text, and styling, but more or less they're going to look, more or less they're going to have the same job. I'm just going to assign a different function that is going to perform when clicked, but it's going to be a button no matter what it does. We've got a lot of other components. So for example, if I want the user to type the name with a text box, that's the component I want to use. So, but it's not just components, right? Say, I have a screen. The screen has limited space, and I need to assign these components, place them, lay them out on the screen in a way that makes it readable, clean, intuitive, and consider how many variables we have here. The text can have varying size. We can have long text, short text. We can have images of different proportions. Now I said we have user input, right? So we have data that is going to change. So you might have more or less components, more or less information, different quantities of everything. Add to this, in this age, we also have all sizes of screens, from mobile phones that are so tiny, laptops, and screens as big as this one. Now, also different proportions. This is a landscape screen. This might be a portrait screen. So we also have to take this into account. We call this responsive user interface, and if it is this. But had enough? We also have to consider that users have different needs in terms of accessibility. So for example, if I have some small text on the user interface I've designed, then maybe it might not be readable to everyone. So for example, they might want to set a minimum text size that we can't cross. It will be enforced. And a user interface needs to adapt to this requirement. So a user interface designer will have the job of creating a user interface, and maybe they will make a sketch of a user interface that looks like this. So to present this, after all, the computer has to understand this just as well. We might prepare a sketch on paper, but now the computer needs to understand our user interface, so we can actually display it on a screen and then make it interactive. So for example, maybe I'd like some text up here. Pretend this is text, all right? Underneath, some more text, smaller. Yeah, nice. Now, I need some dynamic content, right? So maybe some text on the right next to this little one, not the one at the top, with some buttons, oh, like this. See, you probably recognize this already. This is a tree. User interfaces may be made with a tree. There are different ways, of course. It doesn't have to be a tree. But as far as I know, this is the most common way, and Fluid also does user interfaces with a tree. So this is what we're going with. Now, our user interface designer prepared the sketch that we have seen just a while ago. Now their job is done, and they pass it to a programmer. And our programmer wrote this code. Oh. This is gross. Look, I just told you, this is supposed to be a tree. This is not a tree at all. This is completely flat. Maybe if I look at this, I can see after a moment that this is a user interface because there are some common keywords. If I want to see what this is actually doing, I will definitely need a piece of paper, sketch it down, see what it is actually doing, but I can't read this code just seeing it. It's not enough. So if we want to make it look like a tree, then maybe we could use a different format. XML is pretty common. You've probably seen something like this before. So now we have this. We turn it into this, an XML file. This is much nicer. This is a tree. It's clear. every tag in XML represents a component, and attributes let us design, specify all the properties that define the layout and values the content. This is nice, but now we have to make this interactive, right? So I have pressed onClick right here, but what is onClick? I never defined what onClick is. So now I need to bind it into decode now. So we get something like this. For example, it doesn't have to look like this, but in this case, we need to know that the identifier I have here in XML is actually this delegate here. We need to bind it together. All right. Now, what about dynamic content? This frame, maybe I need to add more labels, add more text or different components, depending on the information that we have, depending on what the user actually has provided. So our next step is this. We create an attribute called ID, and now given this ID, we can insert new items into this frame. And things are getting pretty ugly here already. See, I have an array of items, and I need to load another XML file, or if I want to take a shortcut, I could create a new label or whatever component I need on the spot, but if you want to stay idiomatic, we are going to have to load another XML file. We need to find whatever content we have in there, and we need to update the text. We need to add the element then, and things are getting pretty nasty at this point already. So maybe we could, someone has this clever idea that we could use templates, right? So inside this XML file, we add those pretty tags that say that for every item in this list on the left, we will create a new label and fill it with the tags in the list. Cool, right? Not really, not really. See, templates are so complex when you look at this. It just takes a while to see that we already have 3 languages involved. We have D, we have XML, and now we have another template language. And furthermore, 2 of these languages are programming languages, which means that we have 2 distinct programming languages with different semantics. So every once in a while, this is going to bite us because we forget, for example, that something doesn't work like this in one language, something works differently in the other language. And also because this is an XML file that will probably run at runtime. We'll probably load it at runtime. Of course, there are things like diet, but I'm not going to cover that. Usually, these things will be runtime, right? So now we have to bundle a runtime for this language, for this template language, along with an app in order to actually fill what this template here does to make it work. And those runtimes usually aren't cheap, and this is a lot of overhead going on in here. We could do it better, right? I hope we do. And let's think about this for a moment. Does anyone write arrays like this? There are some use cases, right? But usually there's no need. We can do something like this, right? We have a nice array literal, it does the job. Couldn't we apply something like this to our user interface? Couldn't we make our components this way? So I'm here to present you, I'd like to present to you how Fluid does it. This is nicely, immediately you can see this is a tree. We can immediately see we have components, vFrame label, HFrame label, vFrame label button. Additionally, with all the properties like the layout that we have specified earlier in XML, and we also need no binding because D handled this. D has a full namespacing, module system, everything. So we can add all the dynamic content inline using names from D, and I can also specify the delegate I wanted write in the code. Neat. So if we want to make a user interface like this, where do we start? Let's see. A user interface has multiple layers that we need to go through. When I make a window, the first thing, I'll need some context, right? Content. I have to display some text, information, wherever. That's one thing. Second thing is layout. I need to place all the things on the screen. And thirdly, I need to style them. Need to, like I said, my buttons might need to look differently depending on whatever the designer required me to do. So let's start with content. Fluid is object-oriented underneath the declarative layer. So maybe for constructors, let's go simple and just go with content. A label is there to display text. So a label is going to take a string of text in order to have something to display. A button actually is a label underneath. There are different types of buttons. We can have a button that displays some text that we can press. So we could have a confirmation button that says OK, so we can confirm our action, press OK, we're done. And furthermore, a button needs to do something whenever it is pressed, so we also bind the delegate on the spec. Simple enough. An image view is there to display pictures. So a path to an image is going to do the job. Maybe if I want to, I can also pass image data on the spot. A frame, like we said, we could use more components to create our user interface with more components. So a frame is another component that is going to display our things, just like in the example I showed earlier with the tree. A frame, in case of fluid, actually does both the job of a column or a row. So now that we have all those components, and we know that their constructors are going to take content, there's just a little thing I need to complain about, is that a frame, like I just said, could fulfill two roles. It could either align the components it contains in a column vertically or in a row horizontally. Now we have a single constructor because as I said earlier, we have a rule of thumb. Our constructor will only take in content. So our frame, how do we say if it's vertical or horizontal? We could use a static method. So one static method will create a frame and make it vertical. One static method will create a frame that is horizontal. We will have a button, and a button uses a regular constructor because there's just one main text button. Other types of buttons will be a different type of component. Like a frame button will actually be a frame that acts like a button. So we have a frame button with two static methods, and now we have a number input, which is a template, and you probably see where this is going. This is inconsistent. Like, I don't want to remember whenever I have to use a dot in a name or when do I have to type new and when I don't. So maybe we could simplify this a bit with the most powerful primitive that D offers us. It's called a function. So we could use a vFrame function and an hFrame function to specify if our frame is going to be vertical or horizontal. Similarly, we can create a button with a button function, a vFrame button for a vertical frame button, an hFrame button for a horizontal button, and so on. We can also make shortcuts for templates that we instantiate very often, like int input, float input. Now, we've covered content, so how about layout? See, I've said we have frames. In this case, we have two horizontal frames, each with 3 nodes inside, except for the text. This, we have 3 tightly squeezed components, very close to each other, that have a lot of remaining space. And below, we have 3 components that occupy all of the space that we have here. We need to set a distinction because a frame itself does not specify which one of these two it will be. We have two special properties that every node can specify. We call them expand and align. In case of fluid, some frameworks do it differently. So a node that expands, that has expand set to 1 or more, will take all the remaining space, or rather a fraction of the remaining space that no node needs as a requirement, as a minimum. So in this case, for example, we have in the second row, we have 3 components with expand 1 that each take a fraction of the space that is available. This way, we have 3 columns equally sized. Here, next to these 2 components, we have one frame that has expand set to 1 and align set to fill. The alignment makes it so, unlike the components on the bottom that take up space but don't actually use it, align fill makes the component use the space it has expanded to. So these components on the bottom instead have different align values, align left, align center, align right, which places them relative to the box that they have been assigned, the space that they have expanded to. So the space they occupy is now, it defines how they're placed within the space they occupy, simply. Now, to do this with frame, we're going to use the previously mentioned tags, like these ones. A layout template function takes a number and a string. The number defines our expand property, and the string defines the alignment property. For what it's worth, expand is a number and not a Boolean, because you can make a component take 2 columns instead of just 1, if you need more control over the space. But most often it's just 1. Now we can stack as many of these. We can stack as many of these as we want. So I can put a frame, and I can set a theme which checks another box that we've prepared. We have styling now. All the 3 layers are now complete. On top of that, we have a layout. And we also have other tags, like tags. Actually, a misnomer. I should have called it properties from the start. It's called node properties. But I could use a tags property to specify the tags for a node, which allow for organization. That is very similar to CSS classes. And for example, I don't want a component to be visible from the start. Maybe I want to prepare it for later use. So I can use a hidden property to hide it and show it later. A disabled property is for nodes that I don't want the user to interact with yet. Maybe they're anxious and they're not ready yet. And maybe for other components, we could also define other properties, like a frame. Maybe we want to support drag and drop, so I want to be able to drag one component and drop into the frame we have prepared here. Accept drop does the job. A size limit is for size-locked nodes and allows me to restrict the size that the node will take. This is very helpful for responsive layouts. What I call this is the node builder. This is the node builder pattern, similarly to the builder pattern that you might find often in object-oriented programming languages like Java, which in this case, we create a node, and the second thing we do is we set the properties on the node using the builder pattern. So in this case, the frame, the function that creates the frame is what we call the node builder, and these parameters, these properties, these purple fields, parameters, we call them node parameters. This is terminology specific to Fluid. It does not apply to other frameworks, but I just want to make that clear because I will use these in the rest of the presentation. We can create our own node properties by creating a struct with an apply function, an apply method this method has to take a node. Like I said earlier, nodes don't have, our properties don't have to apply to every node. Maybe I want them to only work on a frame or on a size-locked node, so I can replace the node parameter here with another type of node. And it will only apply to these types of nodes that I want it to work on. Inside, I define what exactly this property is going to do. So for example, the hidden property on the left is going to do exactly what it does on the right. This is actually the actual definition in Fluid source code. It just says that this hidden property to true, and properties are usually simple. They don't do anything too complex. Instead, usually they just control behavior that is defined within the node itself. So what we have on the left is really more or less equivalent to what we have on the right. I've also mentioned variants, like we could have a horizontal or vertical frame. So to make the behavior work, our H frame is going to differ from a V frame function by setting a node is horizontal property to true the moment the node is created. You might ask, what makes this different from UFCS? Because these are very similar. So isn't this just UFCS with extra steps? My simple example is that in case of a component, these properties are usually, there's very few of them. The ratio of properties to content is usually very small. So when I see a node, it is really far more comfortable for me to have them at the very top of the node, because this just makes my job easier when reading the code. I can immediately see what's going on. For example, by seeing the theme that is applied, I can immediately know that this node has a certain styling properties or whatever. Content is slightly less important. And also, it does make some decorational visual changes, like in case of UFCS, I do think that in a tree structure, UFCS is a bit awkward to use. Like, this formatting is weird. So in case of a node builder, we instead place them inside the parentheses, which makes it very clear that these properties apply to the node that we are creating, and this is like obvious, I hope. I don't say that UFCS is bad. I actually love UFCS. But I think UFCS is better for properties that are transformative, like, for example, mathematical transformation, geometrical transformation are a perfect example of using UFCS, or ranges. In this case, we are creating a node immediately with some properties set, so a node builder, in my opinion, is just more appropriate for the use case. Oh, something went wrong with the PDF. I did not see that. So it's time for the magician to reveal the magic. A node builder inside Fluid is made with a template. This is a node builder template, which takes a parameter that defines which component the node builder is going to build. So a V-frame node builder is going to build a frame. In case we have a variant like an H-frame, we can set the property, like I showed you earlier, through a delegate that will set it immediately the moment the node is created. So, like the misplaced node is supposed to show you, I should really note that I've very recently coined the term node builder. So inside of Fluid, for the lack of better name, it was always called simple constructor, and it remains so in the source code. Only the very latest version that I've released like less than a week before DConf, node builder is even available at all. So you'll still see simple constructor all over the place if you use Fluid. Just saying. Now strap in, because I'm going to show you some metaprogramming. And as simple as it is for metaprogramming sense, I do still think it can get pretty difficult to understand at times. So what a node builder is I've lied to you because I said it's a function, it's actually a struct. there's a few things that make it easier for later metaprogramming use, that make it more practical to use a struct over a function, but whatever, it doesn't matter. It could be a function if I wanted it to. Now, we create the struct by passing the frame parameter into the struct. The struct is templated just as well. So the node builder is also going to take the same parameters that the template above takes. And from now on, inside the node builder, we will refer to the type that we are creating using the magical keyword type. So whenever you see type from now on inside the struct, you know we mean a frame. Now, to make our node builder behave like a function, we need to overload the opcall function. It's from, you can check the spec, it's in operator overloading. Opcall lets us define what happens if we try to call the struct as if it was a function. It returns a type, like I mentioned earlier, which means it returns the frame. And it takes a variable template parameter eggs, which lets us take as many arguments as are needed. The user, while calling this function, can pass it as many parameters from 0 to 100 or more, however unpractical that might be. And what this lets us do as the programmer, as the developers of this function, it lets us check the type, analyze the type of each argument, which is going to come really handy in the next step, as we have to split the parameters, the node parameters, from the content that we are going to pass into the constructor of the function. We have to draw a line between them. So the first thing we're going to do is to calculate the number of parameters that we have. So in a case like this, where we have 2 labels inside a frame and no parameters, the parameter count is going to be 0. In a case like this, when you have 2 parameters and 2 labels inside, the parameter count is going to be 2 because we have 2 properties at the top. Edge case, however, we are not going to accept cases where the parameter will be somewhere after the content, mixed with the content. We want them to be at the top because otherwise we are just missing the point. And besides, it also makes things simpler. So on leading parameters function will return parameter count 1 in this scenario. Leading parameter is rather straightforward. We're going to iterate on each of the parameters earlier, on the types, and we're going to go through each type and return the index of the first type that is not a node parameter. In case we have a function that is full of node parameters, that means the argument count is the exact same as the count of parameters, and that's the whole function we have. So, for example, if you have a call like this, a theme will take a theme is a node parameter, all right. Layout is a node parameter, all right. Label is not a node parameter, and its index is 2. So we are going to return 2, which matches a parameter count 2. A node, to check if a type is actually a node parameter, we are going to use traits compiles, simply to see if this call to apply will compile. There's nothing complex about this one. We don't need the init. They don't need to work on the init values themselves. They most likely won't. But the point is that these have to compile. All we're checking is if this parameter, if this type is actually compatible with the node, and also if it actually has an apply method that could work, right? So, for example, a theme will work on a V-frame because it has an apply method. A layout will work on a V-frame because it has an apply method that accepts a V-frame. However, a label method does not have an apply function at all, let alone one that would work with V-frame, so it is not a node parameter. And size limit is however, like I said earlier, will only work on a size-locked node, not on a regular V-frame, so it also won't work. This will be rejected at compile time. Now, to finish our job, we are going to pass all the parameters after the line that define our content and pass them into the constructor. And the remaining parameters, the ones before the line, are going to be our node parameters. So we are going to place them. We are going to call the apply method on the resulting node. And also, in case we have a variant like hrame, we are going to call the function that we've passed into the second parameter if this was 1, and in order to make sure it creates the right variant. Like in this case, a direction horizontal for a horizontal frame. And that really is it. As a side note, actually, because I did not make a slide for it, you might also ask me why didn't I use named arguments? The answer is as simple as the time as I created Fluid, there was no named arguments. But it's also, if you recall the argument as the slide when I said why not UFCS, named arguments also fail there, because usually they will be placed after the content, not before, but also they're still beta quality, so they don't work well with templates or inheritance. So thank you very much for listening in. If you want to try Fluid out, then there's dub init. T-Fluid will do the job, but just please make sure to use the latest version because dub doesn't always fetch the latest. I don't know how it works. And in case you feel so inclined, you can also sponsor me on Patreon to help Fluid's development. Thank you very much. Time for questions.
All right, who's got a question? First time DConf speaker, so let's make it a good question just to start off.
I want to, first of all, thank you for your nice presentation. And last night at BeerConf, I was already talking with Attila about how GUI programming sucks and all the libraries are awful. So I'm always nice to see some actually, nicer interfaces for that. So as a question, first of all, have you heard of immediate mode GUIs?
Yes, I did.
So the question then is, have you considered using that, and why did you choose this approach?
It was a while ago when I decided that Fluid would be a stateful framework. And I think the reason is I'm just a lot more familiar with how stateful ones work in general. I have a lot of familiarity with it because I've worked with so many stateful ones before, and at the time I started creating Fluid, I actually did not use an immediate mode library, not even once.
Okay.
When it comes to writing these modules and having like the layout, the content and whatnot, as well as like the styling information, like whether there's spacing in between, the font size, these kinds of things, what are your thoughts about systems that completely separate like the style from the contents, kind of like CSS and HTML? And I recently read that GTK apparently can load certain CSS properties, which I was surprised to learn. What are your thoughts about a complete separation of style and content?
Well, if by complete CSS is enough, then I actually really like it. I really like it, but in case of CSS, I don't like it exactly because CSS is not... CSS also does layout, actually, because you specify display type inside of CSS, but other than that, I'm a big supporter of separating styling from the content myself, and Fluid also does that. What I showed you here is that you have a node parameter for theme, which like I said, connected with the actual theme set earlier, defined earlier in like a style sheet. And you also have tags, which like I said, are basically the equivalent of CSS classes. For what it's worth, I did not show you because I thought I wouldn't have the time for it. Fluid actually also has a declarative declarative API for creating themes just as well. But it's a bit more quirky than this one, actually.
We have a question from Ricky on YouTube. Would you consider swapping those strings for alignment to the member of operator?
Can you repeat the question?
The strings that you had for alignment, he's asking if you want to switch it to the member of operator.
Yeah, actually, I would. I originally used strings exactly because we did not have a member of operator. So if in case we do get one added, it would be very, very nice.
Is there any more questions out there? Going once? Going twice? 2.5? No, all right. We're done. Thank you.
Thank you.
See, it's that easy to be a first-time DConf speaker. So for those watching at home, come on, submit some talks next year. Everybody else, we're back here in about 12 minutes, according to my clock, for the next talk. So enjoy. Okay, everybody, get back to your seats. Come on. Come on, I know you want to. It's your favorite spot. It's your seat. Come on. Come on. Where is everyone? Oh, back to high energy mode. Welcome to the 3:30 slots. This isn't just any ordinary 3:30 slot. We have a first-time DConf speaker again. See, you get applause if you're a first-time DConf speaker. So submit talks next year, those on the internet. Emmanuel here is going to talk to us about C++ interop. So,
hi everyone, my name is Emmanuel and I'm from Ghana. And I joined D last year working on C++ interop with Matthias, and it has been a great journey. So about me, I like C, I like D, I like C++. Those are the three languages I really like a lot. I write them every day, and I did SOC last year. Matthias was my mentor, and I'm currently researching into network buffer bloat issue of the packets dropping and all. So my target for this talk is two people, basically the D beginners, like the D programmers who joined D very early and have struggles with C++ interop. I was one. When I joined, I used to compile G++. I used to link G++ compiled binary to D code on Windows because the spec didn't really specialize what it was. So I was struggling. I spent over a month. I nearly gave up. I was like, I'm not doing this again, and I stopped. And I think I was reading on a blog, and someone said, no, you should do it on Linux. And I was like, let me try this again. If I try and it doesn't work, I'm not coming back to it again. And I tried on Linux, and it worked. And I was like, oh, okay. So the other people are maybe the experts, the D experts, which are you guys. And that will be showing you guys the state of the STL interop, the C++ STL interop, which is Linux, set, vectors, and then strings and lists, and map and on other map is not a finished work, but it's in progress. So C++ interop is a global topic. I think every emerging language is trying to interface with C++. Rust, Zig, I know Carbon is doing, I know Python also does it, I know Swift also does it, but when you look at their approach, it's very complex, it's very writing a lot of wrappers and finding, like they target as a very difficult topic, and it's like some do and they just give up. Some are investing a lot of time into interfacing with C++, and I'm sure they've not met D yet, but I'm sure if they meet D, they would stop what they're doing and come and do what D is doing. So this approach is very simple, basically matching the C++ name mangling convention and also matching the function calling convention on the registers and the stacks, and also matching the virtual function table layout for single inheritance. So basically, those are the things you should look at when you're interfacing with C++ code from D, and you should, okay, at some point you're writing wrappers, but that will be very minute, not very deep as compared to what the other languages do. So I used to read a lot on the forums and the Discord. People really get confused about how C++ interop goes on, and I decided to use this to give a brief of how to understand what is going on behind the hood, what's going on under the hood when you're interfacing with C++. So let's take an example of a simple program you are running. Your compiler compiles your code, and then in terms of memory, your stack starts and your functions are being called on the stack. And if there is need for heap allocations, all those things goes on. And then your compiler generates assembly instructions, which is understood by your CPU, and which is based on the instruction set architecture of your hardware you are using. And then the instructions go through the fetch, decode, execute cycle until the instructions are all executed. So basically, when you want to start C++ interop, I know a lot of people know C++, but if you depend on your C++ strength, you are going to fail with C++ interop. You should take your mind on D. So when you are doing C++ interop, you should always think D. Follow D rules, and I'm not trying to disobey D. If you try to think C++ all the time, you're not going to get it right. You're always going to struggle with C++ interop. So the backbone of the interop is the semantic analysis phase of the compiler. Any C++ D interoperable routine must semantically agree. So basically, as I showed you here, that this approach is mostly matching the name mangling convention. So they have the semantics of whatever is going on C++ has to be the same on whatever is going on D before they can correctly communicate. If what's going on C++ is a little bit different semantically from what you are doing on D side, and you try to interoperate with them, it's not going to work. You are going to face a lot of issues, and so basically, I'm giving a short recap of the C++ libraries, how most of them are designed. Majority of the C++ libraries are implemented with classes, and C++ classes are value types. They are not reference type by default. And D classes are reference types, but D structs are value types. So basically, if we want our libraries to be able to work in D, we should make sure that they semantically agree. And since D structs are value types and C++ classes are also value types, that's the best pair to work with. So when you are using your C++ class, always use your D struct. As I said, think D. So since D, you want value types in D, so use your struct and try to do your communication with your C++ class, and it's going to work very fine. It's going to work very fine. So then you should know your D struct. And there's a lot of, when you're working with structs, I know D structs and D classes, there are some, okay, maybe difference. The difference is maybe wide, maybe not wide. I'm not really, I haven't really used C++ classes. Most of the time it's D structs I use, but if you try to use D classes, it's not going to work because you like to copy. You like to make copies of your struct and all these things, and D classes is not going to give you that edge. So some few things you should notice from your D struct is when you are starting with your D struct, you should always be aware of the runtime you are using. As I said initially, I was trying to run G++ compiled code on Windows to link, but before I realized it has a different ABI, so if you are trying to use it on Windows, and I was also trying to import it from D runtime, which is distributed compiled, so the mangling of the interface was looking for MSVC compile library, but I was linking it with G++, which is not also going to work. So you'll be getting undefined references. So when you want to use your the default constructor from D, MSVC allocates on default initialization in debug mode, which you cannot do in D, which you cannot realize in D, especially on Windows. But on Linux and Mac, maybe you can get your way around it. But particularly on Windows, it's not good to do that. So to be safe and free, just disable this. But you can use other constructors, like the copy constructors. You can also pass normal constructors, operator overloads, they all work. And your destructors to work here. The destructors to also work. You can interface, you can call C++ destructors on your stack frame from your main function call. And but maybe you need a few wrappers somewhere. You know, C++ accepts our value arguments to const reference parameters, but D doesn't. So per what I know, you cannot, if you have a function like this, let's say if you have a function like this in C++, void full const int reference A, you can call it using, you can just pass an R value of 5 or 6 without looking for a value that has a place in memory. And I know C++ is going to accept it to work, but D doesn't accept it. So the most pragmatic solution is to write the same function, but by passing a const value as a parameter to your D function and forwarding the C++ function which you have interfaced to C++. So, and then now the value parameter will now have a place in memory, and you can pass it to your extend C++ function, which constref would need, because constref would need a variable that has a place in memory. And so using this approach, you can easily call your C++. So if you call this function is also going to call this function, and in the end, you are going to get your C++ function working in D, basically. So move constructors. I know move constructors do not currently work. You cannot call move constructors in D because D hasn't so found a way to do it. But if there's a need for internal move operations, I know I tried once with the STD move in Phobos, and it worked for simple internal move operations. It does copy with very fundamental types, very small types, copies that are not expensive, like ints. Copying 4 bytes on your from your memory is not very expensive as compared to copying huge structs and huge classes. So if there's any internal move operations, you are fine to use the STD move, but calling the move constructor in this still doesn't work. So this is an update. So let's have a look at a simple work here. So this is a class, a C++ class, which has a pointer member field and all in a public scope. And there's a constructor that passes a simple integer and 2 integers and a destructor. So the first constructor allocates on the heap and assigns the value of the arguments passed to the constructor, and maybe print a simple allocating memory. And then the second constructor does not allocate on the heap, it just runs, And then the destructor destroys your resources allocated from your heap. So this is a simple C++ function, and we are about to see what actually goes on under the hood when you're interfacing with C++. So this is a simple destruct, and as I said, you need a class to extract pair before you can get it to work. And you need this, as I said, the constructors work, and the destructors also work. So you interface it directly like this. You call this to your ints, your 2 ints, and then your destructor, and then you call your object on your main stack, and now you first compile your C++ code. So this was done on Linux. I didn't write it. So this was done on Linux x86-64 architecture, and so you compile your C++ code with GCC, and then you try to link it with your D code, which is your U. So your stack frame will be starting from the D main. There's no main function in the C++, and it's a single stack. So when there's a need for a D function, it's going to call the D function on the stack. And when there's a need for a C++ function, it's going to call the C++ function on the stack. And so okay, so this is a function I was testing, right? So I'm calling this constructor, which is the first one, the one with a single integer parameter. And when I'm running it, I'm getting a segmentation fault. Why am I getting a seg fault? Because it's just supposed to run. Why am I getting a seg fault? Okay, let's go back to it. So, okay, this is the function, and the function allocates. It has some heap allocations in the functions, and maybe do you think that would be the reason for the seg fault? I'm not sure. Okay, so now let's see what is actually going on. Why we have our seg fault? So this is the stack frame for the D's main function, and we know that the D's main function has an object, and that object has a size of 1 byte. And so you realize that it calls meme set and allocates 1 byte, offsets the base pointer on the stack, and allocates the address to the RDI. That is, it loads an effective address of 1 byte. The address in 1 byte offsets the base pointer and loads the value and loads the address into RDI. And let's look at our C++ core stack for our int constructor. And we realize here that our C++ constructor is trying to move the value stored in 8 bytes offsets the base pointer into RAX register for whatever arithmetic operation it wants to use it for. And then it's later also moving the RAX. It's later also moving RAX into the memory into the 24 bytes offsets the base pointer. If I was supposed to, okay, so this is it. So the difference here, C++ is moving the value which is found in the memory 8 bytes offsets your base pointer into RAX, and then D is loading 1 byte of memory, the address of 1 byte of memory offsets your base pointer into RDI for whatever operation it wants to use it for. And let's trace our stack, and you realize that the issue was when it was trying to move the value, which is in the memory address, offsets the base pointer to EAX. In the executable, it was having an bad access, meaning that the memory wasn't there, and it was trying to access the memory. It was trying to access the memory which is not there. And what would be the simple cause of this? This is because the core stack started from D's main, and D's main, when D's main was trying to allocate, when D's main was trying to put OBJ on the stack, it allocated it just 1 byte of the base pointer. And now C++ is coming into the stack with a function, and C++ wants that same byte offsets the base pointer. C++ wants 8 bytes, but D has allocated just 1 and has loaded it into the, D has allocated just 1 byte, and and yeah, into the RDI, and C++ is coming into the core stack, and C++ wants to access 8 bytes of the base, offset the base pointer into REX, and since D is the one calling C++, C++ is acting more like a visitor coming into D stack, and D is like, hey, I have just 1 byte. So offset our base pointer, and C++ wants 8 bytes. And since C++ wants 8 bytes, where is it? So since C++ wants 8 bytes, it is not going to allow it to access that memory because that memory is not there. And the stack, which the stack started from the main function, and then the constructor function we were calling was about to run on the next function downwards onto that same stack. And so that memory offsets the base pointer is not there. So C++ will not be allowed to access that memory. And so we are getting a sec fault. So let's look at the next function, the next constructor. The next constructor has 2 integer parameters, and so we pass 5 and 9 arguments to it, and then our OBJ is loaded onto our stack. And then we link and execute, and we are getting an execution success. It is running. The first one, we are getting a sec fault, but it is the same struct, it is the same class, it is the same, but we are getting a sec fault this time. And you realize that, where is it? Okay, so here, you realize that this function also loads 1 byte, offsets the base pointer into RDI, and then it moves the 5 and 9 arguments onto your source and destination registers, and then it calls the constructor onto the stack. And then you realize that when it was calling it, it was move it, here, C++ did not ask for a space the base pointer to move it to REX. If you look at it, C++ is not moving any value from the address offset the base pointer to any REX register. But when you go back to here, you realize that C++ is asking us for a memory into REX, just right on top of the 8 bytes spill. It is asking us a memory of 8 bytes into the REX, but when you come to this side, it is not asking us. There's no instruction of a move of a move offsets the base pointer to REX. And so since there is no request for that, there's not going to be a bad access fault, and so your program is going to run smoothly. So this is why, so what are some of the takeaways we can take from here is that this is why you can pass, if your C++ struct has 2 pointers and you want to pass 8 characters, which in the end is going to give you 8. You want to pass 16 characters, which in the end is going to give you 16 bytes, and you are going to get 16 bytes from C++ class, you are fine, because it's mainly a memory access routine, and so you don't have to care about anything. It's mainly a memory access routine. So if your C++ class has, let's say, 3 pointers, which is 24 bytes, and your D struct has, let's say, 2 pointers and has 8 characters, once it wants to access that memory region and your D function has loaded 24 bytes, offsets the base pointer, you are free, because it's going to have that memory to do whatever it wants to do. So this is why you can pass 2 member pointers, and D can pass 4 integers, or it's going to be 16 bytes, and still get interoperable results. And it's mainly a memory passing routine, and that should be the most factored. So basically, that should be the main priority. Yeah. But there are some trade-offs when it comes to thinking like this. So always make room for whatever C++ wants to come and do in the core stack. if C++ wants to come and sit down, make sure you give C++ a chair. If C++ wants to come and eat, make sure you provide food for C++, because if it wants to eat and there's no food allocated in D, it will try to take something which is not there, or maybe steal your food away or something from your house. So basically, make sure when C++ is coming, you have food for C. If C++ is hungry, you have food for C++. If C++ wants to drink water, you have water for C++ in your call stack, because it is the same call stack. That function is going to be loaded downwards. And wherever your base pointer is pointing to, that's the same base pointer address is going to use. Wherever your stack pointer is pointing to, that is where that same stack pointer is going to be subtracted down to get a new space to operate. So it comes with a trade-off, safety. Some of the C++ libraries are very fond of not emitting their distractors, like especially on Linux. Clang compiler on Linux, yeah, most of them have a design that they will default their distractors from the base class, which is using getting your whatever container or library they are using, and then they have a way of using abstract classes and destroying the resources from the abstract class and not destroying them in the base class. And so you go and see the distractor defaulted in the base class, and you emit your symbols, and you go and you're not seeing any distractor. So what is the state of RAI in the when C++ allocated heap is involved? Like as I was saying, some C++ libraries do not emit their distractors in their symbol table, and some of these libraries allocate on initialization. So you have your heap memory, you have some resources there, and when your stack is being cleared, you still have some memory in your heap, and it exposes your code. It makes your code very vulnerable to whatever attacks it wants to. So, but in C++, they have their way of using RAI to destroy their resources allocated on the heap. But what happens to it on D? I know structs, you can either use destroy on D struct, or when your struct has ended its lifetime, I know that the distractor is called internally in D. So let's find out. Okay, so this is a simple C++ class. Okay, this is the same one with a distractor commented out. And then I call the first constructor, which allocates memory. And then and with the second one, and I've cleared the distractor. So now there is no distractor. So we are assuming the C++ distractor is not emitting its symbol. And then I have my extend C++ struct. And here I decide to include my field with the pointer, because C++ class also has a member pointer to it. So let's say I call the second constructor, the second function, and then I pass a 5 and 9 argument to it. I try to run it. And note this test is for Linux, most reliably on Linux. And then LDC2, and then I compile my C++ library into object files, and I link it. And then I enable my address sanitizer, and now I execute D, and obviously you are going to have 4 bytes leaked in memory because I allocated an integer. I assigned an integer to my memory allocated on the heap, so we are definitely going to have 4 bytes leaked in one allocation. And so now let's call destroy on our struct without reinitialization. Can someone tell me what do you think will happen with this? Would the heap be destroyed? Why don't you think so? Because destroy is going to how is it? The memory address, which is going to be held by the pointer, by the C++ pointer on the heap, when you are calling it from the stack, that's memory address. That pointer will try to come and access the memory in which this P lies below the stack, below the base pointer, offsets the base pointer, and so so definitely, even if you call destroy on your these tracts, you are still going to get your 4 bytes leaked in your allocations. And so what could be the best solution for this? So I'll come to this at the end of my talk. So let's go to the C++ STO. So there are, when you want to use the C++ STO from D, you can either think of looking at the code implementation and re-implementing everything from scratch in D, or interfacing it and using it from D. But each of them has their own problems. If you are re-implementing, you are not going to get a lot of it, and you are not actually going to get what it's actually doing. You would have to take away with a lot of things because D does not agree with some things on C++ and a whole lot. But if you are interfacing it from D, you want to use it, you want to get its full function, what it's designed to do in C++, and you want to get 100% of it in D, then you should be ready for some troubles. And that's what we're about to look at right now. So our runtimes here, Linux is your best friend, Ubuntu is your best friend. When you're linking with GCC compiled binary, you get most of your symbols you desire, and the symbols are easily linkable, and interfacing is quite easy due to the simplified CXX Titanium ABI, and it's not very complex. So if you're on Linux and you just compile your library, you check your symbols, you can get maybe 90%, 80% of it, and maybe you add a few implementations, you are good to go. And then Linux might betray you a little, especially when we clan compiled binaries. When the libc libraries do not like to handle the allocation with the base class destructor, then they default the base struct and go and destroy the resources in an abstract class, which is used to derive the base class. And so if you do not keep very tight track of those, you are going to leave your code vulnerable to leaks. And Windows is that one friend who decides to be good to you, who decides when to be good to you. Yeah, Visual C++ Mangling scheme is very complex, and you can find it very difficult to even call a single C++ function on Windows for just because of maybe a public or a private you didn't declare, or maybe a class or extract, or maybe maybe the layout of your symbol when you're trying to interface it, because it uses, if I try to explain the Visual C++ Mangling, I'm not sure I'll get time to finish my talk. But there are some few trace points when finding it hard to debug your symbols interfacing. So look out for access modifiers. Visual C++ mangles private fields and public fields differently. So if you create a simple class and a simple class in C++, and let's say int a, let's say void full in, let's say, class A, and the class is private by default in a C++ class, it is going to mangle it differently. If you declare public to it and you try to call with the same interface you are using, it's not going to work because the Visual C++ mangling is going to mangle it differently. So you'd have to use an extent. So you have to use an extend C++. If it's a class, you're taking it from extend C++ class, and if basically that. So if you are especially on Windows, if you are trying to call a C++ class, make sure you use the extend C++ comma class. I'm sure it'll be on the spec. I think I added it, but I don't know where it is. Sorry. So, and around time, macOS is your worst enemy. When we started the project, we were testing with macOS 11, 12. Yeah, it was 11 and 12, and you would spend time and you would maybe call a lot of your symbols and maybe get few not emitted and you re-implement them in D, and it will work fine. And immediately you add macOS 12, your code start breaking, and you go and check, and macOS 12 emits some functions as local text symbols, and hence not linkable. So there's the function that you were getting on 11, right now you're not getting them on 12, and now you have to maybe go and implement them. And even sometimes the ones you already implemented on 11 even breaks, because I don't know, I'm still researching into it to find out why, but I personally myself, I don't know why. So maybe if someone can volunteer to explain to me, but sometimes you will get your function which is working on macOS 11, which you re-implemented from D, breaking, and sometimes function which you get a symbol very right and it breaks, and then you re-implement them again, and then now you go to macOS 13, another devil, and then you go and the function that was not global in macOS 12 will now become global in macOS 13, and then another function that was global in macOS 12 will not even be emitted at all. And so you realize that all your work you did with macOS 11 is now waste, and you have to go back again and then go and redo everything again. And with macOS 14, doesn't really care about you. macOS 14 just doesn't care. It emits what it wants and what it doesn't. It can decide not to even emit at all. macOS 14, you can even, maybe for a particular library, you can even on your own written library, you can get very different functions being emitted for symbols which you can easily pick on macOS 13 or macOS 12. And so if you are using macOS, you should maybe be very, 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 should I say, be very, 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 very alert when you're using macOS to interface with C++. It's a very stressful journey using macOS, so it's very. So currently the work done, initially we moved core.scdcpp from D runtime, and now we've separated it into its own package. So you can look it up in GitHub on the DLang repository, scdcpp DLang repository, and it's currently managed in that package. And the containers are worked on vectors, list, and set. SCD set only works on Linux and string. So, and these are our terror runtimes which target, but we will still be going on to maybe BSD and other runtimes in the future. So your primary C++ compiler targets should be on Windows. You should target Clang and MSVC, on macOS Clang, and on Linux Clang and GCC. And so testing. Oh, I just think for you. So, so when you are testing, every library, every container has its own size. So we cannot be always doing the hard coding to maybe verify it from C++ and be like, okay, it has 12 bytes in C++, so we are set to check if it has 12 bytes. And then the capacity is also different as compared to, even on different runtimes, you can get it on. And I think vectors is 24 bytes on Windows, and it's like 16 bytes on, I've forgotten, but the sizes differ on each runtime. So the best is you hacking your C++ compiler which you are using to actually give you whatever size or capacity to to use, which is a very modest way of getting this simple test done. And so with templates, because the STLs are template libraries, you should have a C++ file that has your C++ templates instantiations, and this should basically, maybe for a list, if you want a type int, you should get your template class std list int. If you want a character, you should get your template class std char, and it's going to emit all the symbols for you, and you follow up to link to it, basically. And so, and this also is a test of the size of every container. So for string, for list, for vector, and for set. And then when you compile this and you link it to your code, your interface code in D, you are going to actually get your C++ function running in your stack, which was called from D. So, and so if you want to have a standalone C++ file which has all our instantiations, we can actually instantiate our template classes for all fundamental types, for character, for ints, for doubles, for floats, for all the fundamental types we have in D, so that if you are using your instantiations and maybe you have to assign a vector to, let's say, a float, it's not now that you are going to a C++ file to go and instantiate. Maybe you have it somewhere you can easily link to. And so, okay, oh, I think I doubled the slide. Okay, so the types are not only fundamental. So you can actually pass. You can have a vector of struct, a vector of classes. It's not only vector of int. So how are you also going to do that one? Are you all the time going to? There are a lot of names you can have for your aggregates. You can call any name to a vector. It's not like an int, an int, an int. You can call any name, and the C++ compiler uses the name of the struct during mangling. So if we want to have let's say a file that is going to generate your C++ libraries for you, and let's say you have a struct A, and you want to use your struct A in D for, let's say, vector, and you want to call it from C++, basically you need your struct A template class std vector A, and then you compile to give you your C++ code, your symbols, which you can link to. And should we be doing this for every single aggregate? If you are writing million lines of code and you have like 100 structs, and you want to maybe get your symbols for your struct, and all the time, are you supposed to be doing this? Because there are infinite number of possible names for your aggregates. No. So I wrote a simple program in D which aids in emitting your symbol for you. So I'll be doing a short demo here so you can see. Let me use the screen here. So I copied the instantiations here, and then I had a way of the program generating your symbols, maybe either basically from your aggregates and loading it here, and then that same program or that same process, starting another process by compiling this code for you to get your object file in whatever code you are using. So maybe in the future I will see how we integrate it very well, but I've still not gotten a better name for the program, but I've called it Mango CPP. And so let's say if you are working with vector and you are passing a struct to your vector class, and then you want to get your symbols, you can basically just do a symbol like Mango CPP. And then since it's a vector, the switches I was using were more like, you could get a VC, a VS, so a VC for a vector class, a VS for a vector struct, an ls for a list struct, an lc for a list class, and a set c for a set class, and a set s for a set struct. So let's say when you're having, let's say, a vector of struct A, you can just call it like this: VC, a VS, which is a vector of struct A, equals A. Right? So this is a simple program you can use, and when you run it, you realize that, oops, sorry, I need to type it. VS equals A. Okay, so when you run your program like this, Mango CPP, that's VS, so meaning for a vector struct of A, you get your struct A and your template struct SCD vector appended into your TPP file, and then the process runs it to produce your object file, your test.o object file, and then you can easily link it to whatever code you have. So I thought this is a program that we can use for interfacing with our C++ libraries that are included with aggregates and not only fundamental types. Thank you.
All right, question time. Who's got a hand up?
So the mangling on macOS, is it the Apple client compiler that does that? Completely different, or the symbols on macOS? Did you check using the stock?
It was one compiler, the single Clang compiler, which was, and I tried it for different versions of Clang, and it's still the same. It's like OS 14 is different, OS 13 is different, 12 is different, 11 is different. So,
would it help to use GCC on macOS or not?
GCC, I haven't tried it, but maybe I'll try it and see.
Okay.
Hello.
Hi.
So I've probably done more work on this than anyone. Firstly, congratulations for jumping in on this. This is a ridiculously dense woods full of bears and terrible creatures, and it seems like you just jumped straight in the deep end. So good work. I hope you keep it up.
Thank
you. I was trying to keep a mental track of a whole lot of details through there, but there was so much to talk about. So I think really we just need to sit down and have a really long talk. Yeah, I don't think anything else I can say right here, right now is going to add value for the listeners, but there's a lot to work through there.
Okay.
I think a lot of what you're running into is the result of inlining on the C++ side, and therefore symbols not appearing to link to, and so mangling stuff is almost all compiler bugs, and they just need to be fixed. You showed a whole chunk of what appeared to be an ABI mismatch that could just be bugs, or it could have been some sort of a declaration failure. I'd like to see your specific test case, and we just should sit down and workshop some of this stuff.
Okay.
Cool, thank you so much.
No problem.
Any more hands? It's nothing on the internet, so it's all hands. Who's got a hand? Now you all have hands. Here we go. Walter's got one up. That's what I want to see.
Well, for first project, you sure picked a tough one. I admire your courage in tackling this. So, I just think you're doing a great job.
All right, words of encouragement. Well, if we're not going to have questions, I think words of encouragement are even better than questions there. So thank you again. All right, we have, look at the clock, we got 10 minutes until the last talk of the day, so get ready. It's a good one.
Apparently, since the cord's short, but such is life. That might. Well, okay. Someone else can try it. I mean, if it works, it works. But if I try it down there, it's gonna yank out or something. So. It'll work, I think. I'll live. Yeah, well then I'm probably gonna get shocked because it will take a miracle not to run over time.
Outside.
was here last year. Maybe he was working.
All it does is prevent you from transferring it out twice.
He's still what?
Is he still at Mercedes?
As far as I know, but I haven't heard. Last time I would have heard from him was like last DConf, so.
Are you awake?
No.
You better be awake, because you're going to need to be for this talk. Look who's up here. It's Jonathan. He's got a subject that everybody's going to have questions about. It's Phobos 3, and it's reworking the range API for it. So please take it away.
Okie doke. Oh, there we go. Sound is working. Okie doke. Range API is heavily used in Phobos v2. And in general, this has worked out extremely well for us. And we want to build on that with Phobos v3. We don't want to go and completely change what we're doing. We want to build on what we've been doing and just make it better. But there are some issues that we found over time that we haven't been able to fix with the current range API because making the changes would break people's code. So given that we are now doing a new set of modules with Phobos v3, we have an opportunity to change the API, so we are changing the API. But this is very much an iterative change. It is not a completely drastic rework where we're changing all the paradigms and whatnot. There are some people who want that, but that's not what we're electing to do. So hopefully by the end of this, with Phobos v3, the ranges will be quite similar to what you have in Phobos v2, just with some improvements. Just a quick overview in terms of what ranges are. They're essentially D's answer to C++ iterators, where C++ iterators point at a single element and are effectively an abstraction for pointers. These ranges point at a list or sequence of elements and are treated more like an abstraction for dynamic arrays, or or slices. And they are then categorized. They have multiple categories of ranges similar to C++ iterators, and the most featureful version would be random access ranges, and those are just pretty much outright an abstraction for dynamic arrays and have pretty much all the same functionality as a dynamic array, except that they have none of the appending or allocation stuff going on. It just has the capability to look at the index into the range to see all the various elements and shrink it to iterate through it, just like you can do with a dynamic array. And of course, dynamic arrays are random access ranges. Whereas you go down the layer with bidirectional ranges, they lose the ability to be iterated in the middle. You can't index them in any way, shape, or form. More like, for instance, if you had a linked list and you got a range over the linked list, then you might have bidirectional range to be able to access the front and the back of the range, but you have no ability to access in the middle because it can't be done efficiently. Similarly, forward ranges lose the ability to be accessed at the back end. They can only be accessed at the front end. And then basic input ranges, like forward ranges, can only be accessed for the front, but the key difference is that there is a way to get an independent copy of a forward range to be able to then iterate separately, so effectively you can iterate through ranges multiple times with a forward range, whereas the basic input range has no capability to get an independent copy, so you can only iterate through it once and only once. So just in terms of the basic API as it stands, basic input range has empty, and all the others have empty front and pop front, where empty tells you that there are no more elements. Front gives the current element, assuming the range is not empty, and pop front pops that element off to go to the next element. So this gives you the basic iteration capabilities. Save then returns the exact same range type that you're already dealing with, but that range then is an independent copy of the range you're dealing with so that you can iterate through them independently. But they then have the same elements in the same order, and this is then useful for all the ranges that need, all the algorithms that need to iterate through ranges multiple times. Whereas with bidirectional ranges, they can get pop and pop back, or back and pop back, which are then just the back end version of the front ones. And random access ranges give you the ability to index arbitrarily in the range, and length comes with that because you need to know where the end of the thing is to index it properly. For any generic API, particularly deal with templates, there are some things that you can check statically, and some things you can't. Ideally, everything would be statically checked and you get a compiler error when you screwed it up, but such is not life. I had a coworker at one point who seemed to think for some reason if you compiled Java, it was guaranteed to not have any bugs if you compiled it correctly. I had no clue why he thought that, but that's not the world we live in, unfortunately. So, some of the things can be statically checked with the range APIs. It checks that a range has front, pop, front, and empty. Checks their signatures to make sure, for instance, empty returns bool and not some random foo or something. And with the bidirectional range, it makes sure that front and back return the same type, or with the random access range, that op index returns the same type. You can't have different types from each of those because it's one element type for the range. Or random access ranges with length has to be size t, could be a function, could be a variable, but is random access range can actually check that, giving an error if you don't provide length. On the other hand, there are things that are behavioral requirements that if you don't implement and implement correctly, algorithms are not going to behave properly with your range, but we can't actually statically check it. For instance, front has to return the same value every time that it's called until you call pop front. If it changes for whatever reason, there are various algorithms that are going to break. Some will work because they only call front once, but others call front multiple times, and you will get fun bugs if you implement a range that for some reason returns different values for front before pop front is called. Similarly, if you're dealing with independent copies of the range, so you called save, the result is required to be a range with the same elements in the same order so that you can iterate through either one and get the same stuff. Can't be different. As well, another thing that I think sometimes is forgotten is that all the range API functions have to have an algorithm complexity of O of 1. The various algorithms in Phobos have complexity guarantees. They're not always listed, but if you have any algorithm, you want to be able to rely on the algorithm complexity, you have to be able to rely on the algorithm complexity of each of the operations that it's using. And for ranges, those all have to be O of 1. So for instance, if you have a range that it can only be accessed in O of 1 and to get at the fifth element, because you have to pop through each of them, it's inappropriate to give it the random access range API because it's not going to be O of 1, it's going to be inefficient, and when you use it with various algorithms, while it might actually work, the performance is going to suck. But those are things that you can't actually check with template constraints, but they're still required. Most of the problems with the current range API can be grouped into one of three categories. Auto-decoding is an issue. The fact that we have save and need to use it has proven to be an issue. And there are a number of items, I think they often aren't even thought about, which are behaviors that are underspecified or actually cannot be specified because of the variety of types that we allow to be ranges as things stand. And these sometimes cause problems because the generic code cannot rely on the behavior when it's implementation dependent. There are some things that are inevitably going to be implementation dependent, but anything we can actually nail down with the API requirements then makes it so the generic code can rely on those behaviors and what it's doing, and you can do more. Auto-decoding would honestly take too long to actually properly explain because Unicode is stupidly complicated. But essentially, what it's trying to do is ensure Unicode correctness by default so that you don't have to worry about all the complications of Unicode. Your code is just Unicode correct and it works. And functionally what this means is that arrays of char and wchar are treated as ranges of dchar. So char is UTF-8, wchar is UTF-16, dchar is UTF-32. They're all different encodings of Unicode code points. And UTF-32, each element is guaranteed to be a full code point. That is not the case with char or wchar, because UTF-8 and UTF-16 are variable length encodings. So it's very easy to write code in general, which is dealing with ASCII, which works perfectly fine. It's accessing stuff in the middle of your string, and then you get some actual Unicode characters, and you're chopping into the middle of code points and dealing with garbage. And so in an attempt to solve this problem, the range API on arrays of char wchar decodes the code point from the beginning of the range and returns that from the beginning of the range and returns that. And that's then what you get. So you end up with elements of dchar, even though that's not the actual element type of the array. This was a noble goal, but in reality it doesn't work, in part because code points aren't actually guaranteed to be characters, even though apparently the Unicode spec, as I recall, sometimes uses the term character for them, which is arguably stupid, but Unicode is complicated. And so ultimately, auto-decoding has failed, primarily because it doesn't actually give you correctness by default. If you want full correct Unicode, you have to learn a bunch of extra junk and do that correctly in order to have your code work correctly with Unicode, and auto-decoding does not help you with that, really. In fact, it makes life worse because you don't necessarily want to be doing the decoding in a lot of cases, and it becomes an efficiency problem. So anyone who actually knows what they're doing doesn't want auto-decoding, and the people who don't want to bother with the problem and just have it automatically solved for them don't have it automatically solved for them because auto-decoding only deals with code points. And this has complicated Phobos considerably, because of all the code that attempts to work around the problem to deal with efficiency issues, and it partially manages to do so, but it's just a complex mess, and we'd rather simplify things that will inevitably introduce more bugs in some people's code when they do things like do random access on an array of char, but we can't really prevent that ultimately in the current situation. Just partially fixes some of those issues. But the only real benefit, I think, ultimately of auto-decoding is because it's kind of in your face. It's resulted in a lot of people being forced to learn a bit more about Unicode and go and figure out how that actually works so they can do what they're going to do. But we don't want auto-decoding ultimately. It has caused too many problems. Save has also caused problems. It's required to get an independent copy of a forward range, largely because of classes. Because if you have a dynamic array and you copy it, then you're guaranteed that you're getting an independent copy with regard to the iteration state. Dynamic arrays are pseudo-reference types, so you don't actually copy all the elements. You just end up with a slice of the same memory. But each array can be iterated independently, and so there's technically no need for a function like save. You can just pass them around and copy them. Each one's going to be independent. The same is true for a lot of structs. But for classes, they're reference types. And so if you just copy them around, you're going to end up with no independent copies whatsoever. They're just going to be fully dependent copies, and you're going to have bugs. However, because the vast majority of ranges do give you independent copies when you copy them, you end up with bugs in programs because people forget to call save. And even if you test your code thoroughly, this is easily missed because you have to make sure you test it with the correct types that would catch this particular problem. So ideally, we just wouldn't need save, and we could just have the same copying behavior you get with dynamic arrays, so the problem's just not a thing. And just generally speaking with copy semantics, with the way range API is currently done, we can't rely on them in any way, shape, or form, because you have 4 variations of copy semantics right now, depending on how the range is implemented. You have value semantics, in which case you're getting a full copy of all the elements, and so the copy is clearly independent. You got a reference type, at which point you're just dealing with a class or a pointer, and it's fully dependent when you make a copy. Or you got a pseudo-reference type where the iteration state essentially has value semantics, but the elements themselves aren't necessarily copied, and that's what you get with the dynamic array. So you end up with independent copies as far as the iteration state goes, but you're not actually copying all the elements. And then the nasty one is the pseudo-reference types, where their iteration state doesn't get fully copied. And so you end up essentially with a partial copy, where like some part of the struct is value type and some part is a reference type. This happens particularly with basic import ranges where they've stored front, and yet they have a pointer to something else to give them their iteration state. So if you make a copy, you're getting a value copy of front, but a reference copy of the rest, and that just causes issues. So just some simple examples on that. If you copy a range and you pop off an element from the original range, the state of copy is unknown at this point, because depending on the semantics, you could have ended up with an independent copy, or you could have ended up with a complete dependent copy, or you could even be in a state where it's now the copy is actually in an invalid state because you popped something off of the original one instead of the copy. And if you pop it off of the copy instead, you're in basically the same boat. It's just the original range, which is screwed up, potentially. This means that in generic code, when you copy a range, you basically have to treat the copy as invalid and never touch it again, which can cause issues. And there are people that are going to forget that some of the time because, like with the dynamic array, it's a non-issue. But there are ranges where it's a serious issue. And to work around this problem, of course, forward ranges have save, so you can explicitly get an independent copy. But this doesn't entirely work around the problem, since there are plenty of other cases where you copy a range and you're not even thinking about it. One case is for each, and this particular problem came up in the news group recently, where someone wanted to iterate a range with for each, and then at some point during the iteration, they wanted to break out a loop and then continue iterating the range afterwards. And while this will work with certain ranges, in generic code, this will not work. And if you look at the lowering, that helps explain why, and that the range is copied when you iterate with for each. And so you're iterating through the copy. And so again, we have the problem because the copy semantics aren't defined. The state of the range after for each is going to vary wildly depending on the implementation of the range. Of course, the reason it is copied is to emulate the dynamic array semantics, since I believe that gets lowered to a 4 with indices to access everything. But the result is that when you iterate a range with iterate an array with for each, you don't consume it, you just iterate through it. So you don't want to be consuming the range in it's on a dynamic array, so we do a copy. Now it's still going to consume it in the case of a basic input range because you have no choice. And of course you can call save to then get an independent copy. But just overall, you have to avoid doing anything with a copy, with an original once you've made a copy. And this causes issues just because the semantics, again, are inconsistent. And the assignment semantics are basically exactly the same issue. It's just that instead of getting a new variable, you're replacing the state of current variable. And so what you assign from has to be considered invalid in generic code so that you don't have behavior that's only going to work with some range types. Ooh. Another issue is that the init value is poorly defined. The range API really doesn't say anything about it. And because it allows such a range of types, you have wildly different semantics for the init value. Extreme cases, the class is null with init value. So if you try and do anything with it, you get a segfault, your program's dead. This particular example is a reduced one from a bug report from the protobuffer guys because there was a change to Phobos' chain function which broke their code. Because they were making the assumption, which is technically a bug on their part, that the init value for chain was both valid and empty, which was previously true. And this is the kind of thing that a lot of times, if you're not really thinking about it, you're just going to make that assumption because that's the obvious thing. It's how dynamic arrays work as well. However, the implementation of chain was changed in order to try to make it more efficient. That resulted in no longer being the case that it was valid and empty, so their code broke. And current range API just makes no guarantees about the state of init and cannot do so because of such extreme differences in the types that ranges can be. Another issue that pops up occasionally is there is no way with, you have a question? Oh, lovely. That makes things even worse. I mean, it would be nice to be able to make that assumption, but we cannot currently make that assumption. But another thing that pops up occasionally is, in the general case, there's no way to get an empty range of the same type from a range without popping all the elements off, which is now O of 1. If it's sliceable, then you can slice it with 0.0, and you get the same type. But like for forward ranges or bidirectional ranges, you can't do that. So if you have a case where you need to retain the same type, like in this example, you've been passed in a reference to a range, and it makes sense for this code to make it empty. There's no way to say, hey, we want to make this empty now and return, so that when you then look at it afterwards, it's empty. In this case, the code is using the init value, which for many ranges will work, but of course in the general case does not. And there's just no way to do this in the general case. The closest we have is take none, which wraps it to create another range that is then empty, which works for use cases where you don't need to retain the type, but it doesn't work in any case where you need to retain the type. And so this is a hole in implementation that'd be nice to fix. And the main reason it wasn't fixed years ago was because of the init problem. Another thing that pops up is what we call transient front. The prime example of a function that causes this issue is byline in standard I/O. And in the vast majority of ranges, it is perfectly fine to copy front and store it and do other things with it. So you copy front, you call pop front, and your variable stays the same. However, it is technically possible to do things like return a dynamic array that's being used as a buffer, and pop front reuses it to get a new value, which is what byline does. And so that means your copy has now changed. The vast majority of code assumes that this is not a thing. So it routinely causes problems when it is a thing, which is why we added byline copy for the cases where you want to do something other than iterate with for each. But the fact that this is allowed causes problems. Another thing is non-copyable types, which is not strictly a problem with the range API, but it's not something that we generally handle very well, partially because non-copyable types kind of suck, honestly. But there are cases where you need them. And the ranges in the algorithms in general in Phobos don't even think about non-copyable types. They don't test for them. They don't try to work with them, whatnot. And we need to have a more consistent story of what we're doing with non-copyable types. Even more so with some of the changes we're going to be making. Another thing is with random access ranges, for some reason, is random access range doesn't actually check for slicing. Has slicing as a separate attribute, separate trait. As far as I can determine, if you can randomly access a range in O of 1, there is no reason why you can't slice it in O of 1. Similarly, if you can slice it in O of 1, I see no reason why you can't implement op index in O of 1. But has slicing will technically allow you to implement a forward range with slicing. So as far as I can tell, that just makes it so that you cannot bother to implement slicing on a random access range, even though you're probably going to run into cases where you used your range with code that assumed that slicing was a thing for random access ranges and had a bug. Or you just decided to have slicing for some reason in forward range and were too lazy to add op index. I don't know. But as far as I can tell, functionally speaking, there's no reason to be separating these two traits. Just put the slicing on the random access ranges, and that will be one fewer trait that we have to worry about, because we have way too many of those already for all the variations to be worrying about. Another problem, there's another underspecified issue here, is random access range and has slicing don't check for op dollar, because Andre forgot. And the result of this is there is no guarantee that a random access range has implemented op dollar. The result of this is, in turn, that you cannot use op dollar in generic code, because it will not work with ranges that didn't implement op dollar, and there's no guarantee that they did. So ideally, we would just have that requirement so that we could rely on op dollar. In most cases, it's just aliasing links to op dollar and you're done. But that's not required right now, which effectively means indexing and slicing can't use op dollar, even though ideally we would be able to. And just in general, constant ranges don't really mix very well. Constant elements are generally just fine. But of course, pop front doesn't really make sense with const because it's iterating the range, mutating the range to do the iteration. And while this isn't a huge deal with a lot of code, because when you pass around all this templated stuff, there's no requirement to like slap const on things. It's not a big deal. You're not going to end up with the const range in most of that code. As soon as you start dealing with containers and putting ranges within other objects and whatnot, it's pretty easy to get in a situation where you have a const object containing a range that is then const, and the range is then effectively useless. Arrays do not have this problem because they have a bit of compiler magic, where if you slice them, you get a tail const copy, which means that instead of a fully const slice, you then have a mutable slice of const elements. In fact, templates with implicit function template instantiation specifically instantiate with the slice type, not the actual type of the array, which makes it possible to pass like an immutable array to a range-based function, and it just compiles without you having to dupe anything or cast or whatever, or slice it explicitly, because the compiler knows that it can make that conversion safely, and it's going to be sliced when you pass it to a function anyway, unless it's ref. So we ideally would have that kind of capability with ranges in general, but we don't. And the last issue I have here is one that Walter in particular didn't like, and that currently you have to import standard range or standard range primitives in order to treat arrays as ranges. Ranges are not first class in the sense that arrays are treated that way, in spite of the fact that ranges are essentially an abstraction for dynamic arrays, and we use them all over the place. So at least it would be nice if we didn't have to import a module just to be able to use arrays as ranges. Not the end of the world that we can't, but it's annoying. Now, as for changes, top of the list is actually one of the main reasons that Phobos v3 was started in the first place. We want to get rid of auto-decoding. So we're getting rid of auto-decoding. So all arrays of char and all arrays of wchar will be ranges of their actual element type. This means that you won't have the decoding going on automatically, you won't have UTF exceptions potentially being thrown from that, et cetera, et cetera. Now, we already have the functionality in standard UTF to do all this manually. We have decode, we have decode front, we have by UTF, by char, by wchar, et cetera, to allow you to decode UTF 8 and 16 to code points. And we have ranges to then wrap other ranges to give you other versions of UTF. It's just that with auto-decoding, it's done for you automatically, so you have no choice on the matter other than working around the special cases to get around it. And because these various functions give you the choice of whether you want the replacement character or UTF exceptions when you run into invalid Unicode, you have the choice for how you handle it in your program. The other major change is the current plan with Phobos v3 is we're largely going to be dropping anything that isn't UTF-8. You have a question? No, okay. That is, if right now, if you have a function that takes a string, in most cases, we then try to templatize it to have it take a range of dchar, so it can handle all those variations. And with Phobos v3, it would then take a range of char, not wchar, not dchar, but we would have the wrapper so that if you, for whatever reason, have a range of wchar, you can convert it to a range of char and have it do its thing. But that will simplify the code that we won't have to deal with all those different encodings, which will help life. Next thing is a init has to be valid. Well, okay. If the range can be default initialized, then it has to be valid. And if it's a finite range, init then also must be empty, so that, like in the chain case, you can actually rely on that behavior. And if it can't be default initialized, you're going to get an error for trying to use the default initialized one anyway without giving it a value. In the case of infinite ranges, of course, they are going to be infinite, so they can't be empty, so they'll have to be non-empty. But this cleans up the situation with init. It does get a little bit more complicated. I don't really want to take the time to go and do it at the moment with disabling default initialization and how to handle that. At the moment, the current plan is that we're going to have a free function called empty range, which will work with any finite range that can be default initialized, which is probably 99.9999% of them. and that one will then be guaranteed to give you an empty range from the init value that's required to be valid and empty. And in the very rare case where you disable default initialization for some reason in a finite range, you can then, you'll be required at that point to implement empty range yourself so that someone can use that to get the empty range. But much as we'd like to disable default initialization, there are issues with regards to infinite ranges and their state where you can't really force them to have a valid init state when it actually needs runtime information because they can't give you a valid state without that runtime initialization, so the init value is just not going to work. We would need default constructors or something to handle that in all likelihood. But we don't have those. Now, to try and fix a number of these issues, particularly with regards to copy and assignment semantics, major change here is that ranges must be dynamic arrays or structs. A pointer in a class and the like cannot directly be a range. Now, we still want to be able to do all the stuff with classes that we do with standard range interfaces. We don't want to lose that functionality. But we do want to lose the problems with regards to all the inconsistent semantics. So if you're dealing with a pointer, you're dealing with a class, they're going to be wrappers that will then handle that correctly and give them the correct semantics for the struct so that you can rely on the copy semantics. You don't have to worry about whether you're called saved or not. And ultimately, this will then allow us to put requirements on ranges that give us consistent copy and assignment semantics without having a stray function that we all forget to call half the time. And on that note, there will be no save. Instead, copy semantics are required to give you an independent copy. Technically speaking, this is not necessarily identical to save, and that save right then gives you an independent copy. Whereas if you make a copy, in this case, we don't want, like, if you have a class inside that struct, we don't want to be duplicating it all the time necessarily, because that would be wasteful if it turns out that the original isn't around anymore and there's really only one copy. So it would be possible internally to do something like reference counting and look at the state in pop front and say, oh, the reference count is only one. We're not going to bother actually duplicating the state because we know this is the only copy. It's unnecessary, whereas the ref count were 2 or more, we know it's necessary. We're going to duplicate it. So it will be possible, depending on how the ranges are actually implemented, to avoid unnecessary copies. But in terms of usage, once you make a copy at a forward range, it must be an independent copy, and then all range-based code can rely on that behavior. Now, the flip side of this kind of sucks, because what currently defines the difference between a forward range and a basic input range is save. With save gone, there's no longer a difference. However, if something that's a basic input range, it's because it cannot implement the save behavior. You know, there's no way for it to efficiently give you an independent copy. That's why it's a basic input range. So essentially, the fundamental difference between basic input range and a forward range is its copyability. You got a fun question?
I thought the forward ranges had to have a length and input ranges didn't.
Only random access ranges have to have a length. It is possible for other range types to have a length. They're allowed to. It can be checked for.
Range exists without a length.
Well, look at it like a linked list. You don't necessarily know the length of the list.
Okay, yeah. Fair. Okay.
You know, there are plenty of cases where you'll have length when you can have length, and it's going to be on there. There's an option. It's not tied to a particular range type, except for the fact that random access ranges are required to have it, because if you don't have it, you're going to have problems with indexing. But because the fundamental difference between a basic input range and a forward range is the ability to copy its iteration state, the simplest way to then differentiate them and avoid all the bugs from partially copying state is to make it so they are non-copyable. The alternative would be giving it a separate API so that the code would not match up and you wouldn't accidentally use a basic input range as a forward range. Downside is you then have to duplicate all the functions that might work with both, which you don't really want to do. Plus, if you're really going to make them that different, maybe you should just make them a completely different thing and work on some other set of benefits with additional functions or semantics or something that don't necessarily fit in with the rest of the range API. So the decision was to make them non-copyable, which will be annoying in a number of cases, but for the most part, it's going to prevent bugs. This means that most functions that are, well, pretty much any function that's taking a basic input range is then either going to need to take by ref so that it can take the value because it's not copying it, at which point there is no copy where they're doing the basic input range and a forward range, and just the semantics of that function are that it's mutating what you passed in, or you have to do an explicit move to pass it in to that function because it didn't take it by ref, at which point the semantics are essentially going to match what you had the forward range, and that you're passing it a range that function that gets ownership of, and you're not going to be doing anything with it in the function that you passed in. And since you called move, it now has a init value, so you're not going to have funky behavior going on if you screw up and accidentally use it. There are also improvements that are supposed to be coming to language with regards to move constructors and whatnot, including hopefully the ability to make it so that the last use of a variable would automatically become a move, which would reduce how much explicit moving we have to do. So some language improvements here would make this less bad. But most ranges or forward ranges are greater anyway. And while this particular restriction of not being able to copy basic input ranges is annoying, it does fix a whole class of bugs, and it makes the difference between basic input ranges and forward ranges very clear. And as far as assignment semantics go, that pretty much just comes from what you would expect in the copy semantics. It's the same thing. You get an independent copy when you're dealing with forward ranges, and if you're dealing with basic input ranges, then it's going to have to be a move. So if the compiler turns that assignment into a move, then you're fine. Otherwise, you're going to have to do an explicit move to be able to move a basic input range because it can't be copied. As for transient front, we're just going to say, no, you can't do that. There are other ways to get this behavior without altering the return type or the return value after calling pop front. For instance, if you really only care about for each, you can use off-apply. There's no need to use the range API for that, much as it's nice. Alternatively, you could use a non-copyable type, and we are going to make that work better than we have. So if you use a non-copyable type, then they can't copy front, and you can just reuse your buffer as much as you like, knowing no one's screwing with it. Or maybe you could do reference counting. I'm sure there are other solutions that could be used that people come up to work around the problem. But I don't think that there's anything fundamental about transient front that requires that we support it in any way, shape, or form. There are other ways to solve this problem without making things worse for all the other range stuff, having to worry about it. And as for non-copyable elements, it's not really changing the range API, but again, we're going to essentially make it so Phobos 3, any range-based function either has to use a template constraint to reject non-copyable types because it's just not going to work with them, or it has to work with them and is going to be tested with it appropriately. You can test fairly easily whether the element type is copyable already just with __ traits, but we do have a number of traits already for has movable elements to check whether the elements are movable and some things like that. So we may or may not add a specific trait for that, but either way, there's going to be a standard way to test whether the element type is copyable, and that's going to be needed to use in Phobos to ensure that template constraints do their job with regards to that, and that we don't forget that this is a thing. As for tail-const ranges, we're punting. Insofar as this is really a wider problem, it's not just a range problem. And ideally, we would fix the issue in the language itself. Walter currently has a dip that attempts to do this. I haven't looked at it for a little while, so I don't know if it needs work, but it is attempting to make it so that you can then get a tail-const copy of a struct in D so that we can then hopefully emulate the behavior you get with dynamic arrays. I think the one thing it was missing, if I recall, was it didn't do anything with template instantiations, because if it really was going to match that behavior, then you instantiate a template with IFTI, it should use the tail-const version, which I don't think was in there. But either way, current plan is we're going to use dip with the language to fix this, which would also fix it for Phobos v2, which would be nice. But we considered some other API changes to make it more like functional programming with head and tail and things, and it just didn't really clean up the problem. It introduced some other issues, and it would be a much larger change. So we're punting on this one and going to hope that we can get the dip sorted out with this to fix the issue in general. And then the major change which is annoying, but has some, well, we need to do it for a couple of reasons. But we need to change the function names on ranges. The number one reason for this is that if we move these functions, or if we put these functions in object.d, which is the most straightforward way to then make it so that all arrays are ranges by default without importing anything. This causes conflicts with the functions in standard range primitives. And we can't move the functions from standard range primitives into object.d because the ones in standard range primitives have autodecoding. And we need the autodecoding, as terrible as it is, to continue to work in Phobos v2 so we don't break it. So if we were to put the functions with the same names in object.d, then a ton of code would have to break, and they'd have to put a lot of selective imports into code to say, I really wanted the Phobos v2 ones, which are probably going to be forgotten in some cases and get weird behavior. But there's also a compiler bug or design bug. I forget the exact details off the top of my head, but basically using selective imports with range primitives and standard range primitives and standard range for the range functions, if the functions are in object.d, doesn't work. You can't actually fix the conflict, you still get an error. Which, that may or may not be fixable at the language level, but it's just far cleaner if we put a different set of functions in there. There's nothing where you accidentally use one over the other. And so renaming the functions makes it so we can stick them in object.d and make it so you don't have to import something to get them, and it's much cleaner. The other issue is that the old basic input ranges, which don't have save, then look like the new forward ranges, which do have save. And the vast majority of these basic input ranges, of course, are copyable, even though you're not getting an independent copy. And so if we don't change something in the range API, you're going to have basic input ranges passing the template constraints on the new is forward range, and they're going to have incorrect behavior. So we really want to block that. We want that to be a compilation error. And so using new names fixes that issue. It's a different API, even though it's functionally the same in terms of what each of them do. And so that's a little bit annoying, but it also makes it so if you look at the code, you know whether you're dealing with Phobos v2 ranges or Phobos v3 ranges. You don't have to be confused about it. So it should improve usability from that standpoint as well. Now, this does require a dip because of for each, because for each knows about those functions in order to implement for each working with ranges. So I need to go and write that, and hopefully it won't be a big deal, particularly since Walter wanted this anyway. But there are, of course, some details about, like, if someone is stupid and implements front and the new function on there, like, which one do you get? Just like if you implement the range API and op apply at the same time, for each has to decide which one it's actually going to use. The names that I'm planning to go for here is just front's going to become first, pop front's going to become pop first, empty will be is empty, back will become last, and pop back will become pop last. So they're just basic synonyms for what we're already using. Don't think it's particularly confusing, and it's clearly a different API, even though functionally it's the same thing. And so aside from like some behavioral requirements like not having save and whatnot, your range-based code in general is just going to be the same that it was, except with some different names. And there will be fewer bugs related to underspecified parts of the API and the Phobos functions, and other people writing their own functions can rely on the stricter semantics. And in the end, I don't think it's really going to add any restrictions to any user code in terms of what they're doing. It's just going to let you do more stuff because you can rely on more concrete semantics instead of having a lot more of it be unspecified like it currently is. In terms of implementation details, obviously all the traits and basic helper functions we currently have are going to be ported over in one form or another for the new range API. There may or may not be some name changes based on the whole Phobos v3 thing with general name changes depending on what we're doing, or they may be exactly the same depending on what we're talking about. Also, as far as the standard range interfaces go, we're going to be creating wrappers to deal with all that. So you're still going to have a replacement for standard range interfaces. If you need classes that are ranges, you're still going to get all that functionality. It's just they're going to be wrapped in structs, and because those wrappers are provided, you don't have to go implement stuff like the reference counting to deal with avoiding additional copies when you don't want to be copying all that data and don't need to. Similarly, the plan is to create wrappers for ranges to convert between the two APIs. And it's possible to be some caveats on that because the old range API doesn't have the same level of guarantees, and I haven't finished going through all that yet, so I don't know if there's going to be something where I'm going to have to say, okay, this might have this issue. But ideally here, we're just going to create wrappers so that you can have code that gives you a Phobos v2 range that you then pass to your Phobos v3 code, or vice versa, and be able to deal with that so that it just works nicer in general. So obviously, long-term, ideally, things would shift over to the new API. And another big thing is I very much want to supply a lot more test helpers than we currently have, because there are a number of things that we can't statically check. There are actually some things you can't really test with unit tests either, like verifying that the functions O of 1 doesn't really work with unit tests very well unless you're just dealing with huge data. But there are a variety of things with ranges that we can test with unit tests pretty easily. And if we can provide more helpers to test your function, range-based function with a variety of ranges, to test your ranges to make sure that they're behaving properly in a variety of circumstances, then it makes it a lot easier to write tests and make sure your code's working correctly without having to come with all that mess yourself. And you're less likely to run into issues because you forgot about a requirement and didn't implement something correctly. Another big thing is the documentation needs to be improved. I think in general, if you look at like standard algorithm, the documentation of the functions is generally pretty good with some nice examples. But we don't really have any overarching documentation that's particularly good that explains exactly what the deal with range is and how range-based code typically works. And so if you're coming from another language, most of which don't have anything like ranges, you're going to be pretty confused in a lot of cases, and we need to do better about providing an explanation for that so that people then know how to use them. Similarly, we need very clear documentation on the behavioral requirements. We do have some of that documentation right now for the current range API, but there are a number of behaviors that are emergent from what we've done that are not immediately obvious that you might screw up because you don't know about, even though it's a general requirement. We want all those requirements, ideally, to be listed out in a way that if you're implementing a range, you know what the requirements are, and you don't do something like have a copy not be independent for a forward range. You know exactly what the deal with that is. Just clear documentation on how that works, plus the assumptions you can make based on those would ideally be clearly documented as well, so it's easier to write range-based code using ranges and not be doing things that actually you can't do, but you didn't realize that because you didn't know enough about the details. So just overall with the documentation here, I think we need a much better story of explaining the general concepts and exactly how that works so that it's easier both for new users and for people who are looking to implement a lot of this stuff in their own code. Which that gets me to questions, which hopefully aren't too terrible. So,
I'm thinking if you want to port an old range to a new one, can you just use alias? So just say like first equal to front or something. Can you do this? Is it possible?
Can't understand what you're saying, but if in terms of taking a range from the old API to the current API, in many cases, it's going to be as simple as just changing the names. And yes. So, but like if you're then writing a range in your own code, or you're writing code that's using a range, it's going to be fairly straightforward in most cases to just change it to use the new names, and it will work. Just there are certain requirements that you have to be careful of, like if you do the forward range, it's no longer saved, you're going to make sure the copy semantics are correct, whatnot. But for most code, these extra requirements are what it was doing anyway. You just couldn't rely on it because we didn't define it, and there is code that doesn't follow it. So by adding those requirements, we can then rely on it. And for the most part, your range-based code really isn't going to change much other than you're not having to explicitly call save. Basic import ranges will be a bit more annoying because of the non-copyable aspect, but most ranges or forward ranges are greater anyway, and you're going to have to change the names in your code. So not the end of the world, but it's a bit annoying, I'm sure, in some cases, but it's very straightforward because we're looking to have this be essentially the same thing with some fixes, not completely change what it's doing.
The tailcons thing, how is that a generic problem? Because, okay, I can definitely write a range that could take some const elements from another range and then be tailconst. So I don't understand what's the general problem there.
Well, for starters, if you're slicing a range, the requirement is that it has to be the same type. Causes issues otherwise at present. We could potentially say it could be a tailconst type instead. But if you're wrapping enough stuff, you don't have the way to get it. I mean, with dynamic arrays, the compiler is able to look at the type and know exactly what's going on and avoid any funny business. That's not necessarily possible with other types because it's more complex.
Well, it's automatic, but you could write code to do that, right?
In at least some cases.
I mean, if I have a map result of a const map result, I could, get the first element, I don't know, copy that, everything, and have a non-const map result of const.
Yeah, but I mean, if a separate set of functions we have to call essentially to get that, and it complicates things where it's automatic with dynamic arrays. I mean, worst case, we could look later at adding something to do that, but there's already a dip that's trying to fix the problem, and whether the exact dip is what makes it in or not, we should be able to fix the problem with a dip, and then that just solves the issue, and we don't have to further complicate the range API to solve the issue, particularly since it's not something that happens super frequently anyway, and there's already a lot going on with the range API, so if we can avoid adding extra complication, it's better to avoid adding extra complication.
So if I understand correctly, it's basically, let's do some work in the language/compiler so users don't have to write code to make this happen for their own ranges.
Well, with the dip, as far as that goes, if it solves the problem for you, then you don't have to do extra work. So we'll have to see exactly how that comes out, but that would ideally be what we do. The main thing that we're not doing is head and tail kind of functional solution, because that would be too big a change, and it didn't really seem to solve the problem anyway when I looked at the details, because you've got different types changing depending on the constants and all that, and it got ugly.
There's an order, man.
So I had a question about what it means to be independent for ranges. Like slices are copyable, but if you copy a slice, they will refer to the same elements, and you will see this aliasing.
The iteration state is independent.
Okay.
So we're basically trying to copy what happens to dynamic arrays, except there are, of course, value types where they actually copied all the elements. And just there's enough complication with various types that it's rather difficult to go, oh, this has to be a reference to something so that you can mutate it for the same from either. We don't want to say it has to be a copy because that's going to be a decopy of things. That's not how it works with dynamic arrays. So the range API, for the most part, is not really concerning itself with what happens if you assign an element. That is, there are some algorithms that do that, but that is going to be implementation-dependent behavior insofar. I mean, you have has mobile elements you can test to see about moving out the elements, but whether that's then going to affect another copy is then going to depend on the implementation. So you can't really, you pretty much have to assume at that point that the other ones are invalid if you did something like move elements. But as a general rule, they're independent in that the iteration state is independent, and what happens to the actual elements themselves in terms of whether they were copied is implementation dependent. Much as it would be nice to be able to just go, oh, they're like dynamic arrays for everything, there are too many ranges where it's really not going to work to give them that semantics. So I'd like to nail it down more than it is, but for the vast majority of range-based code, you're just reading what's there anyway. You're not mutating, so it doesn't matter.
Yeah, I mean, I guess there is the issue of nested ranges. For example, in Phobos, there's a transpose function that will consume all the inner ranges place. So I guess Phobos v3 is going to keep that weirdness where functions sometimes mutate even though it seems they shouldn't.
Yeah, I mean, I'd have to look at the specific thing to see what we could do with that. That does get uglier. Some of that's getting uglier just with basic input ranges being non-copyable. But you're also naturally going to end up with copies in more cases because of how forward ranges will then work. So there may be some specific cases where we have to look at it and decide how we want to go about it. But in terms of defining what exactly is happening with the elements as to whether they're copied or not, I don't think it is functionally going to work to put a requirement on that because there's too much variation in what we do with ranges to make that work, much as it would be nice to nail that down as well. So this doesn't nail everything down, but it does nail more down.
Yeah, I mean, on that note, another thing that is confusing to me is how you would implement first for a slice type whose elements are non-copyable.
Well, we return it by ref, which you can already do.
So the user has to put something else in slice while iterating.
I mean, dealing with first becomes more complicated in general. When you get the non-copyability, there may be a variety of cases where we're just like, sorry, this isn't going to, non-copyable is still not going to work with this code. But the core thing here is to ensure that we're dealing with non-copyable consistently and improve that story. So there may be some details that we need to tweak to make things work or nail some more things down that I missed. That's certainly possible. I mean, this is based on the issues I'm aware of and what people pointed out in terms of what we're doing with it. It's quite possible there are additional issues that we're going to find going through the process and have to nail something down further. But this is the current plan.
All right, thank you.
All right. Two questions. First of all, oh, sorry, carry on. You go first. Oh, I understand. That makes more sense. Okay. Two questions. First of all, to the extent that this doesn't depend on object.d, are you considering putting it up on dub somewhere so people can test with it?
Well, I couldn't hear what you said.
To the extent that the range rewrite doesn't depend on object.d changes, are you considering putting the parts that are independent of that up on dub somewhere so people can test their software with it?
Oh, you mean put them up somewhere so that people can mess with it? Well, at this point, it would go into the Phobos v3 part. I've partially implemented it. I haven't completed it. There's some other stuff for Phobos v3 with regards to traits I need to finish, import things over. So it's not there yet, but there's a partial implementation. And when it's large enough, it will go into the Phobos repo in the portion that's for Phobos v3, and anyone who wants to mess with it can mess with it at that point.
Got it. Thanks. Also, I'm not 100% sure if this is covered under the changes about tail const, but are you testing with values in ranges that are immutable? So immutable in the sense of immutable struct where you can't uncall it?
Well, immutable and const are basically the same problem at that point. So there shouldn't be a need to test explicitly for anything that's immutable versus const. And most of that stuff with regard to like highest assignable elements, it'll check, whether it's assignable, and it doesn't really matter why it's not assignable. I mean, it could be that you disabled off assign or funky things like that. So a number of the things you don't have to get too specific on it to just test the behavior and you're fine.
That's fair. Thank you.
About the O1 operations that you mentioned.
Yeah.
So in filter, for example, pop front has to be ON, right?
In what?
In filter. When you use filter, a filter result, you kind of have to skip all the elements, right?
Yeah, I guess in that case, it technically...
So that was mostly like a nitpick, but now for my more serious one. When we were sold ranges and the composability of them, we were sold it as this is a really nice, rich, composable API, but it compiles down to extremely efficient code as if you wrote it directly yourself. And over time, we discovered that's not really the case. When you compose op-apply ranges, like ranges that use op-apply, it's actually correct. But when you use front, pop front, and empty and compose things that build on that, you do see a performance hit, and a significant one. And when we investigated why that is, we discovered that it's because if a range implements 3 methods, front, pop, front, and empty, each of those 3 methods is going to call the underlying range, which it composes above, also multiple times. Like front might call both empty and pop front, and not just one method. And the compiler refuses to inline, and for a good reason, because if you try to inline multiple calls to the same underlying range method, you're going to get an explosion of code size. And this refusal to inline means that they don't really get optimized very well. And in practice, we've seen that really. So my question is, if we're doing like a new kind of range thing, maybe we should consider changing the API to one that is prone to optimization, one that uses maybe a single method when possible to iterate, just like op-apply, so that inlining works, and then we get the true performance that we were sold.
I'd have to think about that more and look at the details. Certainly part of the goal here is to restrict how much we're changing. If there are enough significant issues that we've missed, then we will look at adjusting what we're doing. Certainly if you have solid information on that kind of thing, and post in the news group so we can discuss it and look at the details, we can look at what we would do to change it. Ideally, we'd be able to just do basically what we're doing right now, but if there are some significant performance issues and there's something very clear that we can do that was different, we may look at doing so. But like at the moment, at least, this is the current plan.
Okay, thanks.
Okay. So when looking at the C++, the corresponding range API for C++20, I'm counting to 12 ranges in their hierarchy of the concepts. So I'm just thinking it might be worth considering extending the range hierarchy if there's some recurring patterns on how the template restrictions are going to be modified.
Well, I mean, if you have some concrete things there that you think would improve things, you want to post in the news group, we can discuss it. For the most part, it seems like we arguably have way too many traits already dealing with ranges, and all the static shift branches and everything you have to deal with various types, that it can become very complicated. So if some extra complication would bring us some real benefit, it may be worth adding, but I don't want to be making significant changes like that without a clear benefit.
So regarding the complexity, I think somebody else kind of mentioned it, but I don't think you can require O1 for everything, because you don't know what the underlying algorithm, like map, you can't require that pop front is going to be.
Well, it's O of 1 in the length of the range. So technically, in the case of filter, it's arguably O of 1 because of the length of filters range. Yeah. It's not O of 1 with regards to the underlying range.
And in the case of filter, the only one that's going to incur an O of n is the first time you call front. So it's like,
Yeah, so
we'll call it the front. But I think the main thing is like op index needs to be fast.
Yeah, so if there are enough examples, we may adjust that, but the main thing is that those need to be defined reasonably well so that you can rely on it. And if there's some exception in there where we go, well, this range technically doesn't do that, performance characteristics don't change code behavior in the sense of it's going to do the wrong thing. It's just going to be slower. So there's nothing stopping you from doing something dumb, like saying, hey, this is random access range, even though we have to iterate through the whole thing to get at things. Right. So we can, have exceptions to some of that if need be, and we may word the requirements slightly differently. But in general, we're not supposed to be iterating through the whole range to do all these various operations.
I think it's good to document the expectation of this is how many times someone might call your front function. This is how many times someone might, so plan for that, And the other thing I wanted to say is if the gentleman who spoke earlier about the inlining problems, if we could get that in a bug report somewhere with an example, that would be really nice.
I have a question. If I have a range where I have front, for instance, which is pure, can't it just be inlined? Why can't it be inlined? If it's a pure function?
I don't know what all the inliner is going to do on all that. I'm not an expert on when exactly it inlines and it doesn't. So I can't really say. I mean, for the most part, pure doesn't actually change much in terms of what the compiler does. And I don't think it actually gets used at all by the optimizer, at least for like LDC and what have you. But I'm not 100% sure. Certainly, if there are issues with what's being inlined, we should be looking at those and seeing whether it's worth making changes to make that work, or whether it changes too much. But like, this is the first anyone's brought up that particular issue in terms of it being impossible to inline that stuff, even though it arguably should be.
One more question. Did you try to also specify the difference between computing a value and just returning a value or returning a copy? For example, with front, if we call front 2 times, does it mean that we compute something possibly with effects 2 times? Or should it have some guarantees about that each element is only computed once? Are there any attempts to clarify this?
It is required that it returns the same value every time. As far as computing it goes, as things stand, that's been completely left up to the implementation as to what they do it. I don't know if it makes sense to require it to be in one of the other. Part of the problem is, like, say, in most cases, for instance, you would do the work in pop front. It wouldn't make sense to do it in front. You're just going to do the work in pop front and store the thing, and then you return it from front. But in the other cases, like, say, map, it can't do that because it potentially works in random access ranges. And so you got stuff in the middle. It's not going to be caching any of that because that would be nuts. So we may lock that down a little bit more if we can find some clear requirements on that to make it clearer. I think certainly we need to specify some of that a little bit more cleanly. Like, technically right now, you could do work in empty to determine what was going on with that, and that at minimum should be discouraged. We may lock that down somewhat further, but I haven't done so at present.
Cool. I think we got 2 more questions left. One up the back.
So my question right now is that given that range is something standardized by D right now, and we have an implementation of the UDA must use, I was thinking about we having UDAs for enforcing range APIs, especially because whenever you want to enforce some kind of ranges, you must import standard range interfaces. Also, you have to write plenty of ugly checkings inside your code. And I was thinking about if we had this user-defined attribute, we could have better messages, better checking at compilation time, and even less code emission for being stripped by the dead code.
I'd have to see examples to see exactly how that would improve things. And as a general rule, I don't think it's going to be very pleasant if you have to put a bunch of UDAs and stuff. If it makes sense to have it as an optional thing to give some extra information in some cases, that may make a lot of sense. But as it is, we have to mark up stuff with way too many attributes in too many cases. So if basic range stuff requires a bunch of attributes, even if they're UDAs, to do it, that's going to be really annoying. So I'd have to see some concrete examples of what exactly we'd be getting out of that to see changes. Certainly an optional thing is a lot more palatable than something that would be required.
Yeah, I'm almost sure we had like compilation time tolling when I think Steven made a blog post on that about checking about range properties when you had like a plenty, and I saw that it had more memory usage for the compiler, and also the compilation time went like a little above than one would expect.
Well, ranges in general, we have an issue with compilation time in the sense that there are a lot of traits. There are templates that get instantiated with this whole mess. So just as a general rule, if you can reduce how much we're doing with that, that would be nice, just so we can help improve it. We can't remove all of it, but like as Adam was talking about yesterday, reducing template usage, at least in terms of the depth of things, would help considerably, because we're just instantiating too many stray things. And if we can reduce that where we don't need to, that's going to improve compilation times, as well as reduce the number of stray symbols that there are.
So I'd like to quickly go back to Steven's question about the running times. I think having some sort of universal requirement that front should be constant time is just a non-starter because of ranges like map, where the front will evaluate a user-defined function, and that may in turn use range algorithms inside, right? And so I think requiring a front of map to be O of 1 universally is on the same level as requiring that every loop body is O of 1. And I think nested loops are useful.
Well, it's O of 1 with regards to the length of that range. So if you're doing a whole bunch of stuff internally, it's not necessarily O of 1 in regards to the internal ranges that it's operating on. We can certainly adjust how we list that requirement. It's not a hard requirement anyway, in the sense that your code's not going to behave incorrectly, even if the algorithmic complexity is garbage. But if you want to be able to rely on the algorithmic complexity with regards to algorithms, we have to actually specify what the required algorithmic complexity is. And if you do something that doesn't match that, then okay, fine. Just you're not going to get the algorithmic complexity that the algorithm is saying it does.
Yeah, I mean, I just think you should specify it on a per range basis. Each range should say how fast it is.
Yeah.
Particular for map, you just say it calls the user supplied function once per each call to front, right?
Okay. Yeah.
All right, we got Walter and Attila need to provide some more input, and that'll be at the end of that. So Attila.
About the UDA thing you were talking about, it would be just one UDA per type, basically stating this is an input range, forward range, whatever. And I have a prototype, I guess, of that in the concepts library. So maybe we should think about that. So this is something that exists already. The only problem is you have to do it by convention. So the code that would usually go into is input range goes into a separate function, and then is input range, the template constraint calls that a compile time. And then this thing is then used for error messages. Basically what you try to do is try to verify that it's an input range, and if it isn't, it throws an exception or static assertion.
Okay, I mean, we can look at it and discuss it as far as that goes.
I think we're focusing too much on things like O1. I mean, at some point, think of how your range is going to be used and be reasonable in your implementation. If you're using a range that, has to start from the beginning and iterate to its correct position and then return, you're going to get horrible performance, and that's on you, the designer of the range. I don't think it's the specification's fault if you make a pathological implementation of a range. There's just, common sense with this. Just try to make your ranges as efficient as possible, and you'll be fine.
Cool. Anything else? No?
No?
Cool. Then I believe that's all that needs to be said on the subject ever, and you should not discuss this on the forums, correct? Perfect. Thank you.
Yeah, because that's how things work.
All right, and with that, that is the second day of DConf 2024 out of the way. Eat and be merry. We do have BeerConf again, not sponsored this time. It is at the Travelodge just up on City Road there. It's like 500 meters. You can't miss it. But otherwise, we have about 10, 15 minutes to get out of this building. So you please pack up and let's move on. And see you all tomorrow morning.